Welcome to Python for Data Structures, Algorithms, and Interviews. I'm Jose Portilla, and I've taught thousands of students on Udemy about Python programming and data science. And now, I've created a course to help students with the interview process. This course will help you ace the type of coding interviews done at the top technology companies. So, what do you get with this course? This is a 3-in-1 course. It includes lectures on data structures and algorithms to cover computer science theory, plus coding questions asked in real interviews and answers to them, as well as non-technical interview preparation, such as resume reviews and doing well in in-person interviews. This course is packed with tons of content. You'll get lifetime access to over 200 lectures, where every lecture consists of a video with clear explanation of a topic, along with a notebook of written code and explanations for reference, so you can learn in whatever way works best for you. We cover everything you need to know to ace your coding interview. Overall, the course consists of non-technical interview preparation, reviews of all major data structures and algorithms, practice interview problems, and mock tech company interviews. So, who is this course for? This course is designed for a variety of audiences, including self-taught programmers who already know Python and want to learn about data structures and algorithms and begin interviewing for tech positions, as well as students currently studying computer science and want supplementary material on data structures and algorithms and interview preparation for after graduation, as well as professional programmers who need practice for upcoming coding interviews. And finally, anyone interested in learning more about data structures and algorithms or the technical interview process. With this course, you don't just get high-quality videos and lecture materials. You also get a program designed to effectively teach you what you need to know efficiently as possible. It's like having private tutors design an interview study curriculum just for you. You'll also get to join our community of students who are quick to help with their feedback and share their thoughts, as well as access to the discussion forums where I'm always around to personally help you. This course comes with a 30-day money-back guarantee. If you're unsatisfied in any way, you get your money back, no questions asked. Plus, you can keep all the lecture notes as a thank you for trying out the course. This course will help you achieve your career goals in software and technology. A career in this field is rewarding because of the interesting problems you solve, the financial benefits, and the freedom it offers. Check out the next preview lecture for a full overview of the extensive curriculum of this course. Alright, so what are you waiting for? Start the next chapter in your career and enroll today. Welcome to the course curriculum overview for the Python for Data Structures, Algorithms, and Interviews course. There's a lot of content in this course, but it can be broken up into 3 major components: the non-technical sections, the technical sections, and the mock interview sections of the course. Let's begin our discussion of the course curriculum with the non-technical sections, since those appear first. To begin the course, we have a discussion of company and job types. This section of the course discusses the company types and the various job types available to you in the software technology field. After that, we have a discussion on resume preparation. You'll get hints and tips on how to prepare a great resume, as well as a list of resume creation tools for you to access online. Then, we have an online presence section. You'll learn how to establish your web presence for recruiters on websites such as LinkedIn and GitHub. Then we discuss networking. In this section, you'll learn how to build a network and leverage it for job opportunities. After that, we have the job searching section, where you'll learn about tools and resources to use on your job hunt, such as job search sites, how to organize your job search, and a list of company matching sites. Then we have the non-technical interview questions and answers section. In this section of the course, you'll get ready for your interview with the fundamentals. You'll learn the 5 steps to ace an interview, and you'll also have a list of interview questions and answers, as well as discussion on each one and how best to prepare for the non-technical portion of the interview. After that, the post-interview section. In this section, we discuss post-interview topics and learn what to do after you have your interview. This includes things like salary negotiations and preparing your references. Once we do those topics, we'll have the technical sections. This will begin with a technical material installation guide to make sure you have all the materials you need as well as a setup on your computer regardless of your operating system in order to do the technical questions and have all the materials set up for you beforehand. Then we get to the meat of the course, algorithms and data structures. Each of the specific algorithms and data structures sections has two parts to it: theory lectures and practice interview problems specific on that particular algorithm or the particular data structure discussed in that section. The algorithms and data structures we discuss are algorithmic analysis and big O notation, array sequences, stacks, queues, and Deques, linked lists, recursion, trees, searching and sorting algorithms, graph algorithms, and riddles. Again, each of these sections includes lectures on theory and the topics such as algorithms and the various data structures we discuss, and then the second half of each of these sections has interview problems focused on that specific topic. Then we have the mock interview sections. In the mock interview section, we simulate 4 mock interviews with 4 separate companies. They include simulating an interview with an e-commerce company, a large search engine company, a rideshare company, and a large social network company. Each of these mock interviews consists of tons of questions, as well as the answers and solutions to them, all explained in a mock interview format. After all that, there's a lecture with bonus special offers for my other courses in case you're interested in expanding your knowledge. Okay, with all that being said, it's time to begin the course. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on Company Types Overview. So in this lecture, we're going to give a brief overview of things you can expect from various company types and the size of companies. In this lecture, we're just going to cover what Big Four companies are like and what that term actually means, medium-sized companies, and then startups, which we're going to divide into startups that are small, about 1 to 15 employees, and then well-funded startups. Okay, so first off, what does the term Big Four mean? So Big Four is just a collective term for the top 4 large public tech companies, and there's actually more than 4 of them, but the famous ones that are usually grouped together are Microsoft, Facebook, Amazon, Apple, and Google/Alphabet. So when someone's referring to the Big Four, they usually mean some of these type of companies. So what do we know about the Big Four? Well, the culture can actually vary greatly between all of them. So you should check out Glassdoor reviews for specific information on each of them, since the culture at Amazon can be really different between the culture of Microsoft or Google or Facebook. We also know that they recruit heavily from the top 5 to 10 universities, based on the US News rankings. Since these are large public tech companies, they usually have some sort of strong management structure in place and some sort of formal onboarding process for new employees. You should also take into account that decisions at the company level need to take shareholders into account, since they're large public companies. Now, there are exceptions, such as Amazon, who has basically, instead of focusing on profits, have put a lot of their revenue back into the company. One last thing, you should also note that they have a huge amount of applicants, so networking is the key to getting a job at a Big Four company. Up next are medium-sized companies. So these can vary greatly, but they're usually local companies, and they may have a few satellite offices. There also may be a stronger focus on profitability, since if they're already a medium-sized company and don't have any funding since they're not a startup, they need to focus on profitability in order to keep the bills paid. Management structure can possibly be more informal. You have to try to ask about this during your interview, and we'll touch more on medium-sized companies in general later on in this course. And then startups. So focusing on small startups, the ones that have between 1 to 15 employees, you should note they usually offer lower salaries but higher equity, and you should also keep in mind the high probability of failure. About 90% of these startups fail within the first 4 years. Equity can also be a complicated subject, so you should check out this link right here, stockoptioncouncil.com, and just Google around so you can really understand what an equity percentage means and the type of stocks that there are available to you. The pros of a startup at this level is you're going to learn a lot, but you're also going to have to work a lot. And it's important to understand that people and the early hires are key at this stage. So if you're interviewing at this type of company that's still small, you should really make sure that you get along with everyone you interview with. So the other type of startup are the well-funded startups. These are the type of companies that you've heard that have had huge funding rounds, such as Uber or Lyft, those kind of companies. So salaries at these well-funded startups can be comparable to Big Four large public tech companies. But you should note that equity at this stage can be pretty complicated given the large amount of funding rounds. So keep that in mind and really do your research to understand what an offer of equity really means. For a good list of these type of companies, you can check out breakoutlist.com. And you should keep in mind that funding doesn't guarantee success. Alright, so in conclusion, always research the companies beforehand, and you should really be thinking about your work-life balance and what your long-term career goals are, and what type of company is right for you. So we're going to touch on this topic again later on in this course, so this was just a brief overview. Up next, we're going to get a brief overview of the various job types in programming. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to this lecture on job types overview. So we're going to categorize job types in programming into 7 different categories. Those are infrastructure, back-end, front-end, native, science and theory, marketing, and then finally hardware and graphics. So one thing to note is that there's definitely overlap between the skills required for each of these positions, and even some titles will overlap between categories. So just keep that in mind. First up, infrastructure. So there's sysadmin, which is a position where you manage, set up, and keep systems running. And then there's also DevOps, where you create and use tools that developers use to manage systems. There's also network engineering, setting up, designing, and optimizing network infrastructures, as well as data center operations, who basically keep the cloud running. Along with that, there's also cable and router technicians, database administrators, and then technical support and documentation staff, who actually have to interact with customers and users. Then there's backend. So there's quite a few positions here. There's full stack engineers who do a little bit of everything, backend application development, who use things such as Rails and Django, so Ruby and Rails, and then Python for Django, Node, etc. There's also project management, which isn't always a technical role. And then there's engineering management, where former developers usually get hired into a management position. Just keep in mind that the terms product management, project management, and engineering management may mean different things at different companies. There's also software architects who plan out features before they're actually coded. There's also API design, where you design interfaces between systems. Security and penetration testing. Distributed system architects, who deal with consistency, availability, partition tolerance, timing of large globally separated systems. And then there's also database administrators. Then the front end. So the front end, there's full stack engineers who again do a little bit of everything, but they're focused primarily on the pieces that support a front end of a website. So then there's UX and UI front end designers who deal with Photoshop, InDesign, Sketch, HTML, and CSS, etc. That's their piece of the pie there. Then there's general front end web development, so HTML, CSS, and JavaScript. Single page app development, so those are people who mostly deal with JavaScript frameworks such as Angular or React. Then there's also quality assurance and testing, so you write tests, do human tests, make sure things actually work. Then the next category is native. So these are people who develop in iOS or Swift, Android, Windows Mobile, etc. They also work on consumer-facing Windows desktop applications, OS X desktop applications, and even Linux app development. There's also enterprise software development, so large made-to-order applications for businesses, IT administration and admin software design. These are often very system-specific, hence they go under the native category here, and also software architecture, similar to that back-end architecture role where they design features before they're actually coded. Then there's the science and theory category. So there's scientific research. These are people in academia who use MATLAB, R, and IPython, and more, those kind of things. There's also pure computer science or pure math roles where they research with Haskell, Lisp, and lots of other languages. There's scientific software development. So for instance, there's some companies working on protein folding software, a lot of biotech companies. There's just the general term data science, which is what I do personally, which again is MATLAB, R, IPython, scikit-learn, etc., and machine learning, which also falls under data science. Then there's OS design, which isn't just Microsoft, Windows, and Linux, but also things and companies such as Qualcomm and lots of other telecoms hire tens of thousands of engineers to write embedded and mobile operating systems. There's also marketing, which has a lot of crossover with data science, but terms like growth hacking or web scraping, where they use Selenium, Beautiful Soup packages for Python, Phantom.js, scikit-learn, which is a machine learning package for Python, Pattern, etc. There's analytics, so you can use Mixpanel, Optimizely, etc. This is also closely tied with marketing and SEO, search engine optimizations, and then just general marketing development, things such as Salesforce, analytics, content design, and again, search engine optimization, SEO. Finally, there's hardware and graphics. So there's embedded software. This is known as code that runs very close to the metal, such as the assembly code running an elevator. There's also chip design and architecture. There's game development, which a lot of people feel is much different than normal development, so just keep that in mind. And there's also graphics software development. Sometimes there's crossover between that and game development. Then there's 3D printing and machine coding. And then there's CGI and animation. Alright, I know that was a ton, so you can go ahead and check out the resource link at this lecture for this PowerPoint presentation, so you can look over the positions slowly on your own time. But in conclusion, most engineers and programmers have skills in multiple categories. So just think about what interests you as you go on and continue throughout this course. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on resume preparation. So what we're going to do for this lecture is check out a sample resume and highlight 12 key factors from it. So on your left, we have our example resume, and the first thing we're going to notice is that it's one page. So recruiters do not read your resume. They do about a 15 to 30 second spot check of your resume. When your resume is too long, it just takes your best stuff, the stuff that would have made the one page cut, and dilutes it with more mediocre content. So lengthy resumes don't make you more impressive. A good rule of thumb is to keep your resume to one page if you have less than 10 years of experience, or at most 2 pages if you have more than 10 years of experience. The second point we want to make here is there's no objective statement. So all an objective does is state in a wordy way what position you're interested in. So the company already knows that because you applied for a particular position. So at best, it's just going to waste space. And at worst, it'll limit you since it'll exclude other positions that might have been interesting to you, that the company may have been considering you for. So again, my recommendation is to not put an objective statement on your resume. Third point we want to make here is to use a resume template with columns. So unless you're great with design, you probably shouldn't be creating your own resume template. It'll most likely just look sloppy. So after this lecture, we'll go over some resume creation tools, and in the third lecture of this section, there's actually a list of resume creation websites. So again, you'll be using a template of some sort. Don't try to do it on your own unless you're actually applying for a position where design is a key factor to your skills. Number 4, use tables. So again, if you're using Microsoft Word to create your resume, which you probably should, or at least some sort of Word editor, you should use Microsoft Word's tables. Just make sure to hide the borders afterwards. So if you look at number 4 here, this allows you to organize things better. So point number 5 that we want to make is to keep bullets short. Because resume screeners only spend anywhere between 15 and 30 seconds on your resume, the length of the bullets, anything that feels like a paragraph, just won't get read. So keep your bullets to 1 or 2 lines, with 1 line being better than 2. Point number 6 we want to make is that accomplishment oriented. So your bullets should focus on your accomplishments, that is the impact you had, rather than your responsibilities. So you should be describing what did you build, create, design, optimize, lead, etc. Another key factor to a good bullet point is to quantify things. So whenever possible, you should quantify your accomplishments. If you optimize something, by how much? If you won an award, out of how many people? If you saved a certain amount of money on a project, how much? Okay, this is more for students, but on number 8, your general rule of thumb is to list your GPA if it's at least 3.0 or higher. But there are 2 important rules to know here. The first one is you may choose to list your in-major GPA if it's higher than your overall GPA, but you need to specify that it's your in-major GPA. Point number 2 here is if your school uses a different scale, such as a 10-point scale, you may want to convert your GPA to a 4.0 scale, which will be more widely understood, especially if you're applying to USA companies. Point number 9 is projects. So most candidates should pick their top 3 to 5 projects to list on their resume. These can be academic required projects or just independent projects that you decided to take on. They do not need to be completed or launched either. As long as you've done enough of the meaty amount of work on them, that's good enough to put them on your resume. Point number 10 on additional experience. So you can put additional experience like leadership activities or awards in a section like this, such as shown on this resume. So change the name of the section depending on what you list. Be careful here to focus on what really matters. If you're applying for a coding role, your role as an Eagle Scout in high school is probably not really important or relevant to the position you're applying to. Point 11, languages and technologies. So it's a good idea to list your languages and technologies, but remember that anything you list here will be fair game for the interview to test. So if you want to list a language but you happen to be a little rusty in it, consider listing it as something like C++ proficient, C#, prior experience, etc. So you actually quantify your experience in each of those programming languages. So point 12, what did you not include? So you got to remember, is there anything impressive or interesting that you've done that you left out? About 50% of candidates leave out an important project or other component of their experience because it wasn't finished or official enough. So if you've done it and it's impressive enough to make the cut, you shouldn't just list everything you've ever done. Keep that in mind. But if it's impressive enough to make the cut, then it belongs on your resume. Alright, so up next are resume builder websites and a list of resume creation websites. Thanks everyone, I'll see you at the next lecture. Hello everyone, and welcome to this lecture on resume creation tools. So there's actually a lot of free resume creation tools online, so we're going to go ahead and explore them. Keep in mind real quick that the next lecture contains a full list with links to all the resources we're going to check out right now. So let's go ahead and get started and jump to the browser. Okay, so the first website we're going to check out is CV Maker. That's at cvmkr.com. And it's one of the websites that allows you to create a professional resume. It looks quite nice, and it's all free. And it lets you export it to various formats. So you can go ahead and check that out. Here are some of the examples of what those resumes look like. Next up is livecareer.com. So this whole company starts off with a resume builder, but they also give advice on cover letters, interviews, various job applications, and other resources. So the whole company is kind of revolving around finding and interviewing for jobs, but they get started with a free resume builder that's also based off your LinkedIn profile. Next up is resume.com. So again, easy online resume builder, and it's free. So you can create, edit, and share your resume using resume.com. Another one, resumegenius.com. It's another one. You can create your resume online in about 15 minutes. You can check it out. Resumebuilder.org. You'll probably start to notice that there's a ton of these sort of websites, so you can also Google around for your own pleasure if you're not liking any of these. There's also hipcv.com. Again, stylish professional resume, minutes for free. Save it as a PDF. There's also cvease.com. It's free for a starter package, but they also have a premium with more tools. But again, you just create and download a PDF of your resume for free. And then there's also visualcv.com, which allows you to create a personal portfolio and customize PDFs to help you land your next job. And then I also wanted to show you some links to templates. So here we have links to Google Doc templates, and these are just either cover letter or resumes. So you can go ahead and check out this link in the next lecture, In case you like working on Google Docs, there's plenty of already made templates for you to check out. And in case you like working on Windows with Microsoft Word, you can check out the next link and it'll take you to this templates for Office. And pretty much all of these are free. They're all resume formats already ready for you to use in Microsoft Word. Alright, so I know that was quite an overview and there was just a ton of websites for you to make resumes and CVs. So I really suggest that you go check out the next lecture called List of Resume Creation Websites. It's just a PDF file with the list of all the links. Check out, use the ones you like that work best for you. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on LinkedIn. In this lecture, we're going to discuss what LinkedIn is and how best to take advantage of it in your job search. So, LinkedIn is one of the most important social media platforms for job searching and networking, and it's imperative to have one as you begin your job search. So, in case you're not familiar with LinkedIn, LinkedIn is a business-oriented social networking service. Something to note is that most of the site's revenue comes from selling access to information about its users to recruiters and sales professionals, meaning a lot of recruiters at large corporations actually have their company pay LinkedIn so that the recruiters can use it to find people looking for jobs, people like you. So, if you don't have a LinkedIn profile yet, you should go make one right now, before continuing on with the rest of the lecture. Something I want you to note, though, is you can actually use your email contacts to get connections. So keep that in mind as you create your profile. LinkedIn should automatically ask you this and get a pop-up as the image shows here on this slide. So again, go to LinkedIn and create a profile, explore the website a bit, and then come back and complete this lecture. Alright, so you may already have a LinkedIn profile, you should have created one, looked around a bit. Let's discuss some of the features of LinkedIn. First off, LinkedIn recommendations. LinkedIn recommendations are a bit almost like a letter of recommendation on your LinkedIn profile. If you want a recommendation, you should start off by asking people you've worked under or with to give you recommendations. Always remember to thank them, and if possible, return the favor by recommending them back if it's appropriate. You can also ask professors and teachers to leave recommendations on your profile under your education section. Again, you should really only ask people you personally know for a recommendation. Next are LinkedIn skill endorsements. When you're creating a LinkedIn profile, there's a skills section, and you may have skills such as programming or Python that you'll put on your user profile. Other users can endorse you for these skills. Having scores on these skills might give your profile an edge. Some recruiters keep an eye out for these, others don't really care. Their actual usefulness is kind of debatable. Different people vary their perception of them. Some people think they're worthless, some people take them really seriously, but you should at least know that they exist and keep an eye out for skill endorsements and if someone endorses you for a skill. Okay, next, following in LinkedIn. You can actually follow people on LinkedIn, and if you produce content, let's say you have blog posts, articles, or you produce new code on GitHub, you can post it on LinkedIn to your followers, and they're going to see it in their feed and get notified. And you can also add a follow me button if you have a personal website. Next, LinkedIn as a job search tool. So LinkedIn has its own job hunting platform. You can check it out at www.linkedin.com/jobs. So if we hop over to that real quick, it will look something like this. So it'll say start your job search here. You put in job titles, keywords, or company names, the location, and then search. So it's a pretty good job search tool. I definitely recommend trying it out, especially if you have a pretty complete LinkedIn profile. It'll try to match you with jobs that make sense to you. So check it out. We'll discuss other job site search tools and job boards later on in this course, but as far as LinkedIn, you should be aware of this one. And we'll come back to it later on in the course when we discuss job searching tips in general. So let's go ahead and go back to the presentation. Alright, so after checking out linkedin.com/jobs, I want to discuss with you LinkedIn Premium. So LinkedIn Premium is actually a premium service, and we discussed earlier that some people pay LinkedIn to get a premium version of their website. So LinkedIn Premium gives you a few things. It allows you to in-mail people, such as recruiters, and email is basically LinkedIn's own internal messaging system. It also allows you to connect with and contact recruiters more directly, and it gives you improved information on LinkedIn's job search tools. So if you're looking for a job on LinkedIn's job search, having a LinkedIn Premium profile will actually give you information such as how many people have applied to that job through LinkedIn, what's the average education background, years of experience, etc. There's a 1-month free trial, and what I would recommend you do is after you're done studying and you're ready to actually begin applying for jobs, try the 1 month of LinkedIn Premium, use it to contact recruiters, and take advantage of that 1 month, really milk it, and then if you decide you need it more, pay for it. If not, end your 1 month free trial, no problem, you took advantage of it. Okay, a quick note on discussion etiquette. Please be polite and thoughtful when posting your LinkedIn profile to the discussion boards. I want you to feel free to post if you genuinely need help, and try to give honest feedback to other people who have posted their LinkedIn profiles. However, don't just spam the discussion boards on this course with your profile for no reason. Alright, with that being said, here's your LinkedIn homework. You should create a LinkedIn profile, update your picture to a professional looking picture, make sure your face is fully seen in the photo, complete your profile information. You should get at least 10 connections, people you know, people you've worked with, and your final homework assignment is to get a connection to a recruiter, hopefully at a company that you're interested in. Alright, that's it. Make sure to complete that task list, and I will see you at the next lecture. Thank you, everyone. Hello, everyone, and welcome to this lecture on GitHub. And we're going to discuss what GitHub is and how you can use it as a job search tool. We won't go over how to use GitHub, but we'll send you the proper links on how to learn and get trained in GitHub. So, first thing we want to note is that Git, G-I-T, is an open source version control software used to track changes in the code. Git and GitHub are two separate things. Git, G-I-T, is open source software that anyone in the world can download. GitHub is a company and it's a service. GitHub is a web-based Git repository hosting service. So you can host your own code on GitHub for free and keep track of changes to it. So you use Git as version control to keep track of changes, and if you want to host your code online, you can use GitHub's service, and it's free as long as your repositories, the actual place where you're keeping your code, is public. You need to pay the company GitHub for private repositories. And so that's how GitHub makes their money. So even though both Git and the basics of GitHub for public repositories is free, if you want to have a private repository on the web, you need to pay GitHub. Most open source projects have moved to GitHub. Alright, so moving along, if you don't have a GitHub profile yet, your next step is to go to github.com and create a profile. Let's go ahead and jump to github.com so we can see what it looks like real quick. So it should take you here to github.com. You pick a username, put your email, create a password, and sign up for GitHub. Alright, so once you've done that, you can also download GitHub Desktop. And it's a way for you to use a graphical user interface to help contribute to projects. And you can do things such as create branches, make changes, do commits, and deploy, all from a native interface, regardless of what system you're using. So even if you don't understand what these terms mean, you'll probably be asked to download GitHub Desktop, and if you're not familiar with GitHub at all, I definitely recommend downloading it. Alright, so let's go ahead and go back to the presentation real quick. If you're interested in learning more about Git and GitHub, which I highly recommend you do, most companies use Git and GitHub as their version control software. There's two really great guides that GitHub themselves provide. These guides are so good that it's really not worth for me to try to teach you, since these guides do an excellent job of teaching you the basics of Git and GitHub and how to use it. So start with this link, guides.github.com/activities/hello-world, and once you've done that, then continue on to this training website, which is also provided by GitHub. These two links are really fantastic. They're provided by GitHub themselves. They're constantly updated in case there's any change in their platform. So that's why I'm suggesting you go with these two for learning how to use Git and GitHub. So if we just check out these links real quick, they'll look something like this. So this is the Hello World. It takes about 10 minutes to read. It'll teach you how to create a repository, open an issue, create a branch, make a commit, and then open a pull request and merge pull requests. So go through this. It's really great, and it's probably the best introduction online to how to use Git and GitHub, which makes sense because it's provided by GitHub themselves. Something else I want you to know, there's actually video guides. So if you look over here at the top right, you'll see a link to click GitHub, video guides. And if you click that, it'll take you to their YouTube channel here on home. And if you go to videos, you'll see here there's an intro to GitHub on GitHub and Git Foundations. You can go ahead and check those out if you want video explanations on how to go about learning the basics and foundations of Git and GitHub. It's all free and it's all provided by GitHub, so I really recommend you check that out. It's pretty much the best way to learn GitHub and how to use it. One other link I want you to be aware of is the GitHub training link. So you can use these for simple slides on learning on how to use GitHub and teaching other people how to use GitHub. So they're just basic slides teaching the basics of GitHub. So again, really recommend you check out the Hello World document. And if you want video guides, click on the top right, take you to their YouTube channel, and they have plenty of information on the basics, and they also have advanced factors to learn about on GitHub. Going back to the presentation quickly, as far as where GitHub fits into this overall larger picture of your job search, you should make sure to post personal projects that use code to GitHub, as long as you don't mind them being public, and have them be presentable with README files. If you don't know what those are yet, don't worry, after you do the training, you will. Recruiters sometimes look at GitHub for potential hires. So they may search GitHub for certain software packages or certain modules or libraries in a language and see what users have projects in those languages. So it's pretty important to have a good GitHub presence. And GitHub also has its own job search tool. So let's go ahead and hop and check that out real quickly. That job search tool looks something like this. It's jobs.github.com. And similar to the LinkedIn job search tool we just saw, you can enter a job description and location and then search. Obviously, since this is GitHub, it's pretty much directed exclusively to programmers or things that have to do with programming. All right, so that's going to be it. You're just going to be left with a homework assignment to complete. So let's go ahead and check that out. Your homework assignment is this. You need to create a GitHub account, follow the Hello World tutorial if you're not familiar with Git and GitHub. That will take about 10 minutes. Then check out the basics of training link or check out those training videos on YouTube. That should only take about 10 to 20 minutes. Then fork an interesting project on GitHub. You'll learn what a fork is after doing the Hello World tutorial. And then push some code to GitHub. And that's it. That's your homework. Basically, that should give you the ins and outs of a GitHub account. And as you move on throughout this course, you'll learn how GitHub can be used for your personal projects and creating a good web presence. All right, that's it for this lecture. Thanks, everyone. I'll see you at the next lecture. Hello, everyone, and welcome to the lecture on personal websites and online portfolios. Personal web pages are a great way to showcase your online portfolio or your blog, so we're going to discuss some options and set you up with some links to check out and see what works for you. As far as blogging platforms, some of the most popular ones right now are Medium, WordPress, and Blogger.com. I personally like Medium, but I encourage you to check all three of them out and see what works for you. Blogging is a great way to show recruiters that you're interested personally in the topics of programming, and can give them some insight into your own personal projects and what you're interested in. As far as website creation goes, if you plan on applying for web development or UI positions, any job where you're required to use HTML or CSS or JavaScript, you should actually definitely be building your site from scratch. So I'll just leave it at that. Since web development and website creation is going to be part of your job, you should already be familiar with this and you should probably already have your own web presence. If you're looking for more standard programming jobs, then there's website creation services. These services are basically just drag and drop interfaces that make it really easy to create your own website. Some of these services right now include Weebly, Wix, Squarespace. There's tons of options, so Google around for more. A lot of them provide free versions on their own subdomains. So for instance, you could get yourname.weebly.com if you don't want to pay for a domain name. If you do want to pay for your own domain name, I suggest you check out Namecheap or Google Domains as ways of buying your domain. But again, Google around for purchasing domains. As far as the basics of a personal website, make sure to keep it updated during your job search. If you're running a blog, it's a great way to keep track of everything you're learning. So I would definitely recommend blogging your process of learning about different things, about data structures and algorithms. Recruiters love to see that kind of stuff. One final note, personal websites and personal pages aren't really as necessary as a LinkedIn profile, but they can definitely improve your standings among other candidates, especially if you have an impressive online portfolio on your personal website. So with that being said, go ahead and check out some of those links if you are interested in blogging or starting your own personal website, but I'll leave that up to you. It's more important that you focus on your LinkedIn if you're just beginning your job search right now than building up your personal website. So if you're just starting out, I would recommend build out your LinkedIn and GitHub, and then maybe start a blog and keep track of what you're learning so far. All right, everyone. Thanks, and I'll see you at the next lecture. Hello, everyone, and welcome to the lecture about building your personal network. So, it's important for you to realize that a huge amount of job opportunities are never publicly shown. So companies tend to hire through the networks of their employees. If you just apply to a company straight through their job site, if it's a large company, your application may never be actually seen. So it's important to build a network and leverage it when you're hunting for a job. So as far as building a network, it can be difficult to start out, especially if you're young and out of school. So we're going to look at some options to build out your network. So there's a lot here, so you can just go ahead and check out the PowerPoint presentation that's attached as a resources lecture, but I'm just going to go through a few of these. If you're coming straight out of school, alumni organizations and classmates are a great way to go as far as building a personal network. If you're older and already have children, your children's contacts such as PTA, Little League Scouts, or parents of those friends of your kids are also great contacts for building out your personal network. Let them know that you're available for a job and you're looking around. Bring it up in conversation. Former employers, including supervisors and coworkers, your friends, your relatives, members of clubs such as your gym, either your softball team or hiking club, are all great ways to build out your personal network. Again, strike in conversation that you're looking for a job on the market. Also, members of your church, temple, synagogue, or mosque are great resources for building out a network. Your neighbors, both past and current. Even just professionals. Your attorney, your accountant, who your doctor, your dentist is. Who knows, they may have a link to someone who knows that there's an opening at their company. And then volunteer associations. It's a great way to spend time volunteering, and you also may get valuable network connections there. Just remember to be proactive and to give as much as you get. You just can't be taking everything from your network opportunities. You should be giving equal amount of time. So if they're giving an effort in helping you find a job, you should be rewarding them with an effort back. Also, make sure to take full advantage of the opportunities your network provides. In the next lecture, we're going to be discussing networking events and websites to help you find networking events. All right, with that being said, let's go ahead and move on to the next lecture. Hello everyone, and welcome to Networking Events. In this lecture, we're going to discuss how networking events and websites can help bring you into contact with people directly involved in the industries you're interested in. Let's go ahead and discuss some popular tools. First off, just general conferences. You could consider going to a conference to meet people in your industry. Many conferences also have hiring fairs. The best way to find relevant conferences is by Googling either the topic or programming language you're interested in, plus conference. Most official and large programming languages have some sort of conference related to them. So for example, if you Google Python plus conference, it should lead you to PyCon, which also has a hiring fair attached to it. If you Google something like Python plus data science plus conference, you'll get to PyData, which is another Python data science related conference. There's also meetups. So it's one of the original sources for networking, and it's www.meetup.com. What it is, it allows you to meet up with people in your local area who are interested in the same topics you are. So go to meetup.com and look up programming languages and topics you're interested in. I also want you to be aware of Eventful and Eventbrite. The events on Eventful and Eventbrite, you won't get a gathering of like-minded individuals meeting up to discuss stuff. You'll get more of a professional and official event feel there. And you also may need to buy tickets for those events. So just keep that in mind as you explore those websites. Finally, as far as your assignment, you should at least create a meetup profile so you can get notified of relevant meetups in your area. Alright, that's it for this lecture in this section. Hopefully you have a good idea now of the basics of networking, and I'll see you at the next lecture. Thanks everyone. Hello everyone, and welcome to the lecture on organizing your job search. So we're going to discuss various tools for organizing your job search, and we're also going to discuss job funnels. So first off, staying organized is a fundamental part of a good job search. There's lots of tools out there available for you to use, so I'm going to give you some options to choose from. First off, just general spreadsheets. Attached in the resources portion of this lecture is this PowerPoint presentation and an Excel template for you. There's also a Google spreadsheet version, and you can check out the resource links or go to this link right here after downloading this PowerPoint. So let's go ahead and take a quick tour of the spreadsheet provided for you. Alright, here we are at the Google spreadsheet version. Both the Excel and the Google spreadsheet version are the same thing. So we're just going to go over one of them here. First tab is your job search log. So here I'm actually very zoomed in so you can see. But basically you're going to put in the job you applied for, the position title, the company name, and if you have a contact, maybe you contacted a recruiter, or if through networking you got a contact, put that name here. Then there's phone number, fax, email address, mailing address, website. But more importantly, here's what you really want to fill out. Date resume submitted, how you submitted your resume, when you get to that portion, if you send references or not, how you heard about the job, and a job description for you to remember what the actual job's about, comments as well, and then the status of the application. There's also a tab for networking contacts. So after you go to a networking event, this might be a good thing to fill out. It's really similar, but basically just holding contact information, the dates you contacted, and then comments and lead titles. After that, there's the interviews tab. So once you actually book an interview, you can say your interview date, your interview name, and whether or not you sent thank yous and comments on how the interview went. And then the last tab is just career websites. So if you've checked the website, your username, your password on the website, date you posted your resume, date you posted your cover letter, and then comments for yourself. So you should really use this log. I highly recommend it. You have to use some sort of organization when you're searching for jobs. So this Google spreadsheet template is provided, and so is an Excel template of the same format. So check out the resources in this lecture for links to those. Let's go ahead and go back to the presentation. Alright, so we took a tour of the spreadsheet. One other resource I want you to be aware of are some websites. So there's a couple websites that help you track your job progress, your job search progress that is. One of them is known as Job Hero. You can check it out at gojobhero.com. let's go ahead and take a look at it in our browser. So this is what Job Hero looks like. Again, these websites tend to come and go, so make sure you check the resources in this lecture in case Job Hero ever goes down or it's out of business. We'll have the most up-to-date information in the resource section of this lecture. But for now, you might want to check out Job Hero. It's basically a dashboard that will save jobs from across the web and track your application process. It tracks from websites such as Indeed, Glassdoor, Dice, LinkedIn, Stack Overflow, and more. So you might want to check it out, or again, you can use a spreadsheet, whatever you prefer. Heading back to the presentation, let's now go ahead and discuss job funnels. So you might be wondering, why is it so important to track every aspect of my job search? Won't I just remember? Well, most likely you're going to be applying for about 100 jobs. That depends on where you live, job availability, or your experience, etc. But most likely it'll be a number in that range. You have to really apply for a ton of jobs because there's a funnel to this. Job hunting can be extremely competitive, so make sure not to focus exclusively on well-known companies because there's plenty of great opportunities at companies you haven't heard of yet. As far as what your job funnel may look like, you're probably going to apply to somewhere between 100 and 150 straight-up applications, either through your networking or people you have met through LinkedIn, or even just on the job website itself, so the company website. Then you can expect about 20 to 30 responses, somewhere in that range, depending on your experience and your resume. After that, you'll probably get passed to about 10 to 15 phone screens, then about 5 to 10 on-site interviews, and if the company happens to do second stage on-site interviews, around 2 to 5, and after that, you'll probably expect to have 1 to 3 offers to compare it to. Now again, this can really vary depending on who you are, what school you went to. If it's a popular school for recruiters, you may get way more offers and way more on-site interviews. Or if you have a lot more experience, you may get better access for interviews. So this could really vary depending on who you are. So just keep that in mind. But most likely, you'll have to do more applications than you think you're going to have to do. So on that note, make sure to not get discouraged. You're already on the right path by taking this course. So with that all being said, go ahead and check out the resources for this lecture to get all the links and all the templates, and I'll see you at the next lecture. Thanks everyone. Hello everyone, and welcome to the lecture on job search sites. So we're going to discuss a variety of sites and job boards, and you can go ahead and check out the next lecture for a continuously updated list of links that we're going to discuss in this lecture. So let's go ahead and jump to a browser to check out the sites. Again, quick reminder, in the next lecture, there's a list of all the sites that we just checked out here with their URL links. So let's jump to the browser. Okay everyone, first site I want to let you know about is angel.co/jobs. This is focusing exclusively on startup jobs, so you can go ahead and apply to thousands of jobs with just one profile. What's also nice about this is you usually see salary and equity up front. Now a lot of times they're inflated, so just keep that in mind when you're applying to companies here. But you can go ahead and make a profile, and remember this is focusing exclusively on startup jobs. So, up next is Glassdoor. So Glassdoor, in case you're not familiar with it, is a job review site, so you can actually review your current job or more your current company. So people working at a company, let's say Google, if they're enjoying their job, they give feedback to Glassdoor and say, hey, I rate Google a 5 stars out of 5 stars to work here. Now Glassdoor also has a job search, so you can look up your job, location, search, and see if there's any connections that way. Next up is LinkedIn. LinkedIn has its own job search tool that you can use, and you need a LinkedIn profile to use it. And as I mentioned back in the LinkedIn lectures, if you have LinkedIn Premium or on the LinkedIn Premium free trial, you'll get extra information about the people who are applying to the same jobs you are. So it may give you an advantage there. After that, there's Indeed.com. Indeed's a general job search engine. So you just put in your job title, keywords or company name, your location, and then you can go ahead and search for it. After that, there's Monster. You may have heard of Monster. It's pretty famous. It was one of the first job hunting / job searching websites. Again, put in your job title, search for location, see if anything pops up that matches. Dice, really similar. It's more focused on the tech side of jobs, so just keep that in mind. Again, put in your job title, keywords you're looking for, location, then find tech jobs. After that, there's Stack Overflow careers. So if you ever had an error and were looking up error hints or how to fix your code, you probably ran into Stack Overflow. So Stack Overflow also has a careers section where you can put in keywords, your location, and search for jobs on their listings. If you're looking to get into Android development, there's androidjobs.io, and this will be focusing more exclusively on just Android development. So keep that in mind if you want that as an option. Another job search site is simplyhired.com, similar to indeed.com. Put in the keywords, location, and you search your jobs. And then finally, if you're looking for an internship, right now there's a website called www.looksharp.com, which focuses exclusively on internships for trying to help students find careers and entry-level jobs. Again, not all of these are tech jobs. Most of them are not, so just keep that in mind when looking through this website. So that's it for all the job websites. Make sure you check them out on your own time, see which ones you like, and use those. I won't go into any more details here because you have the links in the next lecture and you can check them out on your own time. Alright, with that being said, I'll see you at the next lecture. Thanks everyone. Hello everyone, and welcome to the lecture on company matching sites. In this lecture, we're going to learn what a company matching site is. We're going to look at various company matching sites, and you can check out the next lecture for a continuously updated list of links. So don't worry about marking down the websites we're going to check out. In the next lecture, there's a list of all the links you can check out yourself. So let's go ahead and jump to the browser to check out the sites and get an explanation of what we mean by company matching sites. Okay, so the first site we're going to talk about and give you the premise for what a company matching site is hired.com. H-I-R-E-D, Hired. So this is one of the most famous of these sort of company matching sites. And what you basically do, and this is the premise for all of these type of sites, is you fill out a profile, answer some questions, and if you're applying for a technical position, such as a programmer or developer, you'll get some sort of technical challenge that's timed on some sort of website or browser interface. You do the challenge, and if you pass the challenge, then you get matched with employers looking to hire candidates. Hired in particular, you answer a few questions, do their challenge if you're applying for a technical position, and then companies send you offers and they give you the compensation they would provide you with up front. So you know right away whether an interview process is worth going over. Again, these are really interview offers. They don't give you straight up job offers. You still have to interview with the company. But if you're lucky enough to get a job through Hired, you'll get a $2,000 bonus from Hired. A really similar website is White Truffle. Again, one application, one profile. You pass some sort of coding challenge and you get matched with a couple thousand companies. Okay, next site we're going to talk about is Indeed Prime. So Indeed Prime, same thing as White Truffle and Hired. I know we talked about Indeed.com, which was a basic job search tool, but Indeed Prime, you fill out a profile, pass a technical challenge, and if you get matched with a company and take the offer, you get a $5,000 signing bonus from Indeed. If you're interested in working at a startup, you can check out underdog.io, which is the same thing as the other sites, except it's focused on startups. If you're wanting to work at a YC startup, so Y Combinator is an incubator for startups. It's probably the most famous one in existence. If you're interested in YC startups in general, you can go to triplebyte.com. That's Triple Byte, B-Y-T-E. And it will connect you after applying and passing their technical interview with YC startups. And then finally, there's Anthology. It used to be called Poachable, but it's the same thing. You create a profile and you get better job matches using what they call confidential data, so private employer data. All right, go ahead and go to the next lecture. Check out the links. Again, you should really study your stuff and know coding problems well before you check out these sites. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to an overview of the interview section of this course. So in this section of the course, we're going to be discussing a few things. One, the basic 5 steps of any basic interview process. Then we'll go over tough interview questions and how you should answer them. And then we'll go over questions specifically designed for students and how to answer those questions. And finally, some special case interview questions and how best to approach them. So, with all that, let's go ahead and get started. Hello everyone, and welcome to the lecture on 5 steps of an interview. In this lecture, we're going to discuss the 5 major components of the non-technical parts of an interview. Those include preparation, arrival, introduction, communication, and closing out the interview. So let's start with preparation. If you have a morning interview, you're going to want to get up earlier than usual. So for instance, if you usually wake up at 7 a.m. and your interview's at 8:30, try to wake up either an hour or 2 hours before usual. So wake up around 6. That way, once the interview comes around, you're fully prepared and awake to tackle it head on. Also, the day before, make sure you confirm the appointment time and location. Also, make sure to bring extra resumes. A lot of times you'll be informed of how many separate interviews you'll be having in a day. For instance, you'll have 4 half-hour interviews. So always bring resumes for every person you're going to be interviewing with. They usually have some, but sometimes they forget them or don't have them printed out for them. So make sure you bring extra resumes as a tool for them to help interview you. Also, always make sure you have proper directions and the name of the person you should ask for when you arrive. Up next, your actual arrival. Make sure to arrive 10 to 12 minutes before the scheduled appointment. The moment you arrive, you should consider yourself as making impressions on prospective employers. That includes everyone you meet from the moment you step out of your car. You want to show confidence and smile and make a strong initial impact. Also, before meeting the receptionist, you should visit the restroom, view your appearance, and take care of any business. And then be aware of your body language. It's really important that you come off as a nice, confident person, even before you actually start your formal interview. Then your introduction. So make sure to give a firm handshake with a smile while maintaining eye contact. You should speak with confidence and energy, and you should also try to determine that specific interviewer's communication style and adapt to it. So for instance, if he or she tends to break into smile frequently, you should also be smiling often. If he or she doesn't, you want to avoid grinning too much, so try to adapt to your interviewer's communication style. Up next, communication in general. So make good use of openings, and what I mean by that is, for example, if the interviewer begins by saying, "Tell me about yourself," you're already in control of an early part of the meeting. So deliver a quick 30-second personal overview of your background, maybe beginning with education, followed by some sort of 60 to 90-second overview of your career. So like X numbers of years doing this and that, working for them and these other people. Okay. After that, you really want to make sure you communicate your skills, qualifications, and credentials clearly. Then, demonstrate your ability to adapt and learn. You'll probably be asked some sort of situational questions, which we'll go over later in this course. But questions such as, have you ever been in a position where you had to make a tough decision? Or have you ever had a disagreement with a former colleague? Those kind of questions. And remember, plan, prepare, practice, and rehearse. There's no substitute for good practice for an interview. Next, closing. Make sure to ask follow-up questions. We actually have a list of potential follow-up questions for you to use right before the technical section. So you can go ahead and check out that video and the list of questions for you to ask. Then you'll want to review salary and compensation package after you receive an offer. So that's it for those 5 steps. Those are just the non-technical portions overviews. So after this, we're going to go into some especially challenging interview questions called the Tough Interview Questions lecture. And we'll discuss some tough interview questions, how to approach them, and how best to answer them. All right. Thanks, everyone, and I'll see you at the next lecture. Hello, everyone, and welcome to the Tough Interview Questions lecture. So, some non-technical questions can actually be pretty tricky to answer. What we're going to do is prepare a rundown of them and talk about general response strategies. So, overall strategy should be demonstrate your ability to create, use real examples from the past, and show how you'll fit into the company's culture. So what we're going to do is just get some general practice. What you'll see is a bunch of slides with questions on them, And for each question, after I ask it, go ahead and pause the video and then attempt to answer it. Afterwards, play the video and then listen to some general response strategies. So your first question is tell me about yourself. Go ahead and pause the video now and try to answer the question. Okay, so hopefully you attempted to answer, tell me about yourself. Some general strategies. First off, this is one of the first questions you're going to encounter. It tests your composure, communication skills, and ability to develop some sort of rapport with the interviewer. Prepare a 60-second script which breaks the ice in the first 30 seconds of an overview of your achievements. And then the second half should include mention of your recent professional or academic accomplishments to enhance how good of a candidate you are. So again, just a brief personal background overview. Include your academic background if you're a recent student, or some key accomplishments or credentials depending on the type of position and your experience. And then you also want to include the most impressive or differentiating strengths that will resonate with the interviewer. Next question. Why are you leaving your current position? Go ahead and pause the video and come back to it once you're done answering. Alright, so with this question, the interviewer is probing for some sort of dissatisfaction or discontent. He or she wants to see if you will speak negatively about your employer or supervisor. And this question really tests your character and ambition. So, point is, regardless of the reasons you are seeking a new position, always remain positive and don't complain. Demonstrate that you have a vision of your future. Emphasize that your departure will be professional in any setting. So the key message you want to convey here is that you are sitting in front of the interviewer and considering leaving because you want to grow. You want more responsibility and growth opportunities, and that's why you're leaving your current position. Okay, let's go ahead and go to the next question. Why do you want this position? Go ahead and pause the video now and answer the question. Alright, why do you want this position? This is going to be another common but tough interview question. The answer here will vary depending on the position in the company, but what you really want to come across as is someone with desire, commitment, and passion towards your career goals. That's going to be really important to the hiring manager. So your confidence in answering this question should come from knowing your capabilities, desires, and goals. This sort of self-assurance comes across in an interview in your voice and body language, in addition to the actual content of your answers. Confidence is everything with this question, so remember that. Okay, let's move on to the next question. Where do you see yourself in 5 years? Pause the video now and answer the question. Okay, so with this sort of question, the interviewer wants to see how you envision your future. Evidence that supports the fact that high achievers are also people who have defined goals for themselves. So the interviewer also wants to see how realistic your objectives are and how well they mesh with the company's goal. So just keep that in mind. Let's go ahead and go to the next question. Here's a tough one. What's your greatest weakness? Go ahead and pause the video now and answer the question. Alright, so this is one of the weirder and tougher questions, and I actually personally think it's a pretty poor indicator of how well someone will do in your company's culture. But you should be prepared to answer it because it's a common interview question. The general strategy for this question is to turn this question around and discuss an area that needs improvement. That's not just an outright weakness. Then you're going to want to demonstrate that you're doing something to improve in that area. You should definitely avoid overused and cliched answers such as I work too hard or I expect too much of others. What you should do instead is give 1 or 2 examples of something that won't affect your ability to do the job and that you're improving it. It's not just an outright weakness, it's an area that you're working on improving. Let's go ahead and go to the next question. So, what do you know about our company? Go ahead and pause the video now and answer the question. So granted, the answer to this question will vary wildly depending on what the company actually is and who you're talking to. But after all the work you did prior to this and preparing for the interview, this should be a no-brainer. The answer to this question demonstrates to the interviewer that you've taken the time to research the company and have identified where and how you can contribute. So keep that in mind. The answer to this question is going to change a lot depending on what the company is, but you should be prepared to answer it. Next question is, what's the most difficult situation you had to face at a job? Go ahead and pause the video now and answer the question. Alright, With this question, the interviewer is looking to discover what you consider a difficult situation and how you resolved that situation. Again, this answer should roll right out when you're asked. Prepare a good script for this question and spend about 80% of the time on the solution, only just mentioning the problem itself. Again, you want to focus on the solution to the situation, not the situation itself. Let's go ahead and go to the next question. Next question is, what do you think makes a successful manager? Go ahead and pause the video and answer the question. Alright, with this question, the interviewer is trying to determine your management style and philosophy. Here, the emphasis should be on teamwork, training and development, coaching, and leading by example. A mention of attaining corporate objectives would also be appropriate if you're interviewing at a larger company. So, those are all the questions. Make sure you have answers or general ideas prepared for these sort of questions. Good job! And in the next lecture, we're going to focus on questions designed for students, or people just getting out of school that don't have a lot of experience yet. Thanks everyone. Again, go through this lecture right before your interview so you can prep for the tough non-technical interview questions. Thanks, I'll see you at the next lecture. Hello everyone, and welcome on the lecture for questions for students. So for this lecture, after you hear the question, pause the video and attempt an answer. Afterwards, we're going to go over some general advice for the question. So first question is, why did you choose this profession / your major? So pause the video now and answer the question. Okay, so be honest about how you chose your major or profession, unless you fell into it. In that case, you should be honest anyways, but show that you have an abundance of enthusiasm about being part of the field and you're highly motivated to succeed in it. Alright, next question. What subjects did you enjoy the most and which did you enjoy the least? Pause the video now and answer the question. Alright, this is a question that may define your strengths and weaknesses, so use caution when you respond. Be sure to align your subjects that you liked with the position and what it requires. For the ones you like the least, choose the ones that have no bearing on your future with the company. So for instance, if you're interviewing for a software development position, it doesn't look so bad if you disliked art history the most. Just keep in mind if your interviewer has expressed any interest in specific courses or subjects, keep those in mind when you're answering the questions, and don't talk down any particular subject, just say it wasn't for you. Next question is, what's your greatest achievement in school? Pause the video now and answer the question. Alright, this is an opportunity for you to show off with confidence, so emphasize the things you want to highlight overall. Just go for it and don't hold back. And that's it for answering this question. Obviously, it'll be personalized for you and what your greatest achievement you felt was in school. That's it for this section, so good job. Up next, we'll discuss some special case questions. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to this lecture on special case interview questions. So, these questions won't apply to everyone, so only practice the ones you feel apply to you personally. Again, after each question, pause the video and attempt to answer if you feel the question applies to you. After that, we'll give you some general advice on how to approach that particular question. So let's get started. First question is, how do you explain the gaps that appear in your resume? Go ahead and pause the video now. Okay, so if you have long breaks in employment or a number of gaps, you should prepare a brief and credible response. Make sure you're able to convince the interviewer that you won't be moving on to a new job soon after taking this one. The next question is, why has it taken you so long to find work? Go ahead and pause the video now. Alright, so you want to provide a short, concise account of why you've been out of work, and be sure the interviewer knows that you've been working on yourself, your skill set, and your career while you've been out of a job. Next question is, have you ever been fired? Go ahead and pause the video now. If possible, you want to avoid answering this in the affirmative. Try using the terms layoff, downsizing, restructuring, and so on. If there's no clear way around it, the best approach is to be honest and show humility and take responsibility. Another question is, how many positions have you applied for? Go ahead and pause the video now. Alright, so this question usually is just so the interviewer can get a better idea of how motivated you are and how close you are in making a decision. Try to avoid giving an exact number unless you feel you can gain leverage from it. Otherwise, just refrain from specifics. And that's it. Good job. That concludes this section of the course. In the next section of the course, we'll discuss post-interview tactics, such as salary negotiations and answering questions about your salary. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on salary negotiations. In this lecture, we'll get general tips, links for salary information, and you'll have a homework assignment at the end of it. So, here are some general tips about negotiating a salary. First off, don't bring up salary before the company initiates the conversation. You should wait for the company to ask before you bring it up. Then, always provide a range of salary options based off a minimum that you're willing to take. So for instance, if the minimum amount that you'll do a job for is $50,000, your range should be somewhere between 50 and let's say 65. You should also understand what you're worth. And we'll look at the links later on in this lecture to get a better understanding of salaries for given positions you're applying for. That will also help you be prepared to support your numbers with evidence. A couple more tips. Don't forget to include benefits as part of the total compensation package, such as health insurance, free meals, gym, etc. But also, make sure you don't overvalue these. For instance, if your company provides free gym membership, keep in mind how much gym membership costs per month. If it's just an extra $40 a month, that's not a huge addition to your total compensation package. Again, don't be too quick to accept a counteroffer and give yourself room to negotiate. Some resources for finding out relevant salary information are listed here. There's salary.com, payscale.com, and finally, I highly recommend glassdoor.com, especially for the tech field. All of these websites use reported salaries to give you a range for either the specific company and position or just the general geographical area and your working company title. So go ahead and check out those links. Try Glassdoor first and then check out salary.com and payscale.com. Finally, your homework is to view the following video lecture by a Harvard Business School professor on how to negotiate your job offer. It's about an hour long, so keep that in mind, but it's a great resource for learning the ins and outs of negotiation. It's also followed by a question and answer session. The link is also in the resource section of the lecture, so you can either download this PowerPoint presentation and click the link from it, or check out the resource section of this lecture. Alright, that's it, so go ahead and check that video out, and that's it for salary negotiation tips. Thanks everyone, I'll see you at the next lecture, where we're going to discuss specific salary negotiation questions and answers. Thanks. Hello everyone, and welcome to the lecture on salary questions and answers. So in this lecture we're going to go over a few salary related questions and some appropriate answer strategies for them. There's really no need to pause and practice these sort of questions until you're actually getting interviews and offers. So the first question is, what kind of salary are you looking for? So attempt to get the company to make the first offer. Most negotiating professionals believe that whoever brings up salary first loses in the negotiating game. So if possible, try to deflect the question so you don't disclose an exact number first. Another question is, what is your current salary? So bear in mind that what you earn has no direct bearing on what you're worth and what you want to make, though it can be difficult to support this in an interview without seeming defensive or awkward. So, although the interviewer is looking for specifics here, you can be somewhat elusive in general without compromising the quality of your response. Another question is, what would you like to be earning 5 years from now? Here, the interviewer is most likely just trying to gauge your ambitions. So, this is a good time to be honest with your aspirations, but try to assess what the interviewer is looking for with this question. It's a pretty uncommon question. You're more likely just to be asked, where do you see yourself in 5 years? Not what you're going to be exactly earning. Alright, that's it for the specific salary questions. Up next, we're going to cover how to prepare references. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on preparing references. So references are the final stage of the interview process before you actually begin to receive a formal offer. So let's go ahead and go over some general tips. First off, you should identify 3 to 5 people to be potential references. Usually a formal job application requires about 3. And you should always contact your reference at the beginning of your job search. Make sure to get their email and phone number. Then, you should call your references letting them know they should expect to be contacted once you know that the recruiter at the company you've been interviewing with is going to contact your references. So, who to ask for a reference? There's different types of people you can ask. You can ask previous superiors, and you should make sure that they're able to promote your value and ability to perform, produce, and contribute to organizational goals. There's also previous peers, people you worked with. They should be able to endorse your ability to work together as a team member and as a leader. This confirms your ability to put the organizational agenda before your personal agenda. There's also subordinates, people that worked for you, and they should be able to vouch for your training and coaching skills, also promoting your supervision skills. And then there's clients and vendors. They should be able to affirm your high-quality customer service and professional integrity. And finally, make sure to always ask people you know well and will speak well about you. Alright, that's it for preparing references, and that's it for the non-technical portion of this course. Up next, we'll have a little technical break section where we get a quick overview on the format for the rest of the course. Thanks everyone, and I'll see you at the next lecture. This is the technical section overview lecture. Welcome to the technical section of this course. In this lecture, we're just going to be giving you an overview of what to expect for the second half of this course. The next section is called Introduction to Jupyter Notebooks and covers the materials and installation of Python. It'll tell you how to access the notebooks that correspond to all the technical video lectures, as well as giving you an overview of how best to use the Jupyter Notebook system for programming and learning. As far as the actual technical section's topics, they are algorithm analysis in Big O notation, array sequences, stacks, queues, and Deques, linked lists, recursion, trees, searching and sorting algorithms, graph algorithms, and riddles, or brain teaser type questions. Each of those sections usually starts with a presentation on the theory of the topic. Then we do some hands-on implementations of those data structures or algorithms. After that, we'll do some interview practice problems presented to you, and then walk through of the solutions to those interview problems. After all those topics are presented, we'll have mock interview sections. There are several mock interviews with questions designed to simulate an interview at a real tech company. The section outlines are reviewed along the way, so don't worry about having to memorize everything we just covered in this lecture. Information on getting technical help and disclosure on the discussion questions are coming up next for the technical break section. Best of luck on all the interview problems, and let's go ahead and get started with the technical section of this course. Thanks everyone. Hello everyone, and welcome to the course material installation lecture for Windows and Microsoft users. In this lecture, we're just going to be going over how to download Python and the Jupyter Notebook system onto your computer in case you don't already have it. Later on in this same section, we'll get a much deeper introduction to the Jupyter Notebooks, how best to use them, and also where to access the course material and those course notebooks, as well as the interview and mock interview notebooks. With that said, let's go ahead and jump to the browser so we can download the materials. Okay, so for everything we're going to be using in this course, I highly recommend the Chrome browser. It really works best with the Jupyter Notebooks. But let's first begin by installing the Jupyter Notebooks. Go to your favorite browser, I highly recommend Chrome or Mozilla Firefox, and type in Jupyter into the Google search engine. So Jupyter, search for it, and the first link should take you to jupyter.org. You can go ahead and click that link, and this is the Jupyter Notebook website. The Jupyter Notebook is essentially a web application that allows you to create and share documents that contain live code, equations, visualizations, and explanatory text. Their uses include data cleaning and transformation, numerical simulation, statistical modeling, machine learning, and much more. In this course, we use them as the basis for all the interview practice problems, as well as the notes that correspond to each of the video lectures. Once you're on this website, you can scroll down and you have two options here. Try it in your browser and install the notebook. Something that I want to note is that if you click try it in your browser, we'll go ahead and open this in a new tab. It'll take you to try.jupyter.org. This will allow you to go ahead and try the Jupyter notebooks in your browser without installing anything. So you could just come to try.jupyter.org and then click here, write new Python 2 or Python 3, depending on what you want to use, and you can go ahead and begin to immediately code in your browser. And I'll run that cell, and we can see the output. Now we'll explain what cells are, what this toolbar is, and how it all works in next lectures that are coming up. But just so you know, you can go to try.jupyter.org and try this all within your browser without having to download anything. But let's actually focus on downloading. So we want to go to click here on install the notebook. That will take you to the installation documentation for the Jupyter Notebook system. You'll see there's three options: installing Jupyter in Python, installing Jupyter if you already have Python, or upgrading to a Jupyter installation. Here, we'll focus on installing Jupyter and Python. For new users, it's highly recommended that you install Anaconda, which conveniently installs Python, the Jupyter Notebook, and other commonly used packages for scientific computing. I highly recommend you install Anaconda, even if you already have some sort of version of Python on your computer system. So if you click this link, it'll take you to this tab, to continuum.io/downloads. You can go here, jump to Windows, if you're using Windows, and then go ahead and click the graphical installer. Once you download the installer, you just double-click the executable file, that's the .exe file, to install Anaconda and just follow the instructions on the screen. So that's what I recommend for any user who doesn't have Anaconda yet. If you already have Python and don't want to install the entire Anaconda distribution, you can just install Jupyter depending on what installation packaging manager you have. If you already have Anaconda, you would just use conda install Jupyter as a command line either in your command prompt or terminal or PowerShell. So I'll show you an example of that. If I go ahead and type in PowerShell into my search and click PowerShell, I'll get this command prompt terminal available to me. And then I can just type conda install Jupyter, enter, and if you already have the Anaconda distribution, this will install the Jupyter Notebook system. If you're using a different package manager, such as pip or pip3, you can just say pip install Jupyter or pip3 install Jupyter. And you'll see here it'll start fetching the package metadata, solving the package specifications, and eventually download everything for you. I'll let that continue. You should note that some of Jupyter's dependencies may require compilation. In this case, we won't have to worry about that. We're just going to be using basic Python. You can also upgrade a Jupyter installation. If you already have pip, just use this, pip install -u Jupyter. If you're using Anaconda, just use conda space update space Jupyter. That's really all there is to it. So again, just an overview. Go to try.jupyter.org if you want to just use everything in browser. Otherwise, Google search Jupyter and then click on the link that will take you to the installation page and follow the directions that best suit you. I highly recommend installing Anaconda, which will take you to this page. Click on the graphical installer, follow the instructions, and continue from there. Once you've installed everything, you can just go to your PowerShell or command prompt for Windows. Either one is fine. And then type in Jupyter Notebook, and you should get your own instance running. Okay, so that's it. Go ahead and check out the other documentation here as far as running the notebook, migrating from IPython, etc. But once you've installed everything, all you have to do is go to your command prompt or terminal, type Jupyter Notebook, and you should see your own local instance of the Jupyter Notebook running. We'll go over in a lot more detail the Jupyter notebooks and the course notebooks in the future lectures. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Mac OS installation video. At the beginning of this section called Introduction to Jupyter Notebooks, there's also a written out course material installation guide. In this lecture, we're just going to go over those instructions on a Mac system. You can go ahead and follow these instructions if you have a Linux-based system because they're going to be extremely similar. Alright, let's go ahead and get started. First thing we want to do is go ahead and jump to an internet browser. I highly recommend Chrome or Mozilla Firefox. The Jupyter Notebooks always work best with Google's Chrome browser. Okay, now we're here at the Google Chrome browser. First thing we're going to search for is Jupyter. That's Jupyter. That will take you to jupyter.org. You can go ahead and click that link, and you should see a page that looks something like this. If you scroll down, you'll then see a link that says try it in your browser and install the notebook. If you click try it in your browser, here I'm opening it in a new tab, you'll see a page begin to load and it'll look something like this. This is basically the Jupyter Notebook system in your browser. So if you're running this on a Chromebook, for example, or anything where you only have access to the browser, you can actually use this website, try.jupyter.org, to run Jupyter Notebooks completely in browser. You just click here on New, then click Python 2, wait for it to load, and then you can actually type Python code here and print something like hello world, and then run the cell. We'll go into much deeper detail about how to use the Jupyter Notebooks and how to get the course notebooks in general, but I just wanted you to be aware of this website, try.jupyter.org, in case you were interested in it. If we want to install the notebook system locally, click Install the Notebook link, and it should take you to the official documentation, and we can go ahead and zoom in here. And this section just explains how to install the Jupyter Notebook system. You'll see there's three options: installing Jupyter in Python, installing Jupyter if you already have Python, and upgrading a Jupyter installation. It should be noted that Mac and Linux systems almost always come with Python already installed. However, I still recommend going with the Install Jupyter in Python, because when you click it, it'll tell you about Anaconda. Anaconda conveniently installs Python, the Jupyter Notebook, and other commonly used packages for scientific computing and a field known as data science. If you go ahead and click here on the link installing Anaconda, it'll take you to continuum.io/downloads. And then you can just jump to OS X or Linux and follow the relevant instructions. In this case, just go ahead and click here on the graphical installer and follow the directions once you're done executing the graphical installer. There's also a command line installer for an option. If you're using Anaconda for Linux, you also have the same options here for 64-bit and 32-bit, but for those, you'll have to execute them on the command line by following the instructions here. Again, if you're using Mac, I just recommend to use the graphical installer. There is a command line installer option, but the graphical installer is usually just easier to use in general. Okay, so once you've done that and followed the directions, if you go back to the documentation, you should just be able to go to your terminal for a Mac or Linux or command prompt for Windows. To find your terminal, just click the command key and space to open up Spotlight Search, and then begin to type terminal, and you'll get something that looks like this. Here I have my bash terminal. Once you've done that, you can say conda, and we'll zoom in here, conda install Jupyter. Go ahead and click enter, and once you've run that, I won't run it right now since I already have conda installed and Jupyter installed, it'll automatically install the Jupyter Notebooks. After that, once that's all installed, you should just be able to write Jupyter space notebook, hit enter, and you should see a new notebook system pop up. You can come to the right, click on Python 2, and now you're running Jupyter Notebooks locally, wherever you were in your terminal. Alright, that's the basics of the material course instruction installation. You can go ahead and check lecture 28 for more details on the Introduction to Jupyter Notebooks, and how to understand every single step of the way for installation. In the next lectures, we'll actually go over the notebooks in much more detail, how to get the course material, and how to create the interview notebooks. This was just instructions on the basic installation. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Jupyter Notebooks Overview lecture. A quick note, check the previous lectures for installation instructions if you haven't installed Jupyter Notebooks already on your system. In this lecture, we're going to just be looking at an overview of the Jupyter Notebooks capabilities and the best way to use them. So let's go ahead and jump to the Jupyter Notebooks. Alright, so I started Jupyter Notebooks by following the installation instructions where you just type Jupyter Notebook either into your terminal or into PowerShell or your command prompt, depending what system you're using. You should get something like this in your browser. I suggest using Chrome or Firefox. Go ahead and click on the right. You should see an option for creating notebooks, either Python 2 or Python 3, depending on your installation. And then you'll see something like this. So let's go ahead and go over what these buttons are and what this system's like. So first off, we have our toolbar here. This is a save button, which saves and creates a checkpoint for your notebook. This plus button will insert a new cell, and we'll discuss what cells are in a second. So if we click it, we have a new cell. You can cut, copy, and paste cells using these three buttons. This allows you to move up a selected cell and then move down a selected cell. This is run, stop, and restart kernels, which is basically just the same as running a cell. And then you have another toolbar here for file options, edit options, viewing options, inserting options for cells, then running options, kernel options if you're ever having trouble with a kernel being stuck in a loop, and then you also have help. So there's keyboard shortcuts here in case you want to know more about the shortcuts, and there's also help for the various libraries used in scientific Python. Alright, so let's go ahead and see how this works. So for Python, we can go ahead and just write code straight into this cell. So for instance, 1 plus 1. And to run this cell, I could either click run here, and I will see a new output right below the cell. Or I can also type in the code, and by clicking shift and then enter, that will run the cell. So it's not just enter, it's shift and then enter. Alright, so that's one key feature of the Jupyter Notebooks. Another one is hints and docstring completion. So what I mean by that is if I start to write a function in Python, so for instance, str, which converts things to strings, I can click shift plus tab, and it will bring up the document string. So it will return a nice string representation of the object. I can also call help on any function, and I will get the entire docstring for that function. So you have a couple options here. Again, whatever function you have, and I just cleared that by running an empty cell. Whatever function you have, so for instance, let's do another function. Let's go ahead and import from the math library. So I'm going to say from math, import sqrt, shift, enter. And now, if I'm using sqrt and I'm not sure what to do with it, I can do shift tab with my cursor right after that function, and it'll give me the document string. It'll give me the short version, and if I want more, I can click plus here, and it will grow this to give you more information if there's more information available there. So for instance, if we wanted more information on list, shift tab, gets me the doc string. If I want more information, click this down. It'll give you more information if there's more information available. Alright, so what else can we do? We can also see methods and attributes of an object. So for instance, if I say s equals string, let's say it's hello, shift enter. Now s is going to be that string. So one thing to note is that these cells are not independent of each other. If I set a variable in one cell, that variable can be run in any other cell. So if I click s here, it's saved as hello. So just keep that in mind. Again, you can always check the order you ran cells in by checking the numbers here. So 1, 2, 5, 6, 7. 4, we ran over it so that we did 3. But what's nice about Jupyter Notebook and IPython in general is that if you click S dot, so let's say we wanted to do a certain method, such as uppercase all this letters or elements in that string, I could call upper on it, and then we get that as an output. So what if you don't remember what these various attributes and methods are for a string or any object? You can do s dot, or whatever object you have, the dot will be calling the method or attribute on it, and then if you click tab, you'll get a little drop-down list of all the methods and attributes you can call on that object. This is super useful to know. So again, whenever you have an object and you want to call a method or attribute on it, but you're not sure which ones are available, you can have the object, click dot, and then tab, and it'll open up a drop-down list for you. And then if you click one of these, so let's say I want to do capitalized, if I'm not sure what it does, I can just click Shift Tab, and it'll return the doc string for that method. Okay, so those are the main things to know about the Jupyter Notebooks. One last good thing to know is that there's actually different types of cells. So I'll go back to the first cell and delete the code from it, and you can change the cell type. So Jupyter Notebooks don't actually support just code. They can also support Markdown and other cell types. So if you go here to this toolbar or drop-down menu, you'll find that right now we have a code cell. I can click this and change it to a Markdown cell. You'll notice that inbox goes away, and now I can actually write Markdown, which is just basic text. So I can say hello, and when I run this cell, either by clicking here or by saying Shift Enter, you'll notice I just have Markdown text. So that's not in Python or any coding, it's just Markdown text in the Markdown cell. I can double click to edit that text. So this supports various Markdown syntax. So in case you're familiar with Markdown syntax, you can go ahead and take advantage of this. You'll see a lot of this Markdown in the Jupyter Notebooks we have corresponding to every video lecture, so just keep that in mind. These are really useful for writing yourself notes or explanations. So for instance, you just ran 1 plus 1, I hit Shift Enter, the next cell, I'm going to delete that and turn it into a Markdown cell, and then leave myself a little note. I just added 2 numbers. Shift Enter to run it, and here I've left myself a little note about what that cell does, which sometimes might be nicer than writing a comment here. So that's totally up to you. There is a shortcut for making cells into Markdown cells. That shortcut is clicking Control M and then M again. But notice how I'm selecting the cell, it's not going to work. So I have to click outside of the cell. See, notice the highlighting. If I click outside of the cell, do Control M once, and then click M again, it will turn it to a Markdown cell. And now you'll notice here, I've converted this into Markdown text, and all Markdown conventions apply here. You can go ahead and read more about Markdown cells and Markdown conventions if you want to know the various syntax that I can write here to edit the text itself. One last thing to note on Markdown is it also supports LaTeX, in case you're familiar with LaTeX. LaTeX is just the ability to write mathematical equations. So for instance, I can say sqrt, let's say of x here, see if that works. And here, let's go ahead and remove the parentheses since they're not actually needed. And I can write mathematical equations in the Jupyter Notebooks. So that's also really useful for scientific computing and various aspects of mathematics and coding. Another good thing to note, if you accidentally put, for instance, a while loop and it's running forever and you want to cancel or stop the notebook from running, you can go here to kernel and you can interrupt, restart, or reconnect your kernel, and that will allow you to basically reset the Jupyter Notebook. That's all you need to know really for this course. One quick note, in the resource section of this lecture, there's a link to this manual here. And this manual is basically the complete Jupyter Notebook user's manual. It has a lot of information, and you can check it all out here. Goes over what we just went, getting to know Jupyter Notebook's toolbar. It goes way beyond the basics. Talks about Markdown cells, raw cells, and header cells, various cells that we don't use too often in this course. But you can go ahead and check it out here. One quick note, in case you see people calling this an IPython notebook, Jupyter Notebooks used to be called IPython Notebooks until recently, where they changed the name to reflect that it supports other languages than just Python. So just keep that in mind, that IPython Notebooks and Jupyter Notebooks are essentially the same thing, with Jupyter Notebooks being the new name for IPython Notebooks. Alright, so you can go ahead and click the link in the resource section to get a full background on all the capabilities of Jupyter Notebooks, as well as instructions on how to write various headers and markdown text, etc. Okay, thanks everyone for watching this lecture. That's it for now. In the next lecture, what we're going to do is actually go over how we create the interview question notebooks. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Course Notebooks lecture. A quick note, you should go to the resource section of this lecture for the link to the course notebook. There will be two links, one to the nbviewer.ipython.org link to the notebooks, and then also one to the direct GitHub repository link. I suggest you always check out the nbviewer.ipython.org first, because it looks a lot cleaner and loads faster. But in case that one goes down, when it does go down, it's because there's too many people using it. It doesn't happen often, but it has happened in the past. Then you can go ahead and go straight to GitHub, which is almost never down. With that being said, go ahead and click the nbviewer link, and it'll take you to the resource section for the course notebooks. I'm going to go ahead and jump to that now. Alright everyone, we're here at the nbviewer.ipython.org link for the courses repository for all the notebooks. The other link will take you to the GitHub, which is in this tab here. As you notice, there's a lot more going on here, and it's not as pretty, so I always suggest checking out nbviewer.ipython.org first. Also, the notebooks tend to load much faster on this website versus on GitHub. But notebooks can be rendered on both nbviewer and GitHub. So let's go ahead and go over what an example would look like for a particular lecture in the course. Let's say you're in the linked list section of the course. You would just go ahead and click the folder that is named after that section, and you'll see IPython notebooks or Jupyter notebooks that are IPYNB files. These are notebooks that are associated with a lecture of the same name. So if you have a lecture such as linked list overview, which is basically the first lecture in that section of the course, which does a very quick overview of what we're doing, you should get this brief notebook, and if you click on it, you'll get this notebook, which is just a brief overview of the topics we cover in this course. For more technical lectures, if you go back here, maybe we do a double linked list implementation. You can go ahead and click that. I'll open it in a new tab. And you'll see here where we have comments and all the example code that we go over in the video. So if you're feeling more advanced of a programmer, or you already know a topic pretty well, then you can just go ahead and check out the notebook, run through it. If you have any questions, then you can go ahead and check out the video, where I explain every line of the code and code it out with you. Alright, let's go ahead and jump back. Here we are. A quick note, some notebooks that are associated with a lecture, where the lecture doesn't have a lot to do with code but more on theory. If you click that, for instance, the doubly linked list lecture, you'll notice it'll say refer to the video lecture for the full explanation. So the reason for that is we don't really do a lot of coding in that lecture, and it's really a bunch of figures that are hard to put in a Jupyter Notebook format. So if you ever see this, you should definitely refer to the video lecture for the full information on that topic. Let's go ahead and close these. So again, here is the GitHub repository. If this link is ever down, this nbviewer link, which you should favorite, by the way, then you can just go ahead and go to the GitHub link, and this should almost never be down, and you'll get the same thing. So if we go to linked lists here, then we click, for instance, on double linked list implementation, you'll notice it takes a little longer to load, but it'll still render, and you can get it here. One thing to note, in case you're interested in downloading the notebooks, you can always just go to a notebook, for instance, double linked lists here, or double linked list implementation, and click the download button here. So you also have a link to the direct GitHub, but if you click this rightmost link, let me go ahead and zoom in on it. So you get this drop down, you'll get a download notebook if you're really zoomed in. It looks like this. Let's go ahead and zoom back out. It's right here, top corner. Just left click, and you should be downloading a .ipynb file. Put that wherever you're storing the rest of your notebooks, and then you should be able to see it when you start the Jupyter Notebook server. If you want to check out that particular Jupyter Notebook in GitHub, you can click the GitHub link here. I'll go ahead and open it in a new tab, and it will take you to this right here, which is that same notebook just rendered on GitHub. One quick note, you should really be using Chrome or Mozilla Firefox. I highly suggest Chrome. This rendering of notebooks and just Jupyter Notebooks by themselves don't tend to work well in Internet Explorer or other browsers, so just keep that in mind. One last note is if you're interested in downloading all the notebooks for the entire repo, you can go ahead and click back to the original link, click here on GitHub, or view on GitHub. It's this little octocat, and you click it, it'll take you to this page right here, and you can click download zip, and that will allow you to download a zip of all the folders and files. Keep in mind, we may be adding new stuff in the future, so you may have to re-download. I suggest you just download as you need them, or copy and paste from the notebooks themselves. Let's go ahead and go back for one quick note. You'll notice that there's interview problems for almost every section of the course, at least all the technical sections. If you click here, there's a subfolder for each section labeled that section's name and then interview problems. So right now we're in the linked lists section of the course. We have the lectures that go over the theory and the notebooks that correspond to those. And then we have the interview problems. So if I click on this folder, it'll take us to two folders. One will be the problems themselves, and another will be the solutions. You can go ahead and click the interview problems, and then click on, let's say the first one, implement a doubly linked list, and you'll get a for this interview problem, basically the problem statement, implement a node class, and show blah blah blah, how to create a doubly linked list. In pretty much all of the interview problem notebooks, if it makes sense, you can test your solution. In this case, it didn't make sense because it would basically give away the answer structure, but let's go ahead and check one that actually has a test cell for your solution. So we're going to go back here, and we're going to go to the array section of the course. So here we're at array sequences, we're at Python for data algorithms, data structures, and interviews. I click array sequences. Again, I have notebooks that correspond to all the theory lectures. And if I click here on array sequences interview questions, I'll get two similar folders, the solutions and the questions themselves. Let's go ahead and click the questions. And here's the first one, anagram check. So you're given a problem statement, and you'll be asked to fill out your solution below. Just keep in mind, you may get special notes or requirements on certain problems. You fill out your solution below. There may be examples of what it should look like. So for instance, for this anagram, dog and God should say true since those are anagrams. Clint Eastwood and Old West Action, these strings are also anagrams, so they should be true. You'll learn more about this later on in the array sequence. But what I want to get to here is there will be a test your solution section. So once you've actually filled out your solution here in this function, you can run this cell to test your solution. It'll give you all test cases pass, and that way you can test to see if your solution's working without having to jump to the entire solution and essentially cheating yourself of figuring it out on your own. Alright, so if we go back and check out what the solution looks like, let's go back one more. We can click on the solutions folder, click anagram check solution. So solution is pretty much always in all caps, just to make sure you don't accidentally click on solution ever. Here we have the anagram solution. You'll have the same problem statement, but you'll notice there's some explanation as to what we do in the solution, and then there's also code for it. I'll go ahead and hide that real quickly since you will have to do this interview problem later on. We'll go ahead and go back. So a quick note, we always go over the entire solution in the video lecture. So in case you don't understand the notebook explanation, I will explain it line by line in the video solution lecture. So just keep that in mind. Alright, so one quick note, going back to this interview notebook and the interview problem notebook, I really want to make sure you guys all understand how to run and test your solutions. So in the next lecture, what we're actually going to be doing is creating our own example interview notebook. Alright. So I'll see you at the next lecture. We're going to create an example interview notebook. This next lecture is optional, but I do recommend you check it out so you fully understand how to use these interview notebooks. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the example interview notebook lecture. In the last lecture we went over Jupyter notebooks in general, and in this lecture we're actually going to make our own example interview notebook so we can better understand how the interview notebooks work. So let's go ahead and jump to the notebooks so we can get started. Okay, so we're here at our example interview notebook. So all the interview notebooks are going to look something like this. Let me go ahead and make this into a markdown cell. Let's just Control M and then M again. And you'll have the name of the problem as the header. So I'm just going to say add two numbers. Then we'll have a problem statement. And it'll just be add two numbers together. Shift Enter. And then what we're going to do is go ahead and create the function. So I'm going to say solution as the name of the function, takes in num1 and num2, and then it just returns num1 plus num2. So this is a really super basic example of what you would see. So this is the solution coded out. If we were just making the actual problem notebook, I would just have pass here instead with no return function. So you can imagine that you've already filled that out. The part that I really want to get to here is the testing your solution section. So I'll show you how we actually build out the solution tests. So in every interview notebook, or at least most of them, if it's applicable, you have a test cell. And what we do is say from nose.tools, and you may have to download nose. Nose is basically just a testing library. And we're going to import assert equal. Now let's go ahead and zoom in so we can get a little bit of a better view here. So I'm saying from nose tools, import assert equal, and then I'm going to create a class, and it's going to be called solution test. Just create an object, and then the class solution test is going to have a method called test. Takes in itself since it's a class, and it also takes in SOL, which stands for solution. And then what we do here is we use this assert equal function that we imported from the nose.tools library. And the assert equal function basically takes in two arguments and then will return an error if they're not equal to each other. So the first thing we're going to do is take in the solution that we pass and then put in two numbers. So in this case, we'll put in 2 and 2. And we'll go ahead and make sure that this is equal to 2 plus 2, which is 4. So the first argument is the function that we pass, and I'll show you how to pass it in just a second. With these two arguments, 2 and 2, we want to assert that that's equal to 4. So I'll give you one more example. We'll do assert equal, and let's go ahead and pass in our solution, SOL, and we'll do 4 and 4, and that should be asserted equal to the integer 8. After all those assert statements, if none of them have an error that pops up, I'm going to go ahead and print all test cases passed. Note that I'm using a print statement here, not a print function, because this is in Python 2. Okay, so then what I'm going to do is just run the tests. So I'm going to go ahead and make a comment here, run tests. I'm going to create a variable t, and it's going to be an instance of solution test object. And then I'm going to say t.test, and we note that that method takes in a function called SOL. So we'll pass in the solution, and let's go ahead and make sure it works. So I'm going to shift enter to run this cell. Note that all test cases have been passed. Let's say I accidentally got the wrong solution function here. I said num1 minus num2. What would happen if I wasn't able to pass all the assert equal tests? If I do shift enter here, I'll get an assertion error. And we scroll all the way down, you'll see that 0 does not equal 4, which makes sense because it said 2 minus 2 equals 0, and the assert equal function got an assertion error due to that 0 not being equal to that 4. Alright, so that's the basic structure for all the interview notebooks. I encourage you to go ahead and create your own interview problems. You can go ahead and send them to your friends. But this notebook system is really nice because you have this cell to go ahead and test your solutions, but these cells usually won't give away how to actually do the problem. In certain cases, such as implementing a data structure or a sorting algorithm, the assert equal solutions don't really make sense, or having a test cell in general would just give you the solution to the problem due to the way it's asked. So there will be a note in the interview notebooks, each individually, telling you if that's the case, but there will always be a link to a full solution for every interview problem, as well as a video explanation for that particular solution. Alright, with that being said, what you should have now is a full understanding of how the interview notebooks themselves work, and you should also be able to make your own interview notebooks in case you ever want to. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Algorithm Analysis and a Big O Notation section of this course. This is just a brief overview video describing what this section will be like. So as I mentioned, in this section we discuss Big O notation, and we discuss it from a level of why we're doing algorithm analysis to begin with, and how we can actually construct the paradigm of thinking for Big O notation. So if you're already familiar with Big O notation, maybe you've already taken an algorithms and data structures class and you've covered it and understand this already, feel free to just look over the Jupyter notebooks. Take the quiz at the end of the section and quiz yourself. If you've passed all of them, then you're probably good to go. If not, feel free to watch the lectures and follow along throughout this section. This section approaches the topic as if you've never heard of Big O notation before, so just keep that in mind. As always, links to the notebooks are provided in the additional resource section of this lecture, so go ahead and check them out. There's a link to the NB viewer as well as the GitHub notebooks. Okay, with that all being said, let's go ahead and begin. Hello everyone, and welcome to the lecture on an introduction to algorithm analysis and Big O. In this lecture, we're going to start off with a couple of slides explaining what this lecture and what this section is about, and then we'll jump into some live code. Let's go ahead and get started. So, first off, we need to ask ourselves, why analyze algorithms? Before we do that, we need to clarify what an algorithm is. So in this course and in general, an algorithm is simply a procedure or formula for solving a problem. So I don't want you to be intimidated by this word of algorithm, especially in an interview setting when someone asks you to come up with an algorithm. It's just a procedure or formula for solving the problem at hand. Now, some problems are famous enough that the algorithms have names, as well as some procedures being common enough, such as certain types of sorting, where the algorithm associated with it has a name, such as merge sort or bubble sort, etc. And we'll be covering those later on in this course. But now that we know what an algorithm is, we have a good question we need to answer. How do we analyze algorithms, and how can we compare algorithms against each other? So, what I want you to do is imagine if you and a friend both came up with two separate functions to sum the numbers from 0 to n. How would you compare the functions and algorithms within the functions? How would you know which one was better? How would you even define what better is? So let's jump to some live code examples to explore this further. Okay, we're here at the Jupyter Notebook, and notice I have the corresponding Jupyter Notebook available here for you in the Jupyter NB viewer, and this is the example we're going to go through. But let's go ahead and jump into a live notebook so we can code. And I'll just zoom in real quickly so you can have a better view. Okay, so let's start off. Let's say your function looked something like this. We'll call it sum1. It takes in an argument n, and we're going to take an input of n and return the sum of the numbers from 0 to n. And you decide to make an algorithm that looks like this. You set a variable called final sum and set it equal as 0 to start. Then you say for x in, and let's say range n plus 1, you say final sum plus or equal to x. And then we return the final sum. Note we can also use xrange for Python 2 to make that into a generator. But that's not really the point here, so feel free to use either. So you have this. Let's go ahead and test it out. Sum 1 of 10, you get 55 out. So that's 0 plus 1 plus 2 plus 3 plus 4, etc., all the way to 10. So that's your algorithm and your function. Let's say your friend came up with this. We'll call it sum2, the function. And it does the same thing. It takes an input of n and returns the sum of the numbers from 0 to n. But your friend figured this out. N times n plus 1 divided by 2. Let's check if this works. We call the function on 10. And notice we get the exact same thing out. So both functions have the same result, but completely different algorithms. You'll note that the first function just iteratively adds the numbers. So iteratively, you're just adding these numbers to your final sum, while the second function makes use of this algorithm. And I'm going to jump back to the Jupyter Notebook because I have it written out here. So the sum of I from I equals 0 to n is equal to n times n plus 1 divided by 2. So what we want to do is objectively compare the algorithms. So we could compare the amount of space they take in memory, and we can also compare how much time it takes each function to run. So before we start talking about big O notation, let's just get a general idea of what we're actually talking about here. Let's go ahead and compare how much time it takes these guys to run, these two separate functions. And what we're going to do is use some built-in magic commands in the Jupyter Notebook. So I'm going to use the timeIt magic command. And we'll say the first function, sum 100. So it looks like it takes about 3.62 microseconds per loop. Now let's check out the other algorithm. Through timeIt, sum 2, 100. Right now it's performing the loops. And let's see. So don't worry about this right now. This just means that a result might be being cached, but what you really want to focus on is that it's taking on an order of nanoseconds per loop. So you can see that the second function is actually much more efficient. So running at a much faster rate than the first means that this second function, or this second algorithm that the function used, sum2, is a lot more efficient. But the problem is here, we can't just use time to run as an objective measurement, because that will depend on the speed of the computer itself and hardware capabilities. So we want to use an objective method to compare how much time it takes these guys to run, both of these functions, but we want it to be hardware independent, so we can't use time. And that's where big O notation is going to come in. So we're going to be able to use this idea of big O notation to compare algorithms objectively, both in how much time they take to run and how much space they take up in memory. All right, so what we discussed in this lecture, just to go over it again, I'm going to hop over to Jupyter Notebook, is just a general idea of why analyze algorithms, how to analyze algorithms, and start getting a notion of you're going to have to do this objectively and hardware independent. So you can't use just time to run. We'll have to use big O notation. All right, that's it for this quick introduction. In the next lecture, we'll dive in more into what big O notation actually is. All right, thank you, and I'll see you there. Hello everyone, and welcome to the Big O Notation lecture in this section of the course. In this lecture, what we're going to be doing is just going over the corresponding Jupyter Notebook that accompanies this lecture. We won't be doing that much or really any live coding. We'll just be discussing the functions that we previously looked at. Okay, with that being said, let's go ahead and jump to the Jupyter Notebook. All right, this is the Big O Notation Notebook, and I recommend that you actually read through this notebook, and then if anything doesn't make sense to you, come back to this video lecture, where we're going to be going over it. All right, so we previously discussed these two functions. And now remember, these functions take in an n, and then they return the sum of the numbers from 0 to n. The first one did it iteratively, and then the second one took this algorithm, this n times n plus 1 divided by 2. So what we want to do is develop some sort of notation to objectively compare the efficiency of these two algorithms. And a good place to start would be to compare the number of assignments or operations each algorithm makes. So let's start with just assignments in general. So if we look here, the original sum1 function will create an assignment n plus 1 times. And we can see this from that xrange or range-based functions. Just a quick note, since this is in Python 2, we're using xrange, which is just a generator, but range in Python 3 is the same. So don't worry about that detail, we're really just discussing big O notation here. So continuing on, this original function will create that assignment n plus 1 times. So this means it will assign that final underscore sum variable, this one right here, it's going to assign it n plus 1 times. So here is the 0, and then it assigns it n plus 1 times. So we can say that for a problem of n size, here it's input, this function will take that 1 plus n steps, or that n plus 1 steps. And this n notation right here allows us to compare solutions and algorithms relative to the size of the problem. So since sum1, this first function of 10, will be different than sum1 of, let's say, 1,000,000, if n equals 10 or n equals 1,000,000, they could take very different run times. But if we get some sort of big O notation that's relative or in terms of the input, we can objectively measure it across any sort of input as long as the big O notation is relative to the input. So that's where this n is going to come into play. And we'll see that when we actually formalize the notation. Okay, so let's go ahead and scroll down here and zoom in a bit so we can discuss the formality of big N, or big O notation, excuse me. So big O notation, formally we can say it describes how quickly runtime will grow relative to the input as the input gets arbitrarily large. So there's 3 points there, and let's go ahead and examine them more closely. So first point, this first bullet, we want to compare how quickly runtime will grow, not compare exact runtimes, since those can vary depending on the hardware. So as we mentioned before, we want to compare objectively these two algorithms, not based on runtime. And what I mean by not based on runtime is not based on exact runtime. We just want to compare how quickly runtime will grow. So I don't want to compare, let's say, 10 seconds versus 12 seconds. I want to compare something objectively, and that can be how quickly runtime will grow. Second point we want to make is since we want to compare the variety of input sizes, we're only concerned with runtime growth relative to input. And that's going to be where this n notation comes into play. And then the third point is as n gets arbitrarily large, we only worry about terms that will grow the fastest as n gets large. And to this point, we can think of big O analysis as sometimes also known as asymptotic analysis. Okay, so let's go ahead and scroll down to the table where we can see how this syntax works. So the syntax for that first function can be said to be big O of n, since its runtime grows linearly with the input size. In this next lecture, we'll go over more specific examples of these big O types and types, but just to note, this is what the format of the big O notation is going to look like. It's going to have a big O and then the big O notation or performance inside the parentheses. So here are some common runtimes of big O functions. So the common ones are constant, logarithmic, linear, log linear, quadratic, cubic, and exponential. So what I'm going to do now is use a library called matplotlib to plot out the differences between these big O's. So you can go ahead and check out that code yourself, but don't worry about it. We're just discussing big O notation here, not matplotlib. But I use that code to create this plot here. So here we can compare the growth
on relative runtime versus the size of the input. So you can see here in constant time, you'd have a straight line, and then you'd also have logarithmic, log linear, quadratic, and cubic and exponential. So let's go ahead and zoom out a bit so we can see them all. Here we go. So you can see that there's a big impact if you don't have a good big O for your algorithm. So there's a huge difference that a big O efficiency can make for the same n value against some sort of projected runtime. And clearly we want to choose algorithms that stay away from any exponential, quadratic, or cubic behavior, these guys, since they grow so fast. You can note that for small input sizes, so very low values of n, they're all very similar and to each other. So if you only expect to deal with low n, for certain cases, the big O doesn't actually matter to you. But as you can see, as n grows larger, you'll get huge differences depending on the efficiency of your algorithm. So in the next lecture, what we're going to do is learn how to properly denote this big O, and then we'll look at examples of various problems and calculate the big O of them. So what did we see in this lecture? We just saw a quick, kind of almost a preview of the various big O types, why it's so important to choose or try to create an algorithm that has an efficient big O relative to its performance and runtime. Okay, so in the next lecture, we're going to see a bunch of examples and break down their big O. All right, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the Big O Examples lecture. So what we're going to be doing here is showing you various examples of big O notation and what those algorithms and functions will look like. So at the end of this, there's a reading assignment. So here I have open the Jupyter Notebook, and if I scroll down here, you'll see there's a homework assignment. So make sure that after we go over this video, and once you've gone through this Jupyter Notebook, you check out these two sources, which are additional explanations of big O notation and various big O examples. They're great explanations, so go ahead and check them out. Okay, so let's go ahead and start off with our own examples. So what we're going to do is start with some simple examples of various big O functions. So the first one we're going to explore is the constant, so O1. So I'm going to make a function here, and I'm going to call it func_constant, and it's going to take in a list of values. And what it's going to do, it's going to print the first item in a list of values. So it takes in a list called values, and it says print values, takes that first index, and let's go ahead and run this. So if I say func constant, remember I'm just doing tab for autocomplete, I can then go ahead and pass in a list. Let's go ahead and just say LST and assign LST to be the list 1, 2, 3. Okay, so I've run that cell, and let's see what happens here. I get a result of, let's zoom in, of 1 here. And if you notice, I'll always get that result no matter how large that list is. So this function is constant because regardless of the list size, the function is only ever going to take one constant step size, in this case 1. So it's just printing the first value from a list. So we can see here that an input list of 100 values will still just print one item. Even if it has 10,000 values, it's still going to print one item. So a list of n values will still just print one item, which is why this is of constant big O. So let's move on to linear. So we'll make a function here called func_lin. It'll take in a list object. We'll just call it LST in this case. And this will take in a list and print out all the values. So it's going to say for val in LST, print val. And if we go ahead and call that on that list we just made, note how we get every single value printed. So this function runs in ON, or linear time. So this means that the number of operations that are going to take place here, the number of print statements, is going to scale linearly with n. So if we have an input list of 100 values, it's going to print 100 times. If we have a list of 10,000 values, it's going to print 10,000 times. And a list of n values will print n times. So that's why this is a linear example. All right, finally, let's go ahead and check out a quadratic example. So let's say func_quad, and we'll have it take in LST, and it's going to print pairs for every item in a list. And what I mean by that, it's going to say for item 1 in that list, and then for item 2 in that list, go ahead and print item_1, item_2. Okay, so let's go ahead and see what this looks like. I'm going to reassign the list to just be 1, 2, 3, and then I'm going to call that function on that list. And let's see what we get here. All right, so what happened? So note how we have two loops, one nested inside the other. This means that for a list of n items, we will have to perform n operations for every item in that list. So that means in total, we will perform n times n actions here. We're going to print this n times n times. So that's going to be n times n, or n to the power of 2, n squared, which is quadratic. So a list of 10 items is going to have 10 to the power of 2, or 100 operations there. So you can see how dangerous this can be for very large inputs, and that's why big O is so important to be aware of, and is such a crucial part of the interview process. So now we're going to move on to a section of calculating the scale of big O. So we want to discuss now how insignificant terms will drop out of big O notation. When it comes to big O notation, we only care about the most significant terms. So remember, as the input grows larger, only the fastest growing terms will matter. And if you've taken a calculus class before, this is going to remind you of taking limits towards infinity. So let's go ahead and see a quick example of how to drop constants. I'm going to make a function called print_once. Takes in a list, LST, and it prints all the items just once. So it's going to say for val in LST, print val. And now if I call print once on that list, I just get 1, 2, 3. So what is the big O of this function? Go ahead and take a moment to think about it. All right, hopefully you saw that it's just on, it's linear. You're going to do an action n times for the size of the list. Now I'm going to show you a different example. I'm going to call this function print_2. And I'm going to say for val in LST, print val. And then I'm going to do it again. I'm going to say for val in LST, print val. So now let's call this function print_2. You notice I get an output 1, 2, 3, 1, 2, 3. So now the question here is, what is the big O, or performance, of this print_2 function? Notice we are printing it twice, but what's actually happening here? It's not going to be n squared because it's still linear. It's going to be n plus n, so 2 times n. And this is where we get to terms with insignificant or significant constants. So we can see here that the first function we made will print on the order of on, and the second one will print on the order of 2 times n. So it's going to do it twice. However, if n is going to infinity, the constant can be dropped, and that's an important thing to remember. You're going to be dropping most constants and only focusing on the terms that grow the fastest and have the largest effect. So in this case, both of these are order n. They're big O(n). So this is O of n, and this is also O of n. Now, as I mentioned before, in reality, it's really just 2 times n, but we're going to drop the constants there since 2 times infinity is going to basically be the same as infinity. Okay, so let's go ahead and see a more complex example of this, of dropping these insignificant terms and these insignificant constants. I'm going to make a function called comp, and it's going to be 3 parts to it. What it's first going to do, it's going to print the first item in the list. Once it's done with that, it's going to print the first half of the list. So the way I'm going to do that is I'm going to call a midpoint equal to the length of that list divided by 2, and then I'm going to say for val in list, and I'm going to slice it all the way to the midpoint index. I'm going to say print val. And then I'm going to say for x in range 10, this is going to be the third operation. It's going to print a string 10 times. It's going to say print, let's just say hello world. Okay, so let's go ahead and make a list. I'm going to say 1, 2, 3, 4, 5, and then call or pass that list into the function. And I get 1, 1, 2, and then hello world, hello world, hello world. Let's go ahead and make this list a little larger so the effect of that midpoint is a little more obvious. All right, so 1, and then 1, 2, 3, 4, 5, and then 10 hello worlds. So what is the big O of this function and the algorithm within it? So let's break down the operations here. Well, notice the first operation, this prints the first item, is O1. So I'll comment that in here, O1. Okay. Now what about this middle operation, which I'm separating with some comments here? So if you notice here, we're going to go all the way to n divided by 2. So in this case, this is order of 1/2 times n, which is the same as n divided by 2. Now keep in mind that this is the same as order of basically 1/2 times n. So just keep that in mind. This is still a constant. So n divided by 2 is the same as 1/2 times n. And that's going to be important because we're going to keep the idea that as n gets larger, these constants will go away. And then this last one, it performs the action 10 times. So it's a constant. So it's going to be constant officially 10 there, order 10. So first part, order 1. Second part is order 1/2 times n. And third part is order 10. So in total, what we can do is add all of these up. And you may need to do this in an interview setting, is add up the different components in order to figure out the entire big O. And in this case, we get something that looks like this. We have an order, or big O, and let's go ahead and make this a markdown cell. So right now, that's the order of that function. 1 plus n divided by 2 plus 10. But now we can actually simplify this. We can see that as n grows arbitrarily large, remember that was part of our definition of big O. As n grows larger and larger, this 1 term and this 10 term become insignificant. And then this 1/2, or the divided by 2 term, multiplied against n, as it grows larger and towards infinity, is really not going to have much an effect. So that means that this function is actually can be simplified down to be of order, or big O, n. All right, so let's just do a brief overview of what we did there. In order to figure out the big O of this entire complicated, well, semi-complicated equation or function, we separate it out into parts, right? Then we put them all together, and then we simplified it as n grows arbitrarily large. And then Finally, what I want to discuss is worst case versus best case. So many times we are only concerned with the worst possible case of an algorithm. But in an interview setting, it's important to keep in mind that the worst case and best case scenarios may be completely different for different big O times. So let's see an example and consider the following function. I'm going to make a function called matcher. It takes in a list and it takes in some item you want to match. And what it does is, given a list, it returns a Boolean indicating if a match item is in the list. So I'm going to say for item in list, if item is equal to match, return true. If no true is returned, then the function will return false. Okay. So remember, I have my list here. It's 1 through 10. And if I call matcher on it and pass in a list and then say I want 1, it's going to return true. So 1 is in that list and we got a match. Now if I call matcher list and I say a number that's not in that list, such as 11, notice I get a false here. Now, when we're concerned about big O, you notice that we have a best case here. So the best case is that the match occurs in the first item of that list. And that means that in this particular best case, you actually have a constant runtime here. The best case is actually O1, constant, since the match is found at the first element. In the case where there is no match, every single element has to be checked, which is going to be n elements. So the worst case is ON. Now, in an interview setting, you're pretty much always dealing with either worst case or sometimes average case. And we'll discuss that in further detail for different data structures. But you can consider it, if someone's asking you what is the big O, consider the worst case. But make sure that you make a point of considering best cases as well. Now finally, I'm going to introduce the topic of space complexity. Many times you're also concerned of how much memory or space an algorithm uses. So right now we've been talking about performance or time complexity, but we also want to keep in mind space complexity. And I'm going to show this through just 2 simple examples. So I'm going to make a function here called def create list. It's going to take in n. And what I'm going to have here is make a variable called new list, which is just an empty list. And then say for num in range n, new underscore list, append a string called new, and then just return new list. Okay, so if I say create list 5, here we have 1, 2, 3, 4, 5 news there. So note how the size of the new list object, this object, scales with the input of n. So right now I'm just talking about space or memory. So in this case, this shows that it's a big O of just n, or linear, in regards of space complexity. It'll have to take up n items in memory. All right. So another example I want to show you is a function I'll call printer. And it's going to print hello world a number of times. So it's going to say for x in range 10, go ahead and print hello world. So if I call printer and I pass in 10, it prints hello world 10 times. So what's the big O for the time complexity here? Well, it has to do this n times, so it has an ON for time complexity. So for time complexity, this is linear. But what about space complexity? How much does this algorithm actually have to attribute to memory? If you notice, it's printing the same thing over and over again. It doesn't actually have to save n items. It just has to save one, the hello world string. So as far as space complexity, it's constant. It has O1. So that's an important difference to make here. In this case, we have space complexity is a constant, O1, since we're only having to save in memory this one item, this print hello world string. But we're doing it as far as time complexity, order n. Okay, so that's just something to keep in mind, that there may be trade-offs between time complexity and space complexity. Usually in interviews, you'll be concerned with time complexity, but depending on the interview question or case or who your interviewer is, you may be asked about both space and time complexity. So it's important to keep them both in mind and know the various trade-offs in certain situations. All right, so as I mentioned before, at the end of this lecture, there's a homework assignment. So make sure you go ahead and read those 2 explanations on more big O notations and more big O examples. All right, just to review what we did here, we went over various examples of different big O notations and big O common functions. All right, thank you very much, and I will see you at the next lecture. Hello everyone, and welcome to the Big O for Python Data Structures lecture. This is going to just be a very brief lecture, and we're going to go over the big O of built-in data structures in Python. And it's going to be 2 data structures, lists and dictionaries. So if you're already familiar with a little bit of CS background, what lists are in Python is they act as a dynamic array, and they support a number of common operations through methods called on them. And the most common operations that are performed on a list are indexing and assigning to an index position. Now what's really amazing here is these operations are both designed to be run in constant time, O1. So let's imagine you wanted to test different methods for constructing a list that looked something like this, 0, 1, 2, all the way to 10,000. What we're going to do here is go ahead and compare various methods on a list or through a function, such as appending to the end of a list, concatenating a list, or using tools such as casting and list comprehension. All right, so instead of jumping over to the live code, I'm just going to go ahead and show you the methods I built out here. So zooming in, first method is this function method 1. We take an empty list and then say for n in x range, or range if you're using Python 3, in 10,000, go ahead and take your current list and then add n to it, which is already in a list. Method 2, what it does is, it takes L, puts it as an empty list, and then it uses the append method. Method 3 uses list comprehension, again using xrange the generator, in order to create that list. Method 4 takes the range and just uses a straight range function. In Python 3, you'll have to use this, list range 10,000. Okay, so if we test these methods using the timeItMagic function, you'll see here that clearly the most effective method is using the built-in range function in Python, which is good to know that the built-in method is the most efficient one. And in most cases, that will be true. The people that write and created this language take a lot of time to think about these things, and that's why built-in functions are very efficient and usually the best choice instead of building out your own functions. So it's important to keep these sort of factors in mind, such as using range or built-in functions, when you're writing efficient code, when you're perhaps whiteboarding on an interview question. So more importantly, we want to begin thinking about how we're able to index with a constant time. We're going to discuss this in more detail when we cover arrays in general, but for now, what I want you to do is just be aware of this table right here. It's a table of big O for common list operations. So here are all the list operations or different methods you can perform on a list, and here's their big O efficiency. And remember, this is just time complexity. Okay, so keep that in mind. We'll discuss how this actually works later on in the course when we discuss arrays. Dictionaries in Python, again if you have a CS background, are an implementation of a hash table, and they operate with keys and values, so you're familiar with this already. K1, 1, K2, 2, and then you can call that K1 and it'll bring out that value. So again, something that's again pretty amazing here is that getting and setting items in a dictionary are also in constant time. So hash tables are designed with efficiency in mind, and we're going to explore them in much more detail later on in this course, since they're one of the most important data structures to understand. In the meantime, here's a table with the big O efficiencies of the most common dictionary operations. All right, so as I mentioned, this is just going to be a brief overview, and by the end of this section, and this section in general of big O analysis, what you'd have developed is an understanding of how big O is used in algorithm analysis, and you should be able to work out the big O of an algorithm you've developed. Okay, so get ready. There's a quiz up next to test your understanding, and the quiz is just going to consist of various code examples, and it's a multiple choice to choose the correct big O of the performance of that algorithm. Okay, so just a quick overview. Keep in mind dictionaries and lists, which are essentially hash tables and dynamic arrays, how they work, and just start wondering how they're able to do this so efficiently in constant time. We're going to go over how arrays and hash tables are actually able to do this when we construct them ourselves, but I just want you to be aware of that. All right, so with that being said, best of luck on the quiz, and I'll see you at the next lecture. Thank you. Hello everyone, and welcome to the array sequence section of this course. And in this lecture, we'll be getting a brief overview of what this section is about and what to expect in this section. So in this section, we'll get a brief introduction to arrays. That includes low-level arrays and dynamic arrays. We'll learn about how arrays are constructed, why they have the big O properties that they have. And we can think about that as the first section of this section of arrays. So this section of the array sequences can be thought of as in two portions. One where we learn about, on a computer science level, how array sequences are built. And then on the second part of it is going to be all the interview problems. So we'll have a series of array-based interview questions for you to solve out on your own. And we'll ease into this second half of the section with an array-based mini project where we're going to build out, based on a project, our understanding of array sequences and how they work. So the first half will be mostly slide-based, and you'll be just looking mostly at notes, the computer science decisions made that really build out arrays properties. We'll do our mini project, and then you'll start tackling actual interview questions presented to you in the Jupyter Notebook format. Okay, so let's go ahead and continue on. Just a brief introduction to arrays, very brief on what we're actually talking about when we use the term arrays in Python. Array sequences in Python, sometimes you'll hear the term arrays and strings as array sequences in Python. So that's because the term array or array sequence is pretty general across all languages. And in Python, we have three main sequence classes. At least these are the three main ones we're going to focus on in this section. We have the list, the tuple, and the string. So all of these support indexing. So for example, if I had any of these objects and indexed them at 0, they would all return the element 1. Okay, so again, as I mentioned, for the rest of this section, we're going to focus on various aspects of arrays, how arrays are constructed. It's going to focus pretty heavily on computer science theory. And then on the second half of this course, we're going to see interview problems that are really heavy on practical uses. So these are interview problems based off of arrays, and your understanding on the first half will help you tackle the problems on the second half. All right, so with that being said, let's go ahead and get started with the section. Hello everyone, and welcome to the low-level array lecture. In this lecture, we're going to be going over basically how computers store information on a low level. So we'll focus on computer memory, how we have memory addresses, so how a computer can actually keep track of where information is stored. We'll have units of memory, such as bits and bytes, and learning how memory is retrieved. So just a quick note, the next few slides are a little text heavy, but as we continue on, we'll see more and more picture examples of what we're actually talking about. So let's go ahead and continue. So in order to accurately describe the way Python represents the sequence types, we're going to have to learn about this low-level computer architecture. So the primary memory of a computer is composed of bits of information. And those bits, they're typically grouped into larger units that depend on usually the precise system architecture, but a typical unit is a byte, which is equivalent to 8 bits. And so a computer system will have a huge number of bytes in memory. And to keep track of what information is stored in what byte, the computer uses an abstraction known as a memory address. And in effect, each byte of memory is associated with a unique number that serves as its address. So for instance, you might have byte number 2144 versus byte number 2147. And in that way, the computer system can refer to the data, and the memory addresses are typically coordinated with the physical layout of the memory system. So let's go ahead and see kind of a drawing example of that. So this is usually how we represent a low-level computer memory. It's individual bytes with consecutive addresses. Okay, so despite the sequential nature of the numbering system, the computer hardware is designed in theory so that any byte of the main memory can be efficiently accessed based upon its memory address. So in this sense, we can say that a computer's main memory performs as a random access memory, RAM. And that is to say, it's just as easy to retrieve, let's say, byte number 8675309 as it is to retrieve byte number 309. So each individual byte of memory can be stored or retrieved in order 1 time, so in constant time. And in general, a programming language keeps track of the association between an identifier and the memory address in which the associated value is stored. So you, for example, might have an identifier X might be associated with one value stored in memory, while Y is associated with another value stored in memory. And a common programming task is to keep track of a sequence of related objects. For example, if you're making a video game and you want to keep track of the top 10 scores for that game, rather than use 10 different variables for that task, you would prefer to use a single name for the group and then use index numbers to refer to each of those high scores within that group. Okay, on to the next slide. So a group of related variables can be stored one after another in a contiguous portion of the computer's memory. And we can denote that representation as an array. So that's what we're really talking about. So let's go ahead and see a more tangible example, such as a text string stored as an ordered sequence of individual characters. And something to note here is that Python internally represents each Unicode character with 16 bits, or 2 bytes for each character. So when we actually diagram it out, it looks like this. So here we have our bits, 16 of them, and since each Unicode character with 16 bits needs 2 bytes for the character, if we have a sample string, so we have a 6-character string here, such as sample, it would be stored in 12 consecutive bytes of memory. Since each Unicode character is taking 2 bytes, or 16 bits, since 2 times 8 is 16. Okay, so what's up next? Just some basic terminology. We have an array here of 6 characters, and each location within the array we can call a cell. And the integer index can be used to describe its location. So for example, in this figure, the cell of the array with index 4 has the contents L, and it's stored in bytes 2154 and 2155 of memory. So something that's important to note is that each cell of an array must use the same number of bytes. And it's this requirement is what allows an arbitrary cell of the array, or any randomly chosen cell, or any randomly accessed cell of the array, to be accessed in constant time based on its index. So in particular, if we know the memory address at which an array starts and the number of bytes per element, so in this case 2 for a Unicode character, and the desired index within the array, then the appropriate memory address can be computed using something like start plus the cell size times the index. So by this formula, since the cell at index 0 begins precisely at the start of the array, the cell at index 1 begins precisely cell size bytes beyond the start of the array, and so on. So in order to flesh that out a little more of some numbers, the cell in this figure, cell 4, begins at memory location 2146 plus 2 times 4, which is 2146 plus 8, which is 2154. And we can see here that indeed the letter L begins at 2154. So I got that by just saying our start is 2146, and I'm adding the cell size, which is 2 in this case. We're using 2 bytes per Unicode character, and times 4, which is the index I want to achieve, or access, excuse me. And that's going to be 2146 times 2 plus 2 times 4, which is 8. So 2146 plus 8 brings us to 2154, and that's how I can access index 4 there, or the letter L. So that's the low level thinking. But usually we're thinking on a higher level abstraction, and basic abstraction is what we're really going to use for real world discussions. When we're discussing the interview problems, we really won't be talking about those bits and bytes. We'll be talking about real world abstraction levels, this higher level where we just say we have this sample string here and the indexes are 0, 1, 2, 3, 4, and 5. We won't be worrying about cell size or bytes per element. Okay, so moving along, the last topic for this lecture is going to be a referential array and how arrays can use object references. So this is a pretty important topic, and it's going to seem maybe a little confusing at first, but at the end we're going to drive it home with a bunch of examples, and it should be pretty clear to you what the array is doing by referencing. So let's imagine we have an example. We have 100 student names with associated ID numbers. So we have a student name, let's say Renee, another student named Joseph, we have Janet, Jonas, Helen, and Virginia, and each of those students has an ID number with them, 0, 1, 2, 3, 4, 5. So we might be considering using an array-based structure to maintain the names of the students currently assigned to the ID numbers. So in Python, we would just use a list of names in brackets, and we want to represent this list with an array. But remember, we must adhere to the requirement that each cell of the array uses the same number of bytes. And yet the elements are strings, and strings naturally have different lengths. So we could attempt to reserve enough space for each cell to hold a maximum length string, not just of currently stored strings, but of any string we might ever want to store. So a maximum length of any possible name, no matter how long their name is. But that would actually be kind of wasteful. We'd be using a lot of space almost preemptively in case a name popped up. So in our last example, we saw the word sample used, but in this case, we'd have to kind of set aside bytes of information for names that we don't know how long they're going to be. So instead of doing that, what we're going to do is make an array and use object references. So let's go ahead and see a diagram of what that looks like. So here we can see that each element is a reference to the object. So we have index 0 referencing the object, that's string Renee. And we have a list now of names where the index is referencing an object. So although the relative size of the individual elements may vary, the number of bits used to store the memory address of each element is fixed. And in this way, Python can support that constant time access, that order 1, to a list or tuple element based on its index. So in this figure, we characterize this list of strings that are names of the students, and it's more likely that we would be able to manage this using that list of references. Okay, so let's go ahead and see some more examples of referencing objects to the list. So this idea that lists and tuples are essentially referential structures is pretty significant to the semantics of these objects classes. So a single list instance may include multiple references to the same objects as elements of the list. And it's possible for a single object to be an element of 2 or more lists. And we'll see what that looks like in a diagram in just a second. So we can have 2 lists simply store references back to the same object. So an example of this is maybe when you're slicing a list, the result looks like a new list instance, but that new list actually has references to the same elements that are in the original list. So let's go ahead and see what that looks like. So here we've computed the slice of a list. Here on the bottom I have a list called primes, and it's just the prime numbers. Notice how each of these indexes, 0, 1, 2, 3, 4, up to 7, is referencing some prime integer. And then if we say temp, some new list, equals primes 3 through 6, this new temp list, this temporary list, is referencing the same elements here, or the same objects. So we're not actually creating new objects, we're just referencing them when we do this slice of the list. Okay, so what if we do some sort of maybe a reassignment? So in this case, when the elements of the list are immutable objects, and since integers are immutable, the fact that the two lists share elements isn't really significant, as neither of the lists can cause a change to the shared object. So if, for example, I said temp of 2 is equal to 15, so here I say temp of 2 is equal to 15, what I'm actually doing is just changing the existing reference here. So I'm not changing the actual integer object. So I didn't change 13, I just pointed to the index 2 on the temp list to another object. Okay. And so the same type of semantics here are demonstrated when you're making a new list as a copy of an existing one. So if you're using a syntax such as what I have here in bold, maybe you make a list, you have a new list that you're calling backup, and you set it equal to list of primes. What you're actually doing is just producing a new list that's a shallow copy, in that it references all the same elements as in the first list. You're not actually duplicating those original objects, you're just duplicating a list that references those same objects. Okay, and if you wanted the contents of the list, maybe like they were immutable type, so you were referencing a list to a list, you could make what's called a deep copy, meaning a new list with new elements, and that can be produced by using the deep copy function from the copy module in Python. Main takeaway here is that if you were to make a new list in a normal manner, you would just be making a shallow copy, in that it's referencing the same elements as the first list. So in order to really show this, we'll kind of do a more extreme example. So a lot of times in Python, and I just added an asterisk notation here. So a lot of times in Python, you'll see a list initiated like this. You'll have an element 0 and then say times 8. So what that's actually doing is you're saying all 8 cells reference the same object. So if you have your list here, counters, each of these cells is a reference to the same object. You're not actually making 8 integer objects. You're referencing them all to the same 0 number there. So at a first glance, you may think this is a little alarming, but what we rely on is the fact that that referenced integer is immutable. So even if you have a command such as taking counters index 2 and adding 1 to it, something like this, so we say counters 2 plus equals 1, that does not technically change that value of the existing integer instance. What it does, it just computes a new integer with value 0 plus 1, and then sets cell number 2 to reference that newly computed value. And then the resulting configuration looks like what we have here in this drawing. So really the takeaway here is how each of these index or indices in the cells and in the list is actually just referencing some object. And depending on how we make our copies, we could just be making a copy of those references, not of the objects themselves. Okay. So last diagram example I want to show you is if you're doing something such as extend. The extend command is used to add all elements from one list to the end of another. But you should note that the extended list does not receive copies of those elements. Instead, it's receiving the references to those elements. And so here we have a diagram kind of portraying that effect. So if I were to say this list primes, remember it was that list from the beginning, we have indexes 0 through 7, and the prime numbers 2 through 19. If I extend it with, let's say, another list that's 3 elements long, extras, what I'm actually doing is I'm just adding the references to the first list here, the primes list. And that's really the main takeaway, that I'm adding references. Each of these cells is really a reference to an object, and I can have multiple lists with multiple cells all referencing the same object. Okay. So just to review what we've gone over in this section, we went over a very basic computer architecture low-level thinking of low-level array representation and how bits and bytes can be used in order to have constant time or order 1 access to any random element in the array. And then we learned about how arrays are able to be referential and use referencing in order for each cell or index to reference an object in an array. All right. So I know we did quite a bit here, and we went over quite a bit. What we're going to do next is learn about dynamic arrays. Now, as far as how this information applies to the interview practice problems, really the main takeaway from a practical perspective is that idea of referencing. So if you want to play around with the more practical perspective of this lecture, go ahead and make a couple of lists, use extend and use append, and then use slices. Maybe try to edit some of the objects that the list indices are referencing, and make sure you really understand that if you make a change on one list, the other reference on the other list may or may not get affected depending on how you code it out. Okay, so that's really where the practical use case comes in here, that idea of referencing and how slices kind of carry over that reference, or how the extend method would also carry over that reference, and that you're not actually, in a sense, duplicating or creating new objects. You're just referencing the old ones. All right. Thanks. I know that was kind of a heavy lecture and pretty theoretical, but overall it's important to know, especially from a practical perspective, that idea of referencing. All right. Thanks, everyone, and I'll see you at the next lecture. We're going to be discussing dynamic arrays. Hello, everyone, and welcome to the lecture on dynamic arrays. Let's go ahead and get started. In this lecture, we're going to learn what is a dynamic array, and we're also going to learn how to implement a dynamic array. So let's just discuss what a dynamic array is. When you're building out a list in Python, you may have noticed that you don't actually need to specify how large the array or that list is beforehand. So for instance, here we have a little diagram that we saw earlier of all the bytes that are allocated to a particular array. But in Python, these lists are dynamic, so you don't need to specify how large your list is going to be beforehand. You can just keep constantly adding to it. So how does Python actually do this? Well, it does this through the use of dynamic arrays. So that list instance actually often has a greater capacity than its current length. So if you put in a list with 3 elements in it, usually that list is going to actually have a greater capacity to hold more elements than just the 3 you initiated it with. But if you keep adding elements to it or keep appending elements to that list, eventually even that extra space is going to run out. So what we're going to do is show a live coding example that really demonstrates the relationship between the size in bytes allocated to a list or array and the actual length of the elements in the array. So let's go ahead and jump to the Jupyter Notebook and show you an example of this. So here we are at the Jupyter Notebook, and let's go ahead and go over some code that I wrote out in order to experiment and explore the relationship between this list's length and the underlying size that the computer's holding in memory. So first thing I did was I just imported sys, the system, and that's going to allow us to use a getSizeOf function, which will let us know the actual size in bytes that the computer's holding in memory. After that, I just set an arbitrary n, and that's going to be the amount of elements in the array. And then I set an empty list called data, and then we're going to say for I in range of n, set a equal to the length of data, so that's going to tell us the number of elements in that list, And then we're going to set b equal to sys.getSize of data. And that's going to tell us the actual size in bytes. And then we're going to print out the format to say length, which is going to report back how many elements are in that list. And then we're going to see size in bytes. And we're going to format or use print formatting to print that out. And then after that, I'm going to increase the length by 1 by just appending that particular number or integer to the list. So let's go ahead and run this and see what happens. Right now we're running it for n equal to 10. I'm going to zoom out a bit so we can see the various print statements. Here we go. So you notice we begin with a length of 0, and we have size in bytes is 64 bytes are being used. Now here's where the interesting part happens. When we increase length to 1, the size in bytes gets increased to 96. But you notice as we keep increasing length all the way up to 4, the size in bytes doesn't actually change. So what Python has done is it's actually set a number of bytes larger than what it needs to hold the current elements in the list while it's appending new elements to the array. So to get a better idea of this, we're going to actually put in a much larger n. So let's go ahead and put in, let's say 50 and run this. Okay, so you'll notice a pattern here. Basically, as we keep adding elements to the arrays, the size in bytes that the list is using increases. But you'll notice it happens in chunks. So for the first element, we have 64 bytes. Let's go ahead and zoom in on that. And then for the next 4 additional elements, we have 96 bytes. So the first element has 64, the next additional 4 have 96 bytes. And then the next 4 have 128 bytes allocated in memory. And then we have 192 for a larger section of the next bytes. And then 264 for a larger section, and then 344, 432, etc. So you'll notice that as we keep adding elements, basically what Python is doing is it's grabbing more and more real estate in memory. And it's allowing us to see that there isn't an underlying change in memory when you insert more and more elements until you need a memory usage jump. So for instance, back here, if we look at the 5th element, size in bytes 128, we can see that we needed to make a memory usage jump. So a basic analogy of, to this system could be almost like a hermit crab grabbing larger and larger shells. So this list is grabbing more and more space in memory until it realizes, hey, I'm growing large enough that I'm probably going to need more in the future, and then it grabs more memory. But it does it in chunks so that it doesn't need to constantly do it for every element that gets appended to it. So even if you just add one element after the first element, it'll still grab 96 bytes, which is going to be able to hold those next 4 elements, 1, 2, 3, and 4. And then when you add the 5th element, it's going to jump to 128, and that's going to be able to hold future elements as well. And it's going to keep doing these jumps almost like a hermit crab, jumping to a larger shell until it grows large enough that it's going to need to jump to another shell. All right, so let's go ahead and go back to the presentation to finish off some of the theory of this. All right, so now at the presentation, what we're going to do is just briefly describe how to implement a dynamic array. And then in the next lecture, we'll actually live code an implementation out. So the Python list class provides a very optimized implementation of dynamic arrays, which we're going to rely on for the remainder of this course. But just for as an instruction, we're going to make our own basic implementation. So let's go ahead and learn the theory behind how we're going to implement this. And then in the next lecture, we'll actually code it out live. So the key is to provide a means to grow the array. Let's say in this case it's A. So we want to grow the array A that stores the elements of a list. And of course we can't actually grow that array because we already know that it needs to have a fixed capacity. So if an element is appended to a list at a time when the underlying array is full, we're going to perform some steps. And let's go ahead and see what those look like. So the steps are going to be, first we allocate a new array, let's call it B, with a larger capacity. And then we set the indices, let's say B of I equal to A of I, for I all the way from 0 to n-1, where n denotes the current number of items. And the reason we are using n-1 is because the index starts at 0. And then what we're going to do is say set A equal to B, and then henceforth we're going to use B as the array supporting the list. And then finally we're going to insert that new element n into the new array. So let's go ahead and see an illustration of this process so it's a little more clear. Alright, so again, here what we have is an array, A. So we have this array A. We allocate a new array B that has a larger capacity. So that was the bytes, that new chunk of bytes that we saw when we were actually programming out that print statement. So here we have this array A. It already has references. We allocate a new chunk of memory space, and we'll call that array B. And then we set the references here on storing elements of A and B. And then finally we reference the array B, now it's array A. So again, the steps are we create this new array B, store the elements of A and B through a reassignment of the reference, and then we call the B array, now it's A, so now we have this new array. And that information, or that memory space that was allocated to the old array, can now be used. What we're not showing here in this diagram is what's called garbage collection of the old array, or the insertion of the new element. We'll go over those in a future lecture. Now, the last remaining issue is to consider how large of a new array to create. A commonly used rule is for the new array to have twice the capacity of the existing array that has just been filled. And later on, we'll actually have a lecture that's describing the mathematical analysis to justify that decision. And so just to go over that again, we want to learn how large of a new array to create. That common rule is twice the capacity of the existing array, and later on we'll see mathematical reasoning behind this. So just to review what we've done, we learned what a dynamic array is. We saw theoretically how to implement a dynamic array, and we also saw some live coding on the thought process and just what's actually happening under the hood, so to speak, where we're appending new elements, but we can see that there's these chunks of bytes and memory that are being allocated as we create new arrays. All right, so up next, we're going to code our own implementation example of a dynamic array. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the dynamic array exercise lecture. In this lecture, we're going to be implementing our own dynamic array class. So, as always, there's a notebook associated with this since it's a live coding lecture. If you go to the array sequences folder under dynamic array exercise.ipython notebook here, if you click on that, you'll get this dynamic array exercise notebook, and it has all the code as well as some notes and lots of comments for you to fully understand what we're going to go through this lecture. So we're going to basically be implementing this class dynamic array. It's going to act similarly to a Python list. So let's go ahead and get started. Really quickly before we begin, we're going to be taking advantage of two features of Python. One is a built-in library called ctypes. You can check out the documentation link here for more information, but it's basically just going to be used here as a raw array holder. If you scroll down to the very bottom of the dynamic array class that we're going to be building, that's the only part where we use it, where we actually make a new array. Okay, and then the second note that I want you to be aware of is we used an underscore before method's name to keep it non-public. So we'll show a quick example of that by copying and pasting this code into the notebook. So for instance now, if I say lowercase m is equal to an instance of that m class, if I do m.tab, I will get public out, but notice I won't get a list containing private because it has that underscore. I would have to specify underscore in order to see all the special methods available to me, and at the very end, one of them will be private. So we're going to make use of that just because certain methods don't make sense for the user to be able to call them. All right, With that all being said, let's go ahead and get started on implementing our own array class. So we've cleared all the cells, and we're going to go ahead and start our implementation. First thing I'm going to do is just import that C types, and we'll get into that later on why we actually need to do that. So let's start building out our class. We'll call our class dynamic array. And remember, it's pep8 to have this capitalized. Pass an object. And let's go ahead and get started. First, we want to initialize. So underscore underscore init underscore underscore. And we're just going to pass in self. And there's essentially 3 attributes that we're going to have here. We're going to have n. We're going to start it at 0. So this is going to be the actual count of the actual elements. So by default, it's 0. We're going to have capacity be another attribute. By default, it'll just be 1. So it can accept only 1 element by default. Remember, we're going to be using a dynamic array style in order to implement larger capacities. And we'll show methods to do that later on. And then finally, I'm going to say self.a, and that's going to be equal to self dot another method, which we'll call make array, and we'll build that out later. And it's going to pass in capacity. Okay, so we have these 3 attributes: the count actual elements with n, the capacity default is 1, and the self.a, which we'll call make array, which we're going to build out later on. The next one we want to do is a special method, length. It's going to pass in just self, and this is going to return number of elements stored in the array. So all it's going to do is return self.n. All right. And then one more special method we want to do is get item. This is going to take in self, of course, and it's also going to take in a k parameter. And what this is going to do is it's going to return the elements at index k. So after creating a dynamic array, you can use indexing to return the element at index. So I'm going to say if not 0 less than or equal to k, less than or equal to self.n. Remember, that's the count of the actual elements. Basically, this is saying if that k, that index you pass, isn't actually in between 0 and the count of the actual elements, we'll have to return some sort of error. And in this case, there's a specific error for this index error. So make sure you go ahead and review errors and exceptions if you don't understand what this sort of syntax is. But what this is just going to do, it's going to print out k is out of bounds if you happen to ask for a k that's out of bounds of the array. So if that clears, then we're just going to say return self.a of k. So we're going to retrieve from our labeled a array at index k. And the reason we're using that self.a notation is to reflect back on the diagrams from the previous lecture where we had 2 arrays, A and B array. So we'll also keep the B array notation later on as we implement this further. All right. Next method we're going to create is the append method. So this is going to add an element to the end of the array. So I'm going to say append. We can zoom in here a little bit. I'm going to say append. It's going to take self argument since we're acting on that instance of the object. And it's also going to take ele, which stands for element. So it's going to add that element, that ele, to the end of the array. And this is where we're going to have to check our capacity. So as we mentioned in the previous lecture, I'm going to say if self.n, so the count of the actual elements, if that's equal to the capacity, self.capacity, whoops, colon, then I'm going to say self.n And what I'm going to have to do is if my current count is equal to my capacity, I'm going to double the capacity if there isn't enough room. So later on, what I'm going to do is create a private method called resize. So in this case, I'll say underscore resize 2 times self capacity. And just keep a note here, 2x if capacity isn't enough. All right. So when we're going to append an element, we check to see if our current count is equal to our capacity. If it is, we're going to resize and double it. After we do that, we can say self of our A array, pass in n, and set it equal to LE. So we set self.n index to the elements, and then since that's equal to the elements, what I'm going to have to do is add 1 to that count. All right, so we double the capacity, and then we take that last one at n, that last count, set it equal to that new element that we're appending here, and then add 1 to n, to our count. All right, so since we mentioned this underscore resize special method here, let's go ahead and build that out. So I'm going to say def underscore resize. It's going to take in self, and then it's also going to take an argument, new cap, which is the new capacity, which is what we were passing in here that I'm highlighting right now, 2 times the current capacity, self.capacity. And this is going to resize the internal array to the capacity of that new underscore cap. So we're going to use the same sort of notation we used in the last lecture, b. So I'm going to say this b array is equal to self dot make array, and we're going to be using that ctypes library that I mentioned earlier to use that make array method. We haven't developed it yet, but we'll do it after we finish out this resize method. So we're going to make array, and it's going to accept new cap as an argument. So we make a new bigger array and call it b. And then we say for k in range self.n. So we reference all the existing values. I'm going to set b of k equal to self.ak. So here I'm just referencing, as we saw in that previous diagram in the previous lecture, basically referencing all the existing values from A into B. Once we're done with that, I'm going to say self.a is now equal to B. So I call A now that new bigger array. And then I say self.capacity is equal to new cap. So I reset that capacity. All right. And then lastly, we're just going to make a method that actually makes arrays. And this is going to make the raw array that we're actually creating. And this is going to take in self and new cap. And this returns a new array with the new cap capacity. And so we're going to be using that ctypes library here. It's just going to be a one-liner. Don't worry too much about what we're actually typing and how this is working. You can essentially just think about it as grabbing those raw bytes and creating that array. And so it's going to be new cap times ctypes.py underscore object and close parentheses afterwards. So just go ahead and feel free to copy this line from the Jupyter notebook that's available to you. So that's it. That's our entire dynamic array class. Let's go ahead and run it, this cell, and make sure we haven't messed anything up. All right. Let's make a variable called ARR and instantiate it as a dynamic array. Run it. All right. Looks like it's working so far. So let's go ahead and do some things to it. Let's go ahead and say r.append. Let's append the integer 1 to it. All right. Now let's check the length of r. array, and it's 1. So let's go ahead and append another array, or excuse me, another integer. And now let's check the length of the array. And it looks like the length is now 2. And now let's see if we can actually access it using indexing methods. And it looks like we can. So at index 0 we have 1, and at index 1 we have 2. All right, so that was it. We actually made our own dynamic array. Let's go ahead and do a quick rundown of all the methods since we created them all. So we're going to zoom out a bit here. So starting off with the class dynamic array object, we started with some attributes here, self.n, which was the actual count of the elements in the array. We start off with 0 elements in the array. Then we have the capacity of the array. We start off with just being able to hold 1 element. And then we have self.a equal to self.makeArray of self.capacity. So in this case, when we start out, we set a equal to an array of capacity 1. So we come down here and using that ctypes library actually make that raw array. Then we start off with some special methods, length, just to return that count, get item, that allows us to index, but first we do a check to see if it's actually in bounds for that k. If it is, we just return a indexed k. And then we have this append. And this is really the key to understanding all of this, is that we check our actual count against the capacity. And if it's equal to it, then we resize to double the capacity. And that's really the main point of this dynamic array, that instead of having this huge array since the beginning, we just check as we add elements if our count is equal to the capacity, and we double if the capacity isn't enough. That's really what makes this array a dynamic array. And we can keep adding to it, and the space that we have will keep growing as we go along. Then once we do that, we just say a at self.n is equal to element, and we add a count at that n. Then we created a method called resize, which sets this array b, almost like a temporary array, equal to make array at that new capacity. Then it says for k in range, self.n, we basically re-reference everything in a to b, and then we set self.a equal to b again, and we set the capacity equal to the new cap. And then finally, this make array uses the ctypes library to make that raw array that we're referencing throughout the entire class of this dynamic array object. Okay, so that's it. What I want you to do now as a little homework assignment is play around with it, and I want you to see how it auto-resizes. So try using the same sys.getSizeOf. So if I jump over to the Jupyter Notebook, try using this right here. Let me zoom in on it for you guys. This sys.getSizeOf. As remember, if in some previous lectures, we used that to see how many bytes were actually being held. So go ahead and check the length of the array, and then check the size of it, and see how it changes and doubles as you add more elements and reach certain capacities. All right, that's it for this lecture. I hope it was interesting for you to see our own implementation of a dynamic array. And remember, the key takeaway is really this append method here, where we're checking the capacity and doubling it if there isn't enough room, and how we're resizing the array by referencing a new array to all the existing values, and then resetting a to that new array b. Okay, thanks everyone so much, and I will see you at the next lecture.
Hello everyone, and welcome to the lecture on amortization. So we've already discussed dynamic arrays, we've implemented a dynamic array, and we've learned that when dynamic arrays get full, they double in size. So in this lecture, we're going to do an amortized analysis of dynamic arrays. So, the strategy of replacing an array with a new, larger array might at first seem slow, since a single append operation may require order n time to perform. Our new array allows us to add n new elements before the array must be replaced again. So, what we're going to do is use an algorithmic design pattern called amortization. We can show that performing a sequence of such append operations on a dynamic array is actually quite efficient. So, again, just to reiterate, remember, if we have a current number of elements and we're going to overflow, that is, fill up the array, we're going to double it to get more room. But on that doubling, that means that primitive operations for an append is going to be order n. So here we have 1, on 2 we have to double, on 4 we're going to put a append, so it's going to be order n. On 8, again an append will be order 8. On 16, order 16. Everything else is just going to be order 1, or constant. So again, what we're going to do is allocate memory for a larger array of size, typically twice the old array. Copy the contents of the old array to the new array, and then free the old array. Let's go ahead and see a diagram of this process. So, here we have a dynamic array. Initially, we'll call it the table, it's just empty and the size is 0. Insert item 1, we're having an overflow since our array is full, so we have to double it. When we insert item 2, again we're having an overflow, the array is full, so we have to double it. On inserting item 3, you're fine, but inserting item 4, you have to double it because you're having an overflow. Then on 5, 6, and 7, you're alright. So let's do an analysis on this process. Here on the left, we have that same figure showing the insertions. And here on the right, we're actually going to do analysis. So for item number 1, for instance, our table size is 1. So our cost of putting that append or inserting it into that table or array is just 1. Item number 2, table size was 2. So our cost was 2, order n. And here's where basically the magic of the amortized analysis happens. On item number 3, the table size has become 4 since we doubled it, meaning our cost is 3. And then on item number 4, since we've already doubled the table size to 4, our cost is now just 1 for that insertion. Then on item 5 and table size 8, our cost is 5. But for 6, 7, and 8, since the table size is 8, our cost of insertion is actually just 1. So the amortized cost, we can actually sum this all up and divide it by n, the number of items in that array. And we can actually simplify that above series by breaking the terms 2, 3, 5, 9 into 2 as 1 plus 1, 1 plus 2, 1 plus 4, 1 plus 8. So we have those n terms, that 1 plus 1 plus 1, and then using a bit of a math trick, we can have the other ones go 1 plus 2 plus 4, etc., divided by n. Meaning we have n plus 2n over n, and when you divide n out, that will be just 1 plus 2, which is 3. So the amortized cost is actually constant at order 1. So, go ahead and check out the resource section of the lecture for a PDF of a more detailed explanation. That's going to be your homework assignment, so make sure you read that full PDF explanation. It's just a few pages long, but again, it's a nice amortized analysis. This isn't really necessary for you to know, given what the array interview questions are going to look like, but you should know it if you're interested in how a dynamic array works. So, up next, we're going to have a lecture overviewing the interview problems in this section of the course, and after that, we'll get started with the interview problems. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the array interview problems half of this section of the course. So, as you already know, technical sections are essentially split up into 2 parts: theory and learning exercises, and then the interview problems and solutions. So sometimes that theory lines up really well with common interview questions. Unfortunately, this isn't actually the case with arrays. Most likely you're going to find that the interview problems here, just for this section, don't have much in common with the theory and exercise lectures. And that's just because of the way array-based questions are asked in interviews. So, another thing to mention on the array interview problems is don't use Python tricks when answering the interview problems. And this will also be noted in specific interview problems. So for example, if you're asked to reverse a string, don't use a Python slicing trick, since your interviewer isn't really looking for that. Again, these interview problems will seem very challenging. If you find yourself completely stuck, try writing out what you would do manually to solve the problem. Just brute force the solution. And it's highly suggested you try solving these with pen and paper or a whiteboard first. Don't just code out your solution. So, using a whiteboard or pen and paper for a problem makes it much harder. If you're completely stuck on a problem and have already tried brute forcing it, give it 1 or 2 days and try it again. And if you're still stuck, look at the solution and code it out. Then, wait 1 or 2 days and try the problem again on pen and paper. Keep in mind what the requirements are for that specific interview problem. So, again, the lectures alternate between problems and their solutions, so just keep that in mind. With that being said, good luck, you got this. Thanks, and I'll see you at the first interview problem. Hello everyone, and welcome to your first interview problem for the array sequences section of the course. This problem is called anagram check. Problem statement is this. Given 2 strings, check to see if they are anagrams. So as a reminder, an anagram is when 2 strings can be written using the exact same letters. So you can just rearrange the letters to get a different phrase or word. So, for example, the string public relations is an anagram of crap built on lies. And the string Clint Eastwood is an anagram of Old West action. So, just a quick note, for this problem you can ignore spaces and capitalizations. So D space G-O can be an anagram of God and dog, and O space D space G. So again, you're given 2 strings and you need to check to see if they're anagrams. So fill out your solution below in this function. And here we can see anagram of dog and God, Clint Eastwood and Old West action, AABB, and true, true, false, the booleans. You can run this cell right here to test your solution below and see if you can pass the test cases. Alright, with that being said, best of luck. In the next lecture, we'll go over the solution. Thanks everyone. Hello everyone, and welcome to the solution for the anagram problem in the array sequence section of the course. As always, there's a full notebook of the solution, and it explains every step of the way, as well as gives you the code that we're going to go through in this video. So, to start off with, there's 2 ways of thinking about this problem. First off, if 2 strings have the same frequency of letters or elements, meaning each letter shows up the same number of times in both strings, then they are anagrams of each other. On a similar vein of that logic, if 2 strings are equal to each other once they are sorted, then they are also anagrams of each other. So let's go ahead and implement the second solution first, since it's the easier one of the 2. So we'll go ahead and make our function anagram. Takes in 2 strings, S1 and S2. And then what we're going to do is just remove spaces and lowercase all the letters. So I'm going to say replace. And what this replace method does, it's a method on a string, and it says basically replace all white space right here, a single white space with no space. There's no space between those single quotes. And after that, I'm also going to lower it. So let's go ahead and copy this line, and then just change it to S2. So what we're doing now is just taking the strings, both of them, and reassigning them to remove all the white space and then lowercase all the letters. After we've done that, we can simply return a boolean for the sorted match. So I can say return sorted S1 double equal sorted S2. So all I'm doing right now is I'm just comparing the strings that we've replaced after we removed the spaces and lowercase letter. I'm saying if they're sorted and then they're equal to each other, then we know they're anagrams of each other. So let's go ahead and test this out. We have anagram. Let's go pass in God, or whatever. God, and let's say dog. And that's true. Let's go ahead and pass in, let's say, Clint Eastwood, the example from the problem notebook, Clint Eastwood. And we'll do Old West action. So notice how there are different amount of spaces. The first one has 1 space. This second one has 2 spaces, but that won't matter because we had this replace method in there. And if we run that, that's true. If I add another letter in, it becomes false. So we know the solution's working. Great. So this sorting method is actually really quite simple, but it's not the optimal way. And in an interview setting, you're probably going to be asked to implement a more manual solution involving just counting the number of letters in each string to test your ability to understand hash tables, which we go over later on in this course. So what we're going to do is build out a fuller solution using counting and Python dictionaries. So let's go ahead and call this anagram 2. We're going to do the same thing to start off with. Remove the spaces and lowercase the letters. And then we're going to start off with an edge case check. So I'm going to say edge case check as a comment. What I want to do is check if they have the same number of letters. If both strings don't have the same number of letters, we can immediately say it's false, it's not an anagram, since they need to have at least equal matching number of letters. So I can do this by saying if the length of S1 doesn't equal the length of S2, return false. Okay, so let's go ahead and continue on. Next up, we're going to create a counting dictionary. So we could use a default dict from the collections module, but so that we don't use any special modules in Python, we're just going to use a straight up dictionary. Call it count. So we're basically just going to count the frequency of each letter appearance and then check that all the counts are the same. So what we're going to do is fill the first dictionary with the first string, and then fill a dictionary again for the second string, but subtract counts. So the first time around we're going to add counts for each letter. Second time around we're going to subtract counts. And then if we check that all the counts are equal to 0, we know they're anagrams. So let's go ahead and code this out so it's a little bit clearer. So I'm going to say for every letter in S1, that's string, if letter in count, then I'm going to say count letter of that key plus 1. Else count letter equals 1. Okay, so what is this doing here? I'm saying for every letter in that first string, if the letter is already in my dictionary, then add 1 to that key, that letter key there. So as we go along, let's say it's Clint Eastwood. So I see C. Then I say if letter is in count, well, actually C, since it's the first letter as we go along the string, it's not going to be in count yet. So we're going to say else, and that's where I set this. I set count of that letter, which happens to be C. So at that key C, we're going to set it equal to 1. And then we're going to basically do the reverse for the second string. I'm going to say for letter in S2, if letter in count counts letter, I'm going to say minus 1. Else count letter is equal 1. And now I just want to check that all the counts are 0. So for k in count, if counts of k, let's go ahead and zoom out a little bit. If count of k is not equal to 0, I'm going to return false. Otherwise, they're anagrams, so I can just say return true outside of that for loop. So let's go ahead and make sure this solution works. Let's fix that. Okay, so if I call this anagram 2, then we run it. Still false, that's good. Let's see if it works here. And it's true. Great. So a quick note on this second solution. Again, the use of a default dict form from the collections module in Python would clean up this code quite a bit by not having to do these checks. But the thing is, we don't want to use things that might only be specific to Python, so we'll make sure to count out every step. One other thing that might clean up this code, you could technically put in this into the second for loop and build it in, but I quite like this solution because it's really clear what we're doing here. So again, let's just go over each of the steps. This should be your preferred solution if you get asked this in an interview setting. So to check if they're anagrams or not, first off, we clean up the strings. We lowercase all the letters, remove any white space. Great. We do an edge case check. So this should quickly tell us if they're anagrams or not. So we do if length of S1 isn't equal to length of S2, return false. Otherwise, we have a possibility of an anagram. So moving along, we create a dictionary called count. Then for every letter in that first string, if the letter's already in our counting dictionary, we're just going to say count at that letter, so that key, add 1 to that count. Otherwise, set it equal to 1. For letter in S2, which is that second string, do the same thing, but now we're going to be subtracting. So if letter in counts, then we're going to subtract 1 from it. Else, that count of that letter is equal to 1. And this is the setting right here that's basically going to trip up this third for loop in case it's not an anagram. That's why this is, again, a positive equal to 1. So this is what's going to be going off if this is not an anagram, along with this as well. So then it says for k in count, if count of k is not equal to 0, return false. So if it's an anagram, then this line should have occurred as many times as this line. All right, hopefully you understand. Should have been pretty straightforward. Go ahead and code this out. The tricky part to this question actually is having to do this by hand. It's a lot tougher, so I recommend that you go ahead and take out a pen and paper or a whiteboard and code out the solution by hand. All right, with that being said, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called array pair sum. For this problem, given an integer array, output all the unique pairs that sum up to a specific value k. So for example, here's our function called pair underscore sum. Takes in 2 arguments, a list, so that's our array, and then a specific value k, in this case 4. And it would return 2 pairs, 1 and 3, and then 2 and 2. So you have 2 pairs here that are unique that can sum up to this value 4. Quick note, for testing purposes, change your function so it outputs the number of pairs. So in this case, it would just output 2. However, your function should still be able to return the pairs themselves. But at the end, just count the number of pairs if you want to test your solution using the test cell. So, fill out your solution here below, and then run this test cell to test your solution. All right, best of luck everyone. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the solution for the array pair sum problem. Just to go over the problem statement again, it was given an integer array, output all the unique pairs that sum up to a specific value k. So, in this case, the array is a list, a Python list, and then the second argument is just an integer, that specific value k, and you would return pairs. So, let's go ahead and go over the solution. The solution we're going to go over is order n. So it's going to use the set data structure. What we're going to do is perform a linear pass from the beginning, and for each element, we check whether k element is in the set of seen numbers. If it is, then we found the pair of some k and add it to the output. If not, this element doesn't belong to a pair yet, and we add it to the set of seen elements. The algorithm is really simple once we figure out using a set. So the complexity is order n because we do a single linear scan of the array, and for each element we check whether the corresponding number to form a pair is in the set or add the current element to the set. Insert and find operations of a set are both average order 1 constant, and we'll look at that later and why it's order 1. But the algorithm in total, since we're just doing n passes, is order n. So here's the solution. Let's go ahead and go over it and explain all of this as we code along. So let's go ahead and jump over. So first thing we're going to do is create our function and have it take that array and then that specific integer k. We can do an edge case check in case there's less than 2 elements in the array by just saying if the length of array is less than 2. We can even just say return. That means it's just not going to return anything. But you can have it return a string or print a statement, error less than 2 in the array, that kind of thing. It's up to you. Then let's go ahead and make our sets for tracking. So we'll make seen equal to a set and make output equal to an empty set. So this sort of seen equals set using a set for tracking is something that you're going to see over and over again as a strategy for interview problems. This is the first time we've seen it so far, but keep this in mind. It's a really great strategy at converting things that might seem like will take order n squared and reducing it down to a linear order n. Okay, continuing on, let's go ahead and get to the meat of our solution. I'm going to say for every number in our array, so for num in R, I'm going to set the target difference. And what I mean by that is I'm going to create a variable called target, and I'm going to equal to the difference between k and that number. So remember, k is the integer we're trying to find the two numbers that sum up to it. And right now, k minus num is the target we're reaching for. So if that target is not in the numbers we've already seen, we're going to add it. The number, that is. Otherwise, if it isn't seen, we can add the tuple with the minimum corresponding pair. So remember, I asked you to actually keep track of those pairs. We'll return the length of the output, but in this case, I actually want you to output the pairs themselves as well, just so we know we're able to do it. So we're going to add a tuple. The way we're going to do that is by saying, take the minimum between the num and the target, and then take the max between the num and the target, and that's going to be the tuple we add to the output. And then I'm just going to say return length of the output. In this case, let's go ahead and check it out. So we have our solution. Let's make sure it works. I'm going to say pair sum. Let's go 1, 3, 2, 2. Put in 4. We should get, oops, looks like we have an error. Add takes exactly one argument. Let's go ahead and make sure that we have enough to make this a tuple, which we forgot. And I'll go over this line in just a second. Okay, so that's correct now. We are missing a set of parentheses here. Okay, now let's go ahead and add a one-liner to print out the actual tuple. So I'm going to comment this out and say return. This is a little trick to print a new line. And I'm going to join, and I'm going to map a string to the list of the output. So this is kind of a bit of a Python trick just for printing stuff out so it looks nice and it's legible. So if we run this, whoops, we don't want to return this, we actually want to print this. There we go. Okay, so here we have the two pairs as a tuple. Let's go ahead and go over our solution again so we can really break down this line and the logic here. As far as what this line's doing, it's just taking the output, converting it to a list, making sure all those tuples are strings by mapping the str function, which converts stuff to a string, to every element in that list, and then it's joining them with new lines in between. So if you print it, you get these strings of tuples, which have been converted into just a parentheses, 1, comma, the integer, and another parentheses. Okay, so let's break down the important stuff. So we have our edge case check in case there's less than 2 elements. And then we have our sets for tracking, the numbers we've seen, and our output. So we're going along the array and we're saying for that number in the array, the target number we're looking for will be k minus num. So that makes sense, right? So for instance, if we have 4 and we're at the first digit, which will be 1, then we're looking for 4 minus 1 is 3. On the first number, we haven't seen it yet. But you'll see on the second pass, we'll add that to scene and be able to find it. So then we say if target is not in scene, we haven't seen that number yet, we go ahead and add it to that set. And then else, what we do is we add it to the output. So we say output.add, and we take the minimum between the current number and the target as one of the pairs, and then we take the maximum between the number and the target. So we want to find out which was the minimum, so whichever was less between that number we're currently on and the target we're seeking as one of the items in the pair, and the other integer in the pair will just be the one that's greater between the number and the target. Okay, that's it for this solution. Again, just remember, in order to test your solution on the test cell, you had to return the number like this format. So you got something like this. All right, that's it for the solution to the pair sum problem. go ahead and read the entire solution notebook in case you want an explanation of the logic even further, but that's it for the solution. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called Find the Missing Element. So, here's the problem statement. Consider an array of non-negative integers. A second array is formed by shuffling the elements of the first array and then deleting a random element. Given these two arrays, find which element is missing in the second array. So here's an example input. The first array is shuffled and the number 5 is removed to construct the second array. So we have 1, 2, 3, 4, 5, 6, 7. And then on the second array, we have 3, 7, 2, 1, 4, 6. So your function, which we'll call finder here, should be able to take in both arguments and then find the missing number. Go ahead and fill out your solution below here in Finder, and then you can test your solution by running this cell. Here are some examples of what it should output. Alright, that's it, and I'll see you at the next lecture. Thanks everyone. Hello everyone, and welcome to a lecture on finding the missing element solution. So let's go over the problem statement one more time. Consider an array of non-negative integers. Then a second array is formed by shuffling the elements of the first array and deleting a random element. Given these two arrays, find which element is missing in the second array. So for an example, we have this array, this list, and then the second array, a list. Something to take note, I'm saying the term array, but that's just to be agnostic about which programming language we're using. So in an interview setting, you'll be asked about arrays. In Python, these are just lists, as we said before in the beginning of this section. So again, I get one array as a Python list, a second array as a Python list. The second array has shuffled elements of the first one and a deleted random element. Your function should be able to find that random element that was missing. So let's talk about solution and theory and logic. So the naive solution, just brute forcing it out, is to go through every element in the second array and then check whether it appears in the first array. Note that there may be duplicate elements in the arrays, so you would need to pay special attention for that. The complexity of that approach is order n squared, since we would need to do 2 for loops for that. A more efficient solution is to sort the first array. So while checking whether an element in the first array appears in the second, we could do a binary search. We'll learn more about binary searches in more detail in the searching and sorting section of this course. But with that solution, you still need to be careful about duplicate elements. The complexity of that solution is order n log n. If we don't want to have to deal with that special case of duplicate numbers, we can sort both arrays and iterate over them simultaneously. Once the two iterators have different values, we can stop. The value of the first iterator is the missing element. So this solution is also order n log n. So let's go ahead and do the solution for this approach. Let's jump to the solution notebook and code it out and explain along the way. So what we're going to do is define our finder function. Takes in the arrays. We'll go ahead and sort the arrays. So now that the arrays are sorted, we're going to compare elements in the sorted arrays. So for num and num2, num1 and num2 in, I'm going to zip the arrays together. And I'll show you what zip does in just a second in case you're not familiar with it. It's a bit of a Python trick as far as simplifying our code and making it clearer to read. And then I'm going to return the first element if I don't get a return of the first number there. So I'm going to explain zip first, and then we're going to walk through this entire code. As far as what zip does, it essentially just zips together lists. So if I pass in lists like this, 4, 5, 6, the output is a zipped up matching pair of the tuples. So I get 1, 4, 2, 5, 3, 6. So it takes the first element, puts them together of each list, second element of each list, puts them together in a tuple, third element of each list, puts them together in a tuple. So it returns a list of tuples, and I'm doing tuple unpacking here in order to grab those elements. So continuing on, let's go ahead and walk through our solution. First thing we're doing is we're sorting both arrays. So we're sorting both arrays, and then we're saying for those numbers and those pairs, as we go along the indexes, if the number of the first array isn't equal to the number of the second array, then we know we're just going to return the number of the first array because it was missing after we sorted them. Otherwise, we're just going to return the last elements of the first array. So let's go ahead and copy some code to test out this problem or our function solution. This was the example at first, and we got 5 out. All right, great. So in most interviews, you're actually going to be expected to come up with a linear time solution. We can use a hash table and store the number of times each element appears in the second array. Then, for each element in the first array, we're going to decrease this counter. Once we hit an element of 0 count, that's the missing element. So let's go ahead and check out this solution. We're going to learn about hash tables in a more formal manner later on in the course, so don't worry if you don't understand full hash tables right now. But in order to do this, what we're going to do is take advantage of Python and its collections module. So I'm going to say import collections. Let's go ahead and do that. All right. So we're going to do a default dict from collections module, which is just a dictionary in Python where if the key isn't already in the dictionary, it will automatically add it for you. All right. Let's go ahead and use it. So our second solution looks something like this. I take in both arrays, and this is where collections comes into play. I'm going to say D equals from collections, a default dictionary that takes in integers. So all this does is allows us to avoid key errors. So if the key isn't in the dictionary, instead of throwing up an error, it's going to just add the key to that dictionary. All right, so what I'm going to do is add a count for every instance in array 1. So I'm going to say for num, and actually let's do this for array 2. I'm going to say for num in array 2, dictionary num, add 1. And then I'm going to check if the number isn't in that dictionary. So I'm going to say for num, in this case, the first array, so we're going to say R1. If that number's count is equal to 0, return num, because we never counted it. And otherwise, I'm just going to say else that number is going to be subtracted. So let's go ahead and check the solution, and then we're going to walk through this. All right, so that looks like it worked and matched up. Let's go ahead and check it on our second one by putting in finder2 here. Also worked. Great. So let's go ahead and walk through this. What are we actually doing here? Well, we're importing a default dictionary. And again, this is the same as a normal Python dictionary, but if the key doesn't already exist, there's no error, you just add the key. So I'm going through the second array, and I'm counting how many times each element shows up. So I'm saying for number in array 2, set that key plus 1. Note, I'm avoiding the little if statement, so if num in dictionary or D, because I'm using a default dict. So that's what allows us to write this as one line right here. If you try doing this with a normal dictionary, this line would throw an error if num wasn't already a key in the dictionary D. But with default dict, we're allowed to do that. So, as I mentioned, we go along the second array. For every number in it, we add a count. Then, in the first array, what we're doing is for num in array 1, if it's equal to 0, we return num. Otherwise, we're going to subtract 1. All right, so there's two other possible solutions, one of them which we're going to code out, and the other one we'll talk about. The one we're going to talk about is just, you could compute the sum of all the numbers in array 1 and then array 2, and then subtract array 2's sum from array 1's sum, and that difference would be the missing number in array 2. However, this approach could be problematic if the arrays are too long or the numbers are very large. you could end up getting an overflow when summing up the numbers. Or if the numbers are really, really small and have a ton of decimal places, you may lose some information. So your interviewer probably actually wouldn't like that approach. Even though you might think it's pretty clever, algorithmically and in a programming sense, it has trouble. If the arrays are too long or the numbers are very large, you could get an overflow issue. So I would recommend mentioning it, but also mentioning the problems with that solution. Here's the clever trick version. So you could achieve a linear time and constant space complexity without any problem. And the way to do that is you could initialize a variable to 0 and then do an exclusive OR of every element in the first and second arrays with that variable. So what's an exclusive OR? If you go to the solution notebook and scroll down here, this is what we're at right now. By performing a very clever trick, you can do an exclusive OR. And an exclusive OR basically is a bit comparison. And you can read about it more on the Wikipedia link here. And we're going to go over this exclusive OR. We'll see it again in another interview problem. So don't worry about understanding the solution completely right now. You'll see it again later as far as the exclusive OR. And what it does is it shows outputs when the inputs differ. So if your input is A and B, if it's 0, 0, your output is 0. If one of them is 1, then you get 1. If one of them is 1, you get 1. If they're both the same, you get false. So by performing this kind of clever trick, basically what you do is we scroll down here, initialize your result to 0, and then perform an exclusive OR between the numbers in the array. So for num in these sum here, R1 plus R2, we're actually just adding lists, remember that. So if I do this in Python, let me just copy and paste that to show you what it does. If we take these two arrays and add them together like this, then we're just basically concatenating the arrays together. We're not actually summing each element. So then you say for num, the result, do an exclusive OR with that number, and then just print the result so you can see it as it goes along, and then return the results. So this is kind of a clever trick, and I wouldn't expect you to know it right off the bat. And we're going to go much deeper into exclusive OR because it shows up in another interview problem as a really good solution, and not just a clever trick solution. So don't worry if you don't completely understand this last solution. We're going to see it again later on in this course. Make sure you do understand this solution right here, and if you don't understand the default dict, then try implementing the solution with just a normal dictionary. And then remember, you could have also sorted the elements, but make sure you understand the problems with the order complexity of this solution. Alright, that's it for finding the missing elements. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called largest continuous sum. Here's the problem statement. You're given an array of integers, positive and negative integers, and you need to find the largest continuous sum. So, fill out your solution below into this function. Something to note is that many times in an interview setting, the question also requires you to report back the start and end points of the sum. Keep this in mind and see if you can solve that problem as well. We're going to see it in the mock interview section of the course later on. So you will run into this problem again with a little more detail and some different requirements for you. But in this case, all you're required to do in this situation is just find the largest continuous sum. So here we have inputted an array as a Python list, and the largest continuous sum we can get here is 29. Alright, that's it. This is a little trickier than it might seem, so keep that in mind. You can run this cell here to test your solution. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the solution lecture for the largest continuous sum problem. So the problem statement was, given an array of integers that could be either positive or negative, find the largest continuous sum. So our solution goes a little something like this. If the array is all positive, then we just simply need to sum all the numbers. So that makes sense. The negative numbers in the array is what's going to cause us to need to begin checking sequences. So here's the algorithm we're going to follow. We start summing up the numbers and store in a current sum variable. After adding each element, we check whether the current sum is larger than the maximum sum encountered so far. If it is, we update that max sum. As long as the current sum is positive, we keep adding the numbers. When the current sum becomes negative, we start with a new current sum, because a negative current sum will only decrease the sum of a future sequence. And note that we don't reset the current sum to 0 because the array can contain all negative numbers. Then the result would be the largest negative number. So let's go ahead and see the code here and then walk through it and code it out. So we're going to start by just saying, let's go ahead and delete this. Whoops. We're going to start out by naming our function, and we're just going to call it large underscore const for continuous sum, and it takes in an array, in this case our Python list. So we're going to check to see if array is length 0 first, because we know if that the array is length 0, we just return 0. Or you could also put none. So what we're going to do is start the max and current sum at the first element. So I'm going to take in and create two variables. I'm going to say max sum is equal to current sum is equal to the first element, array 0. And now we're going to go through the algorithm. So I'm going to say for every element in the array, so for num in array, and I'm actually going to skip that first element since we've already set it as our maximum sum and our current sum. So I have that going on. And then what I'm going to do is set the current sum as the higher of the two. So I'm going to say current sum is equal to max of current sum compared to, well, plus the number compared to the number itself. So what I'm doing is I have my number, I have my current sum, and I'm setting current sum plus the number we're at right now versus just the given number. Take the max of that and set it to be the current sum. Next, what I'm going to do is my max sum is going to be whichever is greater between the current sum and the current max. So current sum and max sum. And then all I need to do is return the max sum. So let's go ahead and see if this works. I'm going to call and paste. So here I have an array. We have 1, 2, -1, 3, 4, 10, 10, -10, and -1. So our sequence that should produce the highest sum is right here. Let's go ahead and see if it gets it. So it's calculating out, and it gets 29. Great. So many times in an interview setting, this question also requires you to report back the start and the end points of that sum. Keep this in mind and see if you can solve that problem. We'll actually see that statement of the problem, returning back the start and end points, later on in the mock interview section of this course. So let's go ahead and walk through the solution one more time. So let's go ahead here and check it step by step. First thing we're just doing an edge case check. If the array length is equal to 0, we just return 0. For the rest of it, this is what we're doing. We're starting by saying the max sum and the current sum is equal to the first element. Then, going along for each number in that array, not including that first element, we take the current sum and find out which is larger, the current sum plus the current number, or the current number itself. Then, reset the current sum equal to whichever one of those two is larger. Then we have the maximum sum tracker, and we're going to keep track of current sum and max sum. Whichever one of those is larger gets reset for the max sum. After we go for each number in the array, we'll have our final max sum as basically the largest current sum there ever was compared to the max sum, and then we just return the max sum. Alright, so again, we sum up the numbers and store it in some sort of current sum variable, which was here. Then, after adding each element, we check whether the current sum is larger than that maximum sum encountered so far. If it is, then we just updated that maximum sum in this line. As long as that current sum is positive, we can just keep adding the numbers. When the current sum becomes negative, we start with a new current sum. Because a negative current sum will only decrease the sum of a future sequence. And that note here, we're not resetting that current sum to 0 because the array could contain all negative integers. Then the result will just end up being that largest negative number. Okay, so that's it for the solution. Go ahead and go through it. And really make sure that when you're going through this, you're also practicing going through it by hand with pen and paper or on a whiteboard. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called sentence reversal. So, given a string of words, reverse all the words. So for example, this is the best, you want to return best the is this. As part of this exercise, you should also remove all leading and trailing whitespace, so that inputs such as space, 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 and then the words space here, and the words space here, and then several whitespace, both become here space. So notice that even if there's leading whitespace or trailing whitespace, they should both be reversed and have the same output. So keep that in mind. Fill out your solution below, take note of the examples, and when you're ready to test your solution, you can run this test cell. All right, that's it. Best of luck on sentence reversal, and I'll see you at the next lecture. Thanks, everyone. Hello, everyone, and welcome to the solution for the sentence reversal problem. For this problem, given a string of words, you had to reverse all the words. So for example, this is the best, turned into best the is this. You also had to take care of all leading and trailing whitespace. If you know Python well, you could have taken advantage of Python's abilities to solve the problem using split and some slicing, or the use of the reversed built-in function. So these are basically one-line solutions to the problem. The issue with these is that even though they are valid solutions, in an interview setting, you'll have to work out the basic algorithm that is used. So in this case, what we want to do is actually loop over the text and extract words from the string themselves. Then we can push the words to a stack, and in the end, put them all in reverse. So let's go ahead and see what this actually looks like. Again, while these are valid solutions, you probably shouldn't do them in an interview setting. You can go ahead and make your interviewer aware that you know how to do this, but it's kind of cheating using Python's abilities. What you really want to do is manually do the splits on the spaces yourself and reverse everything. So what we're going to do is go ahead and do this. So let's go ahead and jump to the solution and explain as we go along. So we'll start by having rev_word function taking a string s. Then we're going to go ahead and start off by making a list called words, a variable called length, which is just going to be the length of the string, and then a list called spaces, which is just going to consist of an empty string, just a space of a string there. And we'll see why we use that in a second. Finally, I'm going to make a variable called I equals 0, and that's just going to be an index tracker because we're going to be using a while loop to solve this. So I'm going to say while I is less than length, if s of I is not in spaces, and there's a variety of ways you can do this. You could have also, is not in spaces, meaning if that element in that list isn't a space, you could have also just said double equal sign to that. And you could have also have managed to do this as some sort of for loop, but we're just doing it in these general terms in case you want to switch languages. We're going to say if the element isn't a space, then the word starts at that index. So I'm going to say word start equals I. And then while I is less than the length and s of I is not in spaces, meaning we haven't hit a space yet, what we're going to do is try to get the index where the word ends. So in that case, what I'm going to do is add 1 to I, and then outside of that, I'm going to say words dot append, and I'm going to append from word start all the way to that index we got off. And then I'm going to say, line it up with that if that I'm going to add to that index. Then finally what I have are all the reversed words. So in this case, I'm just going to return my reversed words joined up. Okay. Let's go ahead and test this solution so we make sure it works. I'm going to go ahead and copy some statements. So for instance, if we do this, hello John, how are you? Note the white space, we got an error, so what's the problem? Note space is not defined. So if we go to that line in spaces, we'll do this right here. And now we have you are how John hello. Okay, great. So we know it's working. Let's do one more example to make sure we don't have any more errors. Space before, this should return before space. Before space. Okay, great. So let's go ahead and go over this solution. What are we doing here? We're setting words as an empty list. Length is just the marker of that length of that list. Spaces is just equal to a list with a white space in it as the first element. Then I is equal to 0. So we're saying while I is less than length, so while we haven't gone through out the entire string, basically, if s of I is not in spaces, meaning if s of I is not equal to this, then we know the word start, the start of that word, is at that index. So then, while I is less than length, and si is not in space, which basically means keep going until we haven't hit another space, add 1 to the index. Then, once that while loop has completed, we're going to append to that words list from the word start index all the way to that new I, basically once we hit that. Then, we add 1 to the index and keep going until I is less than, until this is no longer true, until I is no longer less than length. After that, we just join that list together with the reversed words, spaces in between, just one space. So if you wanted to further develop this solution so it's completely manual, you can also create your own reversal function here. That's pretty easy, so I'll leave that as an exercise to you to go ahead and figure out. So if you want, we can just say return words here, and let's see what we get here. So now we have a list of words in order. So go ahead and write your own function. So I'll say def final output that takes in that words list. And what I want you to do as kind of your homework assignment is fill this in so that the list comes out as a reversed string. Alright, so go ahead and practice manually reversing this list into a string so that becomes something like this. But the point of this section here is to figure out how to use while loops in succession in order to mark word starts and word endings. There's lots of different ways you could have solved this problem, so don't worry if your solution wasn't exactly like this. There's plenty of ways you can do it. You can do it using for loops, so don't worry about that. Again, just make sure you understand how to do this solution, and as long as your solution works, you should be fine. Alright everyone, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called string compression. So here's the problem statement. Given a string in the form such as this, so multiple letters, compress it so that it becomes in this form. So you have the letter and then the count of how many times it occurred. For this problem, you can falsely compress strings of single or double letters. So for instance, it's okay for AAB to return A2B1, even though this is technically more space. So the function should also be case sensitive, so that the string AAA, lowercase aaa, returns capital A3 and lowercase a3. So fill out your solution below, and then run this test cell to test your solution. Okay, that's it for the string compression. Again, it's okay to do false compressions such as this. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the solution for the string compression interview problem. So the problem was this. Given a string in the form, such as this, a bunch of letters, you need to compress it to become this, the letter and then the number of times it occurred. For this problem, you could have falsely compressed strings of single or double letters. So for instance, a string AAB, it's okay if it returns A2, B1, even though this technically takes more space with 4 elements instead of 3 elements in that string. The function should also be case sensitive, so that 3 capital A, 3 lowercase a returns this, A capital A3, lowercase a3. Okay, so let's think about the solution. Since Python strings are immutable, we'll need to work off of a list of characters, and at the end, convert that list back into a string with a join statement. The solution below, the one we're going to go through, should yield us with time and space complexity of order n, where n is the number of elements in that string. So let's go ahead and take a look. Pay careful attention to the comments here if you're just going to go through the notebook, but we're going to actually code this out and explain what we're doing along the way. So let's go ahead and begin. We're going to start by creating our compress function, and it takes in a string s. The solution is actually known as compressing without checking, and it's called the run length compression algorithm. So this one actually has a name already. We're going to begin a run as an empty string. So I'm going to make a variable called r for our run and compare it or set it equal to an empty string. I'm going to make a variable called l and set it equal to the length of our string. And let's go ahead and do 2 edge cases. First edge case is if we have a length 0 string. Second edge case is for a length 1. So I'm going to say if l is equal to 0, then just return an empty string. If L is equal to length 1, then return the string, which is going to be just one letter, plus the number 1. So for instance, if our string was just a single letter A, we would return A1. So again, we're not actually compressing in that case, but this is just okay since we're just doing a run length. Now let's do the meat of the algorithm. So in order to do that, I actually need to initialize some values. I'm going to make a value called last and set it equal to the first element of the string. Then I'm going to make a value called CNT, which stands for count. That's also going to be equal to 1. And then I, which is going to be an index marker, I'm going to set that equal to 1 as well. So I'm going to say while I is less than L, the length of that list, what I'm going to do is say if S of I, so the element at that index of the string, if it's equal to the one that came before it, so what this basically means is if the letter I is equal to the letter before it, let's go ahead and add a count. So I'll add it to that count. Else, that means they're no longer in continuous series, so we're just going to store the previous data. I'm going to say R is now equal to R plus S at I minus 1 plus the count. But we'll need to convert this into a string, since we're just putting this string together as the run. Once we've done that, we'll just go ahead and add to the index to continue on throughout the entire string until we've terminated that while loop. After that, we're just going to put everything back into run. So I'm going to say R is then equal to R plus at the previous plus str cnt. And then I'm going to return R. So let's go ahead and see if this works. Okay, we'll go ahead and run compress. Let's put a string AAB, see what we output. A2, B2. So we have an error here. What's going on? The reason for that error is because we need to reset the count after we've redefined R. So I need to put in CNT here equal to 1. And now if we run it, you'll notice we get the correct result, A2, B1. Let's try it on some more examples. Here I have 4 C's, so I should get A2, B1, C4. We have A2, B1, C4. If I pass it on AAB, A2, B1, we're still good there. Let's see if it does lowercase. Good. Capital A, lowercase a, too. All right, so that's it. Let's go ahead and go over this run length compression algorithm one more time. So what are we doing here? We're just setting this run equal to an empty string, L equal to a length of S, checking our edge cases, initializing some variables. In this case, sometimes people use last as a marker. We didn't actually use it, but just keep that in mind. Some people tend to use that. We'll also put in a while loop. So what's the while loop doing? This is the heart of the algorithm. We're saying while this index is less than the length of the string, if the string at that index is equal to the index before it, so that means if that element is equal to the element before it, we go ahead and add a count. Otherwise, we build out this section of the run, which is going to be R. In this case, if you look at what we set R equal to, an empty string. So on the first run, that's just an empty string plus that very last previous element plus the string of the count. So all these counts added together, convert it to a string, and then we reset the count. Once we did that, we went ahead and added 1 to the I, and then we're back at the while loop until we're no longer less than the length of the string. And then finally, we add all the R's together in the same fashion we did it up here. Then we just return that run. Okay, that's it for this solution. Go ahead and go over the full notebook if you want every step explained as a comment, but that's basically it. All right, thanks everyone, and I'll see you at the next. Hello everyone, and welcome to your next interview problem. This one's called unique characters in a string. So simply given a string, determine if it's comprised of all unique characters. So for example, the string A, B, C, D, E has all unique characters and should return true. The string A, B, C, D, E contains duplicate characters, these two A's, and should return false. So go ahead and fill out your solution below, and then you can test your solution by running this test cell. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the solution of the unique characters in a string. So the problem statement was if you were given a string, determine if it's comprised of all unique characters. So for instance, the string A, B, C, D, E would be true because it has all unique characters. Alright, so we're going to show two possible solutions. One using a built-in data structure and a built-in function, and another using a built-in data structure but creating our own lookup method to check if the characters are unique. So the first one, which is basically a simple one-liner, uses advantage of Python and advantage of the set data type, or data structure, I should say. And we're basically just going to say return, and we're going to say if the length of the set of the string is equal to the length, of the string itself, then we know it has all unique characters. So let's go ahead and try that out. A, B, C, D, E. So we know that's true, and if we add another A, we get false. So that makes sense, since we're basically taking the set, so that's grabbing everything that's unique, check the length of it, and if that's equal to the length of the original string, then you know you had all unique characters. So in an interview setting, usually for these type of solutions, you want to make your interviewer aware that you're able to do it and you know about it, but you also want to manually do as much as possible. So let's go ahead and again use a built-in data type, set, but then use our own lookup method. So we'll call this unichar2 with a string. So what we're going to do is create a set called char, standing for characters, and say set. So I'm going to say for let for letter, basically, in S in that string, if the let is in characters, and let me go ahead and rename this plural so we know there's going to be more than one there. So if let is in characters, return false. else we're just going to add it to the set. Zoom down a little bit, char add let. So if it never returns false throughout that if statement, then we know we can just return true, since all the characters were unique. All right, let's go ahead and walk through this one more time. So we have our set here, characters, and then we're going throughout every element, basically every letter in that string, and saying if that letter was in the set, then return false. Else, add the letter to that set. And what this is basically doing is essentially the same thing as checking if it already exists in the set. So imagine we're going along for this simple example. All the letters A, B, C, D, E wouldn't trigger this if statement. Instead, they would just be added to that set. But on this final letter, A, it would have been already in that character set, so it would have returned false. If this never gets triggered, then we know all the characters are unique, and we can just return true. Alright, so hopefully both of those solutions make sense to you. Again, make sure you do them manually on pen and paper, or practice on a whiteboard when coding them out. And that's it. You can go ahead and check out the solution notebook in case you want more notes on this, but that's essentially all there is to this problem. We might see it again in the mock interview section, so just a heads up. Okay everyone, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the Stacks, Queues, and Deques section of this course. So in this section of the course, we're going to be learning about three main linear structures, stack, queues, and Deques. And they're similar to arrays, but each of these structures differs by how it adds and removes items. So that's going to be the key difference between all of these linear structures. In this section, as far as the theory portions, we're going to have a brief overview of what linear structures are, then an overview of stacks. We're going to have an implementation of a stack class, and then we're going to do the same thing for queues and Deques, both an overview and then implementation of both of them. Okay. With that being said, let's go ahead and get started. In the next lecture, we're going to go have an overview of stacks, theory, and how they work. Alright, thanks everyone. I'll see you at the next lecture. Hello everyone, and welcome to the Stacks Overview lecture. So what is a stack? A stack is an ordered collection of items where the addition of new items and the removal of existing items always takes place at the same end. So this end, where the addition and removal is taking place, is commonly referred to as the top. And then the end opposite to the top is known as the base of that stack. So you can almost think of a stack as a stack of books on a table. So the base of a stack is significant since items stored in the stack that are closer to the base represent those that have been in the stack the longest. And the most recently added item is the one that is in the position to be removed first. So this is known as a last in, first out principle, this stack ordering, sometimes called LIFO. So it provides an ordering based on the length of time in the collection, where newer items are near the top and older items are near the base. Let's go ahead and see a diagram to show this. So here we have an example of building a stack and then removing items from a stack. So in this first figure here, section 1, we can see that we start with a element 1, and then we push a new element 2 to the top of the stack. Then 3 also goes to the top of the stack, and same with 4, 5, and 6. So we're pushing them to the top of the stack, but basically almost like you had a stack of books on a table, and you were piling them on top of each other. Push is just a term that's commonly used for this method or operation, and we'll see that when we implement a stack in the next lecture. Now when you're removing items from a stack, the last in is the first out to go. So for instance, 6 was the last one to go in, so it's going to be the first one to come out. So when you're popping the items off, you're basically taking them off from the very top of that stack. Okay, so note how those first items are being pushed to the stack begin at the base, and as the items are popped out. Stacks are fundamentally important as they can be used to reverse the order of items. And the order of insertion is the reverse of the order of removal. So if we go back, we'll notice that we'd be able to reverse this entire stack by merely popping it out. So right now I have 1, 2, 3, 4, 5, 6 as I push them in. But if I decided to pop these out into a new stack, that would basically reverse the order, have 6, 5, 4, 3, 2, and then 1 finally. So just keep that in mind. Considering this reversal property, you can perhaps think of examples of stacks that occur as you use your own computer. So for example, every web browser has a back button. And as you navigate from web page to web page, those pages are placed on a stack. Actually, it's the URLs that are going onto that stack. So the current page that you're viewing is on the top, and the first page you looked at is at the base. So if you click the back button, you begin to move in reverse order through the pages. Okay, so hopefully stacks was pretty basic and you understood the concept. Go ahead and go over that figure or even go over the Wikipedia page on stacks in case you're having any trouble understanding. But it's basically a last in, first out principle. To get a better idea of this, we're going to go ahead and implement our own stack class in the next lecture. Okay, thanks everyone. I'll see you at the next lecture. Hello everyone, and welcome to the implementation of a stack lecture. In this lecture, we're going to be implementing our own stack class. As always, there's a Jupyter notebook with notes and the full code for you to check out, as well as some examples of using our own stack class. So before we begin on implementing this, what we want to do is just do a quick review of the properties and methods of a stack that we're going to be implementing. So just a reminder from the last lecture, the stack data type is defined by being structured in a way that their last in elements are also the first ones out. So it's an ordered collection of items where items are added to and removed from the end called the top. So what we're going to do is create our stack class with the following operations. First one is just going to be stack, which creates a new stack that is empty. It's not going to need any parameters, and it's just going to return an empty stack. The next one is going to be push. That's going to add a new item to the top of the stack. It needs the item and then just returns nothing. Pop is going to remove the top item from the stack. It doesn't need any parameters, and it will just return the item. The stack is then modified. Peek returns the top item from the stack, but doesn't actually remove it. It doesn't need any parameters, and note the stack isn't modified. So it'll show you the top item, but it won't remove it. IsEmpty is going to test to see whether the stack is empty. It won't need any parameters, and will return a Boolean value, either true or false, depending if it's empty or not. And then finally, size will return the number of items on the stack. It won't need any parameters, and it's just going to return an integer, depending on the size of the stack. So let's go ahead and jump over to a Jupyter notebook and start implementing this. Let's go ahead and zoom in a bit so you can get a better view. Okay, first thing we're going to do is create our class. Let's go ahead and make a stack object. Okay, let's go ahead and start off by just calling self, and we'll say self.items is equal to an empty list. So we're going to be using the list as kind of a base off of this stack. So self.items, we have an empty list. So there's no items in the list yet. So when we call stack, we're just creating an empty stack. We'll go ahead and make our isEmpty method. Just takes in self, no other parameters. And it's going to return the Boolean self.items equal to empty list. So you notice here we're just returning the Boolean is the items, which when it starts off as just an empty list, is equal to an empty list. If we push more items into the stack, this will not be true, and isEmpty will return false. Okay. Next, let's go ahead and describe how we're going to push items. So I'm going to say self, and then take in an item, and that's just going to be self.items, that list, and I'm going to append to that list. I'm going to append that item to that list. Next, I want to see if I can pop items from the list. In that case, we actually don't need any parameters. We're just going to take the last one in is the first one out. So we're going to just use the list built-in method of popping. So self.items.pop. You'll notice that a list behaves very much like a stack in general. And then let's go ahead and create peek, which is going to be the top item but we're actually not going to pop it out. We're just going to return what it is without affecting the actual stack. So in order to do that, I'm going to go ahead and use some slicing. So I have my self.items, which is that list of all the items in the stack. And then I'm going to say from length of self.items -1. Return that. So that's going to return that top item, the last one that was put in. Go ahead and check out the slicing for yourself and this indexing to make sure it makes sense to you. But basically it's just the length -1 because indexing starts at 0. Okay. And then lastly, we're going to make a size method, and that's just going to return the length of self.items. Okay, so that's it. Let's go ahead and try it out. I'm going to create a stack called S. Let's zoom in one more time here so we can really see what's going on. And let's go ahead and print S is empty and confirm that that's true. So it is true. Note how I have the closed parentheses since I'm actually calling the method and not passing any parameters. So it is empty right now. Let's go ahead and push an item to the top of it. So now we have push, and let's go ahead and push another item. In this case, we'll do a string 2. And let's take a peek at our stack. Notice it shows us 2. Let's go ahead and push in another item. We'll push in a boolean this time, true. And how about we check the size of our stack? So we should have 3 items, which makes sense. The integer 1, the string 2, and then that boolean true. So let's check if it's empty now. It shouldn't be, but let's make sure our function or our method is working. Is empty? False. So it looks like that's working well. Let's go ahead and pop out all the items and see if we can empty out this stack. So I'm going to pop out item, so that's going to be that boolean we put in. If we pop in another one, think for a second what it should be. Should be that string. There it is. And then finally, we should pop out that integer. So let's go check if it's empty now. And it is empty. Okay, great. So we took a big advantage of the similarities between a list in Python and its built-in properties and how it relates to a stack. So just keep that in mind. But this is a pretty basic implementation of a stack. Best thing to know about this is that last in, first out principle that stacks have. Okay, with that being said, go ahead and follow along with the code either here or in the example notebook. Make sure you understand how to implement a stack, and that's it. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Queue Overview lecture. So we've learned about stacks and we've implemented our own stack class, so let's go ahead and now learn about queues. So as I mentioned, we'll get an overview of what queue is in this lecture, and in the next lecture we're going to implement our own queue class. So a queue is an ordered collection of items where the addition of new items happens at one end, called the rear, and the removal of existing items occurs at the other end, which is called the front. As an element enters a queue, it starts at the rear and makes its way towards the front, waiting until that time when it is the next element to be removed. So, the most recently added item in the queue must wait at the end of the collection. The item that has been in the collection the longest is at the front. So this ordering principle is sometimes called first in, first out, or FIFO, FIFO, or FIFO, depending how you want to pronounce it. It's also known sometimes as first come, first served. So the simplest example of a queue is the typical line that we all participate from time to time. So we can wait in line for a movie or a checkout line at a grocery store or a cafeteria. The first person in that line is also the first person to get serviced or helped. So that's the parallel and why the naming scheme is queue in this case. So first in is first out. So, for example, in this figure, we have 2 new terms here, NQ or on queue, and then DQ or day queue, depending how you pronounce it. So we have the back and the front of the queue. So, on queue term describes when we add a new item to that rear of the queue, and the DQ term describes removing the front item from the queue. So when we're thinking about how this relates to the push and pop methods that we saw in that stack implementation, in this case, as we push items into the queue, they're the first in. But as we pop them out, those first in items are also the first to come out. So you can see how this is different than a stack. So remember, stack was last in, first out. In this case, we're first in, first out. So keep that in mind. So you should now have a basic understanding of what a queue is and that first in, first out principle for them. In the next lecture, we're going to actually implement our own queue class. Okay, so go ahead and review this lecture in case anything was unclear to you. There's also a Jupyter notebook that goes along with this lecture, so you can check it out as well. And you can check out the resource for the PowerPoint that we went over in this lecture. All right, thanks everyone, and I'll see you at the next lecture where we're going to implement our own queue class. Hello everyone, and welcome to the implementation of a queue lecture. In this lecture, we're going to build on our previous understanding of queues by implementing our own class of queue. Before we begin implementing our own queue, let's go ahead and review the attributes and methods that this queue class will have. So we're going to have 5 basic methods and attributes. The first one, which is just the queue class, is going to create a new queue that is empty. It won't need any parameters, and it's just going to return an empty queue. The onQueue will take in a new item and put it to the rear of the queue. So it's going to need that item parameter, but it's not going to return anything. It's just going to affect the queue. The Deques item removes the front item from the queue. It won't need any parameters, and it'll just return the item that it dequeued. The queue is then modified. IsEmpty is going to test to see whether the queue is empty or not. That won't need any parameters, and will just return a Boolean value, true or false, depending on whether the queue is empty or not. Then the size method will return the number of items in the queue. It won't need any parameters, and it's just going to return an integer. Okay, so those are the basic 5 methods and attributes we're going to do. So let's go ahead and jump to the code. Okay, so here we are at the Jupyter notebook, so let's go ahead and code this out. We'll first just start by creating our class. And what we're going to do is go ahead and instantiate our class. Just going to take in self. And we'll do the same thing we did for the stat class. We'll just have items equal to an empty list at first. So far we just have an empty queue. Let's go ahead and create our isEmpty. That's going to be the same as what we did for the stack. We're just going to return the Boolean check if that items attribute is equal to an empty list. Then, next up is going to be onQueue or enqueue. So what we're going to do here is say onQueue, takes in self, and then that item. So remember, we're doing a first in, first out principle, just like a regular queue or line as you wait at a cashier or something. So in order to implement this, what we're going to do is take advantage of the insert method that a list can have. And it's going to take 2 arguments. One is the index you want to insert it at, and the other one is the element or item you want to insert. So we're going to have it inserted at index 0, and we're going to put in an item. So as we keep inserting items, we basically push the rest of them up. And then for dequeuing, what we're going to do is not take any arguments there, and we're just going to go ahead and pop off that item. And then finally, for checking the size, what we're going to do is just return the length of self.items. And let's go ahead and make that into the size method. Sorry, I wrote that in a bit of a weird order. Okay, so I ran that. Let's go ahead and mess around with it and make sure everything's working. So we'll create a variable q, which stands for q. Let's go ahead and just check right off the bat what its size is. And let's make sure that it's empty. Okay, so that's looking good so far. Let's go ahead and add an item to it. We'll add 1, and we'll add another item. In this case, we'll say 2. So now what you should be asking yourself is, if I call Deques, what item should I expect to come out? Well, remember, it's first in, first out principle here. So I should expect the first item I put in, 1. If this was a stack, we would have gotten 2 out. Okay, so go ahead and play around with this. Make sure you understand basically the first in, first out principles here that we've done in our own queue class. And make sure you're actually able to implement this on your own. Okay, with that being said, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Deques overview lecture. So, we've gotten overviews on stacks and queues, and we've also done our own implementations of stack and queue classes. So, now let's learn about Deques linear data structure. A deque, also known as a double-ended queue, is an ordered collection of items similar to the queue. It has 2 ends, a front and a rear, and the items remain positioned in the collection. What makes a deque different is the unrestricted nature of adding and removing items. New items can be added at either the front or the rear, so that's a huge difference between a deque and a queue or a stack. We can add items either to the front or the rear of the deque. Likewise, existing items can be removed from either end. So in a sense, this hybrid linear structure provides all the capabilities of stacks and queues in a single data structure. It's important to note that even though the deque can assume many of the characteristics of stacks and queues, it does not require the last in, first out, and first in, first out orderings that are enforced by those data structures. So it's completely up to you to make consistent use of the addition and removal operations. Okay, so let's go ahead and see a diagram of this. So here's just a really simple diagram of what a deque looks like. You'll notice it looks similar to a queue, but in this case, we can add and remove items from either end, either the front or the back. So that's a pretty big difference. So let's learn how to implement a deque in the next lecture. Okay, so I'll see you at the next lecture. Remember that a deque, as just a review, the main difference is that you can add items from either end and remove items from either end. So let's go see how we can implement that. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the Deques overview lecture. So, we've gotten overviews on stacks and queues, and we've also done our own implementations of stack and queue classes. So, now let's learn about Deques linear data structure. A deque, also known as a double-ended queue, is an ordered collection of items similar to the queue. It has 2 ends, a front and a rear, and the items remain positioned in the collection. What makes a deque different is the unrestricted nature of adding and removing items. New items can be added at either the front or the rear, so that's a huge difference between a deque and a queue or a stack. We can add items either to the front or the rear of the deque. Likewise, existing items can be removed from either end. So in a sense, this hybrid linear structure provides all the capabilities of stacks and queues in a single data structure. It's important to note that even though the deque can assume many of the characteristics of stacks and queues, it does not require the last in, first out, and first in, first out orderings that are enforced by those data structures. So it's completely up to you to make consistent use of the addition and removal operations. Okay, so let's go ahead and see a diagram of this. So here's just a really simple diagram of what a deque looks like. You'll notice it looks similar to a queue, but in this case, we can add and remove items from either end, either the front or the back. So that's a pretty big difference. So let's learn how to implement a deque in the next lecture. Okay, so I'll see you at the next lecture. Remember that a deque, as just a review, the main difference is that you can add items from either end and remove items from either end. So let's go see how we can implement that. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture where we implement a deque. So we're going to implement our own deque class, and just like the other lectures, before we begin, let's go ahead and take a look at the methods and attributes that will be in our class. First off, we're going to have deque. Deque creates a new deque that is empty. It's not going to need any parameters, and it's just going to return an empty deque. Then we're going to have adding and removal methods. So we'll have an add front and an add rear. They'll both add items and take items as parameters, and then either put them to the front or the rear, depending on which method's called, and it will return nothing. Then we're going to have remove front and remove rear. These methods are going to remove items either from the front or the rear of the deck. They won't need any parameters, and they're going to return an item. The deck will then be modified. Then we have isEmpty to test to see whether the deck is empty or not. It won't need any parameters and will return a Boolean value, true or false, depending if the deck is empty or not. Then we have size, which just returns the number of items in the deck. It won't need any parameters, and it's just going to return an integer. So, as always, if you go to the Jupyter Notebooks, you'll have an implementation of Deck Notebook, which is what I'm looking at here, as well as the code that we're going to explain and code out right now. So let's go ahead and hop over to the Jupyter Notebook and code this out. Alright, so let's go ahead and get started. So we have our class, deck. I'll go ahead and pass in object. This is going to be an object. And I'm just going to basically initiate this class. Again, just like we've been doing for stacks and queues, we're going to have the items be defined by a list. Then we'll create our isEmpty method. That just takes in self. And that's going to return self.items is equal to an empty list. So that's similar to the same method we used for stacks and queues. It's just checking if the items is an empty list, and if that's true, it'll return a true Boolean. Otherwise, it'll return false. Okay, here's the next method, add front. So we're going to take in an item as well as self. And what we're going to do is just append that item. So remember, append, when you have a list, we'll put it at the very end. In this case, we'll call that the front of our deck. For the add rear method, what we want to do is, again, take an item, say self.items, and in this case, we're going to insert at the 0 index that item. So this will allow us to add that item at the rear. Then let's go ahead and remove those items. So we'll make two removal methods, a remove front and a remove rear. Let's go ahead and zoom in on it just so we can really see it. For remove front, we're going just to take in self, and we will return self.items.pop. And then for remove rear, what we're going to do is take in self, and we will return self.items. But in this case, we're going to pop at the 0th index. Okay. And then just for the last method, which is size, we're just going to return the length of that items list, which will be self.items. All right, let's go ahead and play around with this and make sure it all makes sense. So we'll create a variable d and create an instance of our deck class that we just made. We'll add to the front of it, we'll say hello, just a string hello, and then we'll add to the rear of it another string world. So our hello world strings. Let's go ahead and check the size. It should be 2. All right, that's looking good. And now let's go ahead and make sure that the ordering makes sense to us. So what we're going to do is print d-remove front plus a space string, and then we're going to say d-remove rear. And just a reminder, I'm just doing tab there to get that fill out or that autocomplete. And if I run this, I get hello world. So I removed both the front and the rear. Let's go ahead and check the size now. It's 0, which means if I call isEmpty, I should get a true Boolean. All right, that's it for the deck. So you can kind of see how this was a mix between the stack and the queue classes, especially since the adding front and rear, and the removal front and rear methods looked really similar to almost like a combination of both stacks and queues. Again, the main thing to be aware of is that you're going to have to be careful as far as keeping these in order if you decide to use your own deck creation, especially in an interview setting where you may be asked tricky questions on adding and removing items to really test your understanding of a deck. Okay, that's it for the lectures. Up next are the interview questions of the course. So I'll see you at the next lecture, and thank you everyone. Hello everyone, and welcome to the Stacks, Queues, and Deques interview problems section of this course. Before we begin with the actual interview problems and solutions, let me just give you a quick reminder of where you can find both the interview notebooks and the solution notebooks. Let's go ahead and jump to the NB Viewer link. So, here at the NB Viewer link, you'll see the Stacks, Queues, and Deques section of the course. You can go ahead and click here for interview problems. That will load up two folders, Stacks, Queues, and Deques interview questions, and then the solutions folder. So if you go ahead and click on the interview questions, you'll notice that some of the questions are just implement a deck, queue, and stack. Those are actually going to be the first three questions we face. That's just going to be implementing a deck and a queue and a stack, just exactly what that line is. So we'll go ahead and cover those in a little more detail, but there's two other questions that are more typical interview problem questions, not just a simple implementation. Alright, with that being said, let's go ahead and start with the interview problems. I'll see you at the next lecture. Hello everyone, and welcome to your first interview question for this section of the course. Your first interview question is just a common interview question, and that question is just implement a stack. So you're going to have to try your best to implement your own stack class object. So it should be able to do the following methods. Check if it's empty, push a new item to the stack, pop an item to the stack, take a peek at that top item, and then return the size of the stack. Keep in mind how a stack works while you work through your way in your implementation. Try not to look at the implementation lecture until you've given it a fair shot on your own. Alright, there won't be a solution lecture associated with this because we already did an implementation of a stack earlier. Go ahead and check that previous lecture if you want the solution to this one. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. So for this interview task, you've been asked to implement a queue. It's a pretty common interview problem, just like implementing a stack or implementing a deck. So in this case, implement a queue class. The class should be able to do the following. Check if the queue is empty, do an onQueue or enqueue, do a dequeue, and then return the size of the queue. Review the theory lecture if you don't remember what these two terms mean, but don't take a look at the implementation of a queue lecture until you've tried doing this on your own from memory. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem for the Stacks, Queues, and Deques section of the course. This interview problem is to simply implement a deck class. Your deck class should be able to do the following. Check if it's empty, add to both the front and the rear of the deck, remove from the front and the rear of the deck, and check the size of the deck. Okay, with that being said, there's no solution lecture associated with this particular problem because we already have an implementation of deck lecture. So after trying this out on your own, you can go ahead and review the implementation of a deck notebook and lecture to get your solution to this problem. With that being said, make sure you try out your own solution beforehand. Don't take a peek at the solution before trying it on your own from memory. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called balance parentheses check. So here's the problem statement. Given a string of opening and closing parentheses, check whether it's balanced. So we have three general types of these parentheses. Round brackets, which look like just general parentheses here, square brackets, like the ones you use when you index a list, and curly brackets, like the ones you use for a dictionary in Python. So assume that the string doesn't contain any other character besides these 3 types of parentheses, and it won't have any spaces, words, or numbers. As a reminder, balanced parentheses require every opening parentheses to be closed in the reverse order opened. So for example, if we just zoom in here, you'll see I have a open parentheses, an open square bracket, then a closed square bracket, and a closing parentheses. So this is balanced. But however, this one right here, open parentheses, open square bracket, and then a closed parentheses before you close that square bracket is not balanced. So you can assume that the input string has no spaces. Alright, so you can go ahead and fill out your solution below. You'll be given a string. So for example here, we check if this is a balanced checked, we check here if we have a balanced parentheses using the function balance check. This is truly balanced. This one, if you look at it, it's balanced as well. This one is not balanced. You can see the error here. We're missing a square bracket. Alright, you can run this test cell right here to test your solution with the various cases of brackets as strings. Alright, best of luck, and I'll see you at the next lecture, where we're going to be going over the solution for this problem. Thanks everyone. Hello everyone, and welcome to the solution for the balanced parentheses check interview problem. Just as a reminder, this is a pretty common interview problem, and it's one of the main ways to check your knowledge of stacks. So, what the problem statement was, you were given a string of opening and closing parentheses, and you had to check whether it was balanced. Let's go ahead and go over some logic for our solution. Let me go ahead and zoom in here. So, as I mentioned, this is a common interview problem, and we're going to start our solution logic as such. Starting with this step, first, we're going to scan the string from left to right, and every time we see an opening parentheses, we're going to push it to a stack, because we want the last opening parentheses to be closed first. So remember that first in, last out structure of a stack. And that first in, last out is just another way of saying last in, first out. Okay, so the second step is going to be when we see a closing parentheses, we're going to check whether the last opened one is the corresponding closing match by popping an element from the stack. If it's a valid match, then we can proceed forward. Otherwise, we just return false because we know it's not balanced. So, if the stack is empty, we'll also return false because there's no opening parentheses associated with the closing one. And in the end, we also check whether the stack is empty. If so, we just return true. Otherwise, we return false because there were some open parentheses that were not closed. So that's our basic logic written out. Let's go ahead and code out the solution for this so we can see this implemented in action. Alright, so I'm going to go ahead and fill out that balance check function. It takes in a string. And first thing we're going to do is just a quick edge case check. So we can already check that if there's an even number of brackets, we know we can continue on with the solution. Otherwise, if there's an odd number of brackets, we'll just return false, since that's going to be an impossible string to balance. So I'll say if the length of that string, s, mod 2 is not equal to 0, then I know we have an odd number of parentheses and I can just return false. Keep in mind that we were given the statement that there's no spaces or words or elements besides parentheses here. Otherwise, you wouldn't be able to do such an easy check. Next thing we're going to do is create a set of opening brackets. So I'm going to create a variable called opening, and I'll make a set, and I can pass in a string to this set, and I just want the opening brackets. You'll notice that Jupyter Notebooks and IPython in general will auto-generate the closed brackets. Don't worry about that right now. So just to show you what this line is actually doing, I'm just going to actually run it here so you can see. It's basically a nice quick way of creating a set of these brackets individually. So it's taking each element in that string and passing it into the set. Alright, so we have our opening brackets. Let me go ahead and delete this. So we have that opening set of brackets. Let's go ahead and make a set of the matching pairs. So I'm going to make another set. I'll call it matches. And I'm going to pass in a list here of tuples of the matches. So we have 3 types of parentheses, which means I'm going to have 3 tuples. I'm setting them up here so hopefully you can see the logic that we're doing. So let's go ahead and make the first match. That first match would be an opening and a closing parentheses. So note how that's our first tuple here. Let me space this out so it's a little more clear. So that's our first basic tuple set or pair. And next one's going to be the square brackets. So there's the open square bracket and there's the closed square bracket. And then let's go ahead and do the curly one. So curly open and curly closed. Okay, let me go ahead and make sure you guys understand what this is by just running that string, or excuse me, running that line. And you'll notice we have our set, and it's of tuple pairs here. Open, closed, open, closed, open, closed. All right, so that variable is called matches. And what we're going to do is use a list as a stack. So remember when we were implementing our stack, we were basically using all the built-in operations of a list. So that's totally fine in an interview setting. Just make sure your interviewer knows that you realize a Python list can operate the same as a stack in this situation. Maybe as an earlier question, they asked you to implement your own stack, so you might want to keep this in mind. And a good challenge would be to implement your own stack first, and then do this problem with your own implemented stack class. So, continuing on, let's go ahead and check every parentheses in the string. So I'm going to say for paren, short for parentheses, in S, that string we took in. What I want to do is check if it's an opening, I'm going to append it to that list. Basically push it to the stack. So I'm going to say if paren is in opening, meaning it's an opening parentheses, going to take my stack, which was that list, and append that paren. So I'm pushing that parentheses if it's an opening one. Else what I'm going to do is check that there are parentheses in the stack. So if it's not an opening parentheses, it means it's a closing one. So the first thing I'm going to do is I'm going to say if length of stack, put that in there. If length of stack is equal to 0, return false, because I already know there wasn't a matching opening parentheses for that closing parentheses if the length of the stack is already 0. If that's not the case, what I want to do is check that last open parentheses. So I'm going to create a variable, call it last open, and that will be that pop from the stack. Remember our first in, last out, or last in, first out principle. And what I want to do now is check if that has a closing match. So I'll say if last open paren is not in matches, return false. So hopefully now you can see why we did that tuple set here of these pairings, so I can use this sort of notation, last open paren not in matches. There's definitely other ways you could have gone about making this check, but I like this because it's a little cleaner and it makes a nice use of a set as a one line here for checking your matches. Okay, so if none of those ended up returning anything, then I'm just going to do a quick check if the stack is empty. So I'm going to say return length of stack equal to 0. And let me go ahead and zoom out a bit so you can see how the code is laid out. All right, so you can see that this 4 lines up with that return for that check if we've emptied out that stack completely. So let's go ahead and do some balance checks and make sure this all works out and check if we have any errors in our code. Okay, so it looks like this one's true. Makes sense to me. Let's check another balance check. This one should also be true. All right, and now let's check one that we know is false. Great, and we got false. All right, that's all there is to this solution. So let's go ahead and see it one more time and walk through the steps we're doing. So remember, the first thing we're doing is we're just scanning the string from left to right, which is what this for loop is doing. And then every time we see an opening parentheses, we push it to the stack. So we created our opening set of parentheses, and we're saying if paren is in the opening, I'm going to push it to that stack. And in this case, since my stack is just a list, I'm using the append method of that list. All right. We do this because we want the last opening parentheses to be closed first. Then, when we see a closing parentheses, we're going to check whether the last opened one is the corresponding closing match by popping an element from the stack, which is right here in this case. If it's a valid match, then we proceed forward. If not, we're going to return false. Another method or step here is that if the stack is empty, we're also going to return false because there's no opening parentheses associated with that closing one, which is what we did here in this check. So in the end, we'll also check whether the stack is empty right here. If so, we'll end up returning true because that means we've balanced out and matched all the parentheses. Otherwise, we return false because there were some open parentheses that were never closed at the end of going through the entire string. Okay, so go ahead and walk through that solution, make sure you understand it. Go ahead and see if you can implement your own stack class and use it in the same way as we did with our list as a substitute. And if you want, you can go ahead and check out other methods or create your own methods for doing this check right here of the matches with this line. Okay, that's the solution, everyone. Thanks a lot, and I'll see you at the next lecture. Thanks. Hello, everyone, and welcome to your final interview question for the stacks, queues, and Deques portion of this course. So, your question or assignment for this interview problem is this: implement a queue using two stacks. So you're going to be given a stack class below, and what I want you to do is implement a queue class using two stacks. You should also note this is a classic interview problem, so you should really know this one. What I want you to do is use a Python list data structure as your stack. So instead of having to create your own stack class, what I'm going to do is say this list is a stack class. So here's stack 1, it's just an empty list, and here's stack 2, it's an empty list. And so your solution right here, you're given a class, let's go ahead and zoom in on it, called Q2Stacks. And here are your two stacks, those empty lists. I've already set them up as self.stack1, self.stack2. And what I want you to do is fill out these two methods so that you're essentially creating a queue using these two stacks. You can go ahead and test your solution here. What you should be able to do is with your current knowledge of stacks and queues, you should be able to tell if this is working as it should. So for example, the following should print as such here. So for I in X range 5 and I in X range 5, when you're calling on Q and DQ, you should see something that looks like this. So go ahead and run this cell and make sure that your solution output makes sense and behaves as a queue that you've built out of two stacks. If you need a quick reminder on what stacks and queues look like and operate, you can go ahead and check out the theory lectures on them. Try not to check out the actual implementation lectures until you've given your fair shot at this interview problem. Alright, with that being said, I'll see you at the next lecture where we're going to be going over the solution to this problem. Thanks everyone. Hello everyone, and welcome to the solution for implementing a queue using two stacks interview problem. So again, the problem statement was given the stack class below, implement a queue class using two stacks, and you were allowed to use a Python list data structure as your stack. So, what was the solution? Let's go ahead and zoom in a bit. Whoops. So the key insight is that a stack reverses the order, while a queue doesn't when you're pulling stuff out of it. So that was the main key, and we mentioned that when we were going over the stack theory lecture. So always keep that in mind, that as you pull stuff out of a stack, you're reversing the order of which you put them in. So a sequence of elements pushed onto a stack, remember, becomes reversed when you pop them out. So consequently, two stacks chained together will return elements in the same order, since reversed order, reversed again, is original order. So that's why this is such a classic interview problem. It really checks that you understand what both a stack and a queue is. So we use an in stack that we fill when an element is on-queued or n-queued, and the dequeue operation takes elements from an out stack. If the out stack is empty, we pop all elements from the in stack and push them into the out stack. So you were given some filler code. Let me go ahead and zoom out here. Given this class, and then two stacks, and you're supposed to fill in the on-queue or n-queue, and then the dequeue. So what we're going to do is rename these stacks into something that will show the logic a little better. We'll have an in stack and an out stack. Okay. So what we're going to do for on queue, or adding elements into that queue, is say self dot in stack, and we'll append that element. So that's all we have to do for the on queue. We just take the in stack and then append it, basically pushing it onto the top. And then the dequeue is where we have to do that double reversal. So we're going to say if not self.outStack while self.inStack, and this is basically the checks for the empties, what we're going to do is add the elements to the out stack to reverse the order when called. So I'm going to say self.outStack.append, and I'm going to append the popped element from the in stack. And then all I have to do is just return self.outStack.pop. Okay, so this is really the key insight here. These two lines, one for that in stack where you just have to append the element, and the other for that dequeue. So remember that we have a stack that's going to reverse order when a sequence of elements is pushed onto a stack or onto a stack. It's going to come back in reverse order when popped. So that means that two stacks chained together are going to return elements in the same order. Since we're reversing them twice, we just reverse, and that's the original order. So what we're doing is we're using this in stack right here, and we use that in stack when we fill an element. It's n-queued, and the dequeue operation takes elements from that out stack here. So if the out stack is empty, what we're going to do is pop all elements from the in stack right here, and then push them onto the out stack. Okay, so this loop is basically checking the empties for that particular piece of logic. So using that in stack, we fill when an element is on-queued, and then the dequeue operation takes elements from an out stack. If the out stack is empty, we pop all elements from the in stack, which is why we say here while self in stack, and then push them onto the out stack, which is what we're doing in this line. Okay, so go ahead and code out the solution. Make sure you can do this from memory, or at least from your memory of the theory of queues and stacks, because it is a really common interview problem. Alright, thanks everyone, and that's it for the stacks, queues, and Deques lectures and section of the course. What you should have gotten out of this is a full understanding of stacks, queues, and Deques, how to implement each of those, and then how to use their logic for interview problems. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the linked lists section of this course. So, in this section of the course, we'll be going over singly linked lists, then we'll implement a singly linked list using Python. After that, we'll go over doubly linked lists, again, do an implementation of those in Python, and then have the interview problems that are really common when it comes to linked list topics. Okay, so with that being said, let's go ahead and get started. I'll see you at the next lecture. Hello everyone, and welcome to the lecture on singly linked lists. In this lecture, we'll have an overview on singly linked lists, what they are. We'll see some diagrams to explain them. And then more specifically, we'll also go over adding elements to a linked list and removing elements to a singly linked list. Okay, formally, and in a general sense, a singly linked list, in its simplest form, is a collection of nodes that collectively form a linear sequence. Each node stores a reference to an object that is an element of the sequence, as well as a reference to the next node of the list. So if we see this drawn out as just what a single node looks like, we have our element. In this case, we're going to use airport codes as our elements. MSP is the airport code for Minneapolis. And then we have another reference to connecting to another node in our linked list. So we can think of this as a bunch of nodes that are linked together by these pointers. Here we have a more full diagram of a singly linked list. The list instance maintains a member named head that identifies the first node of the list, which is this one right here. Notice how nothing points to the head since it's the first node of that list. In some applications, another member named tail that identifies the last node of the list may be found over at the end. And in this case, this node points to none or nothing, indicating that it's the tail. And remember, each of these nodes, again, it's referencing its own element, in this case, the airport codes. Again, the first and last node of a linked list are known as the head and tail of the list. We can identify the tail as the node having none as its next reference. This process of going throughout the nodes and going through them and checking the linked lists by going through the nodes is commonly known as traversing the linked lists. So just a couple terms to review. We have the head and the tail of the linked list. And if we start going through the nodes and going through the connections of the pointers, that will be known as traversing the linked lists. Because the next reference of a node can be viewed as a link or pointer to another node, that process of traversing a list is sometimes also known as link hopping or pointer hopping. We'll just call it traversing. Each node is represented as a unique object, with that instance storing a reference to its element, in our case, those airport codes, and a reference to the next node, or in the case of the tail, none. So we changed the diagram here just for simplicity's sake, with the reference to the element just being part of the node, instead of writing out that pointer. That way it looks a little cleaner. Now let's talk about inserting an element at the head of a singly linked list. How do we actually go about doing that? An important property of a linked list is that it does not have a predetermined fixed size. It uses space proportionally to its current number of elements. That means to insert a new element at the head of the list, we have to do 4 things. We create a new node, set its element to the new element, set its next link to refer to the current head, then set the list's head to point to the new node. Let's draw this out in a diagram. Okay, we have 3 steps here, 3 diagrams, A, B, and C. A is what our singly linked looks like before we actually do an insertion into it. So we have the head node, Minneapolis, pointing to Atlanta node, pointing to the Boston node, pointing to none. And now we want to insert an element to the head of a singly linked list. So we want to insert LAX here. After we create the new node, what we end up doing is a reassignment of the head reference. So we assign LAX and reference the next node, Minneapolis, and then do a reassignment of the head reference to LAX. Now we want to insert an element at the tail of a singly linked list. We can also easily insert an element at the tail of the list, provided we keep a reference to the tail node. In this case, we create a new node, assign its next reference to none, set the next reference of the tail to point to this new node, then update the tail reference itself to this new node. Let's see what this looks like as a diagram. Here we have 3 figures. This first one, A, is what it looks like before the insertion. So we have Minneapolis as the head, pointing to Atlanta, pointing to the tail Boston, which itself points to none because it's the tail. Then we create a new node here in this figure, and after we do this, we set that new node to reference none. It's important to note that we must set the next link of the tail in this step B before we assign the tail variable to point to the new node in C here. So we set up our new node and then first point it to none before pointing our previous tail to the new tail node. Now let's talk about removing an element from a singly linked list. Removing an element from the head of a singly linked list is essentially the reverse operation of inserting a new element at the head. Here we explain it through some diagrams. This is what our singly linked list looks like before removal. We have LAX, Minneapolis, Atlanta, Boston, with LAX at the head, Boston at the tail. And we basically just link out LAX by pointing the head to Minneapolis, and then we can easily remove that node. We cannot easily delete the last node of a singly linked list, however. Even if we maintain a tail reference directly to the last node of the list, we must be able to access the node before the last node in order to remove the last node. But we cannot reach the node before the tail by following the next links from the tail. If we want to support such an operation efficiently, we will need to make our list a doubly linked list. So we've learned a lot about singly linked lists and how to add and remove elements from them. Up next, we're going to implement a node class and create a singly linked list. As far as the actual topic of linked lists, formally and through diagrams, you might think, hey, this is pretty simple. It's just a bunch of nodes pointing to each other and then pointing to an element. And I think when you see the actual implementation, you'll realize it is just that simple of an idea. The singly linked lists, you have nodes that point to each other. The trick is just doing certain operations on them, such as reversing them or checking a particular node in that list, or removing nodes from the tail of a singly linked list, in which case you have to go to a doubly linked list. Hopefully you can see in our implementation in the next lecture that this is a pretty simple topic and straightforward. The challenge is feeling comfortable enough with it in order to solve the interview problems that we see at the end of this section. Alright, so let's go ahead and jump to the next lecture where we're going to implement our own node class and create a singly linked list. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the singly linked list implementation lecture. In this lecture, we're going to be implementing a basic singly linked list. Remember, in a singly linked list, we have an ordered list of items as individual nodes that have pointers to other nodes. So as always, you have a Jupyter notebook with the code that we're going to go through. It's actually pretty simple in this case. And there's also some more discussion on pros and cons, which we'll get to later after implementing it. So let's go ahead and jump to the live code and implement this singly linked list. First thing I'm going to do is actually just create my node. So I'm going to say class node object, and this is a big part of doing any sort of linked list interview problem or question. Usually you're going to have to implement your own node class and use the different methods and attributes of that node class to further answer the question that's referring to a linked list. In this case, we're just implementing a singly linked list. Meaning, I'm going to take in just one attribute, value. I'll say self.value is equal to that value. So, for example, in the previous lectures, we saw examples of values being pointing to strings referring to airport codes. So we could use that later on. And since this is a singly linked list, I just care about the next node I'm pointing to. I'll leave it as none for right now. Alright, so we have this really basic class of a node, and we're going to use it to build out a linked list as a collection of nodes. I'll say A equals node with a value 1 to keep it simple, then B with a node of value 2, and then C as a node of value 3. Now I want to actually link these nodes together, and to do that I can just say A next node is equal to B. And similarly, I can say B next node is equal to C. And that's all there is to it. So we've already developed our own linked list. So I can go ahead and check out values from it. And I can also check out the nodes that are coming next. Meaning I could say A.next node. And I will actually just get a statement on an object class here. So node where it's being stored. But I could call the value of the next node, and that should get me the value of B, which in this case was 2. So if you run that, we get 2 out. Okay, that's really all there is to it. I hope that this implementation shows you how simple the idea of a linked list is. You just have a node in this case, and for a singly linked list, you just care about that node's value and then the next node that's coming up. You go ahead and create instances of those objects, and then you just assign what the next nodes are. And then you can call their values. As far as pros versus cons, what's nice about linked lists is that they have constant time insertions and deletions in any position. In comparison, arrays will always require linear, or big O-N, time to do the same thing. Linked lists can also continue to expand without having to specify their size ahead of time. So try to remember our lectures on array sizing from the array sequence section of the course, where we talked about amortization and how we kept having to double that array size. Since linked lists are just collections of nodes, we can just keep inserting the nodes. And we don't have to worry about the lectures on dynamic arrays. Some cons to a linked list is to access an element in a linked list, you need to take OK time to go from the head of the list to the kth element. In contrast, arrays always have constant time operations to access elements of an array. These pros and cons are written out for you at the bottom of the singly linked list implementation lecture, and this is probably the main one here, that to access an element in a linked list, you need to take OK time to go from the head of the list to the kth element. In contrast, arrays always have constant time operations to access elements in an array. Definitely the main things to know here are this line of the pros versus this line of the cons. Essentially, if someone asks you in an interview, what are the pros and cons of using a linked list versus an array, you're really going to want to have these answers ready to go. Okay, hopefully the implementation was pretty simple. I know we went over the theory in the previous lecture and it might have seemed a little obscure, but now you can really see how easy it is to just implement a node, set up a value, and set up a next node for a singly linked list. In the next lecture, we'll be discussing doubly linked lists, and after that, we'll actually implement one in Python. And it'll also be pretty simple, but we'll have to add certain attributes and methods to that node class. Okay, that's it, and I'll see you at the next lecture. Thank you, everyone. Hello, everyone, and welcome to the doubly linked lists lecture. In the previous lecture, we implemented using Python nodes and created a singly linked list from those nodes. In this lecture, we'll talk about what doubly linked lists are, and then in the next lecture, we'll go over an implementation in Python of doubly linked lists. So as I mentioned, we're going to have an overview, and we're also going to focus on some specific topics that occur in a doubly linked list, known as header and trailer sentinels. Okay, so what is a doubly linked list? In a doubly linked list, we define a linked list in which each node keeps an explicit reference to the node before it and a reference to the node after it. These lists allow a greater variety of constant time update operations. This includes insertions and deletions. We continue to use the term next for the reference to the node that follows another. We'll have a new term, however, called previous, or PREV for short, for the reference to the node that precedes it. Okay, so we add special nodes at both the ends of the list, so that header and that trailer. A header node at the beginning of the list and a trailer node at the end of the list. You can check the diagram here. Note how this looks similar to that singly linked list, except now we're referencing previous lists as well, not just what comes next, but what was previous. These dummy nodes are known as the sentinels, or guards. So we have this header list, this header node, this header sentinel, and this trailer node, or trailer sentinel. Every insertion into our doubly linked lists representation will take place between a pair of existing nodes. When a new element is inserted at the front of the sequence, we simply add the new node between the header and the node that is currently after the header. So for instance, let's go ahead and take a look at what inserting and deleting would look like in a doubly linked list. Here in figure A at the top, we have our header sentinel, or trailer sentinel, and then 3 nodes. And note how they all point, at least all the nodes in the middle, point to a previous node and a next node. If we want to insert a new node, what we can do is just change the header or the next pointer and the previous pointer to accommodate the new node. So the steps are A, what it looks like before the operation, B, after creating this new node, and then C, after linking the neighbors to the new node, pointing the next and the previous to the corresponding nodes. Now imagine we wanted to insert a node to the front. What would this look like? It's actually a pretty similar process. This is what it looks like before the operation. After we create a new node, and then we just relink the header sentinel to that new node, as also the new node then points previous to the header node. And the similar situation happens to the node that it just replaced. The node that used to be at the front, right next to the header. Now let's talk about deleting a node. The 2 neighbors of the node to be deleted are linked directly to each other. As a result, that node will no longer be considered part of the list and it can be reclaimed by the system. Because of sentinels, the same implementation can be used when deleting the first or last element of a sequence. For example, here we have 3 figures. A is what it looks like before we actually delete a node. And if we want to delete a node, we just link the old node. So in this instance, we're linking out PVD. So we point JFK to SFO, and then that node, we say the previous node is actually JFK, no longer PVD. So all you have to do is just link out old nodes. Okay, so we learned about doubly linked list nodes, how they point to both what's coming up next and what came up previously. We learned about insertion and deletion. And now next we're going to implement a doubly linked list using node classes in Python. Okay, thanks everyone, and this will make a lot more sense when you actually see it coded out in the next lecture. I'll see you there. Hello everyone, and welcome to the lecture on doubly linked list implementation. In this lecture, as you might have guessed, we're just going to implement a doubly linked list in Python. As always, you have all the sample code in the corresponding Jupyter notebook. This one's called doubly linked list implementation. Let's go ahead and get started. First thing we're going to do is just go ahead and create our node class. I'm going to go ahead and call this class doubly linked list node. In an actual interview setting, you would probably just call this a node class. And then let's go ahead and initialize the attributes we're going to be using. That's going to be self, and then the value of that node. First thing we're going to say is just self.value equals value. Just like the previous singly linked list node implementation, we have a next node. We'll have a default to none. But now, since we're doing a doubly linked list node, we have the previous node reference as well. And that's going to be equal to none. All right. That's all there is to it, so let's go ahead and build out our linked list now that we have a node that can reference both next and previous values. We'll say A equals doubly linked list node, and I'm just putting tab as a reminder. So if I just do do and then click tab, it should autocomplete for me. That way to save myself some typing. So we have 1, 2, 3 as the values, and then A, B, C are the actual nodes themselves. Now let's go ahead and define the doubly linked list. I'll do this by saying A.nextNode is equal to B, meaning B.previous node is equal to A. So that's setting B after A, and now I'm going to set C after A. So I'm going to say B dot next node equals C, and then C dot previous node equals B. And that's all there is to it. Now we have a doubly linked list that allows us to go through our linked list both forwards and backwards through this previous node. One more quick note is that you could have also created, using this node class, a circularly linked list, meaning just that this final node, next node reference would be A. So you would just have a loop, A, B, C, going around to each other. That's also an option for you to do. It has its own use cases, so just keep that in mind. But in this case, we have our header, A, and our trailer, C, for our doubly linked list. Okay, that's all there is to it. Hopefully this was pretty straightforward and basic for you, especially after implementing the singly linked list. Coming up next, we'll discuss more about linked lists and how to approach interview problems for linked lists. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your first linked list interview problem. This one's called Singly Linked List Cycle Check. Here's the problem statement. Given a singly linked list, write a function which takes in the first node in a singly linked list and returns a boolean indicating if the linked list contains what's known as a cycle. A cycle is when a node's next point actually points back to a previous node in the list. This is also sometimes known as a circularly linked list. I mentioned this topic when we were implementing the doubly linked list in Python. Here's what's going to happen. You've been given a linked list node class code. So you have class, node, value, next node. What I want you to do is fill out your solution below. That is, here you have your function called cycle check. It should be able to take in a node, and based on its attributes, specifically the next node attribute, your function should return a boolean if this linked list contains a cycle, meaning that a node's next point actually points back to a previous node in the list instead of a new node that has never been pointed to. So that's a circularly linked list, meaning you don't have a straight line, but there's actually a loop somewhere within your linked list. And your job is to create a function which does that cycle check. Once you filled out that solution function, you can go ahead and test your solution by running this cell. What this cell does is it creates 3 nodes, creates a cycle. Note here how we have c.nextNode equals a, meaning we have a perfect loop here. Then we also create a non-cycle list, and then we just check to see if the cycled linked list is true and the non-cycled linked list is false. Alright, that's the problem. Best of luck, and in the next lecture we'll go over the solution to it. Thanks everyone. Hello everyone, and welcome to the solution for the singly linked list cycle check problem. In this problem, you were given a singly linked list, and you had to write a function which takes in the first node in a singly linked list, and then returns a boolean, indicating if the linked list contains what's known as a cycle. And that cycle is when a node's next point actually points back to a previous node in the list. This is also sometimes known as a circularly linked list. You were given this linked list class node. Okay, so here we have our solution and the code to go along with it. Let me go ahead and read through just a basic explanation before we start coding it out. In order to solve this problem, what we're going to do is have 2 markers traversing through the list, marker 1 and marker 2. Those are actually going to be the variable names. Then we will have both markers begin at the first node of the list and traverse through the linked list. However, the second marker, marker 2, will move 2 nodes ahead of every one node that marker 1 moves. By this logic, we can imagine that the markers are racing through the linked list, with marker 2 moving slightly faster with a different step size. If the linked list has a cycle and is circularly connected, we will have the analogy of almost like 2 runners on a track in the field, with marker 2 being the faster runner. And in this case, the marker 2 will eventually be lapping the marker 1, and they will equal each other. If the linked list has no cycle, then marker 2 should be able to continue on until the very end, never equaling the first marker. So let me explain that basic logic one more time for you. You can essentially imagine having 2 tracks. One is a straight single line track, and the other one is a circular track. If you had two runners on the track, one very fast and one a little slower, then if the track was just a single straight line, in this case it was just a list with no cycle, then the runners would never actually meet up. The faster runner would just go ahead of the slower one, and they would never actually meet up. But if you have a cycle, or in this case a circular track, then eventually that faster runner, in our case marker 2, is going to go along that track, that linked list with a cycle in it, and it'll eventually pass or lap marker 1. And they're going to eventually meet, and in this case equal their values to each other. So that's the main logic here. So let's go ahead and implement this so we can get a better idea of what's going on. Jumping to a code notebook, let's begin by saying def, we'll say cycle underscore check, and take in that node. We'll begin both markers at the first node. We'll say marker 1 equals node, marker 2 equals node. And then we're going to go until the end of the list. We're going to say while marker 2 does not equal none, meaning we haven't reached that tail, and marker 2 dot next node does not equal none, meaning marker 2 isn't just about to finish. Then we're going to take a note. We're going to say marker 1 is equal to marker 1 dot next node, and marker 2 is going to be equal to marker 2 dot next node dot next node. That's essentially how we're going to make marker 2 go a little faster. Marker 2 is going to check one node ahead of marker 1. Then we want to check if those markers have actually matched. So if marker 2 is equal to marker 1, we return true. And there's might be a case where the marker ahead reaches the end of the list, meaning there's no cycle there. Then in that case, we just return false. So let's break this down one more time. We have two markers. They start off at just the node. And then we clarify until marker 2 doesn't equal none, or its next node is not equal to, sorry about that, none. Then what's going to happen is we'll check marker 1's next node and marker 2's 2 nodes ahead, meaning this one is essentially that faster runner on that lap. Then if marker 2 is equal to marker 1, we just return true. Otherwise, they never met up. Marker 2 never quote-unquote lapped marker 1, so then we just return false. We can go ahead and run that. So let's go ahead and test this. I'll zoom out a bit. And we'll put in our node class, and then we're going to go ahead and copy and paste the test cell from the notebook. And there's the test cell. So we basically just check against a cycle and a linked list that does not have a cycle. And if we run this, we get all test cases passed. All right, that's all there is. This is a bit of a trick, but it's a really good way of thinking about this problem. And hopefully that analogy of two runners running around the track or running down a straight line, with one of them being basically, in essence, a node faster here, and seeing if they meet up, is a good way of thinking about this particular problem. This is a really common problem in interviews, especially interviews testing linked list knowledge, so make sure you really know this one, and it'll be really great if you can explain this analogy to whoever's interviewing you. Alright, that's it for this lecture and this solution. I will see you at the next one. Thanks everyone. Hello everyone, and welcome to your next interview problem. This one's called linked list reversal. The problem statement is this. Write a function to reverse a linked list in place. The function will take in the head of the list as the input and return the new head of the list. So you're going to be given the example linked list node class. Here we have class node, object, and a value attribute as well as a next node attribute. This is the same one we developed when we were creating a singly linked list implementation in Python. Then go ahead and fill out the function below with your solution. As far as testing your solution, you should note that this isn't a classic just run a cell for testing solution. So go ahead and read these statements below carefully. You should be able to easily test your own solution to make sure it works. Given the short list A, B, C, D with values 1, 2, 3, 4, what you're going to do is check the effect of your reverse function and make sure the results match the logic here below. So for example, here we've created 4 nodes, A, B, C, D, with values 1, 2, 3, 4. Then we set up the order A, B, C, D, so it's A next node B, B next node C, C next node D. So if we go ahead and check these values, we'll get 2, 3, 4. And if we check the next node value of D, we'll run into an error because D does not have a next node. It was the last node. So far, so good. Note again how there's no value preceding the last node, so that makes sense. Now let's reverse the linked list. We should see the opposite order of values. Then, if we go ahead and reverse the linked list by passing in that head node, if you filled in the function correctly, you should get something that looks like this. Print d.nextNode value, get 3, c next node value 2, 1. And if you ask for the next node value of a, this should give the same error as d gave last time, because now it points to none. Okay, so hopefully you can use that logic to just test your function on your own before checking out the solution yourself. Okay, that's it for the problem. Again, you're just writing a function to reverse a linked list in place. Alright, thanks everyone, and I'll see you at the next lecture where we'll go over the solution to this problem. Hello everyone, and welcome to the linked list reversal solution lecture. Again, your problem statement was to write a function to reverse a linked list in place. The function should take the head of the list as input and then return the new head of the list. You were given this example of a linked list node class, and now let's go over the solution. Since we want to do this in place, we want to make the function operate in constant space, meaning we don't create a new list and add elements to it, or set up some other nodes. We have to do it in place. So we will simply use the current nodes. Time-wise, we can actually perform this reversal linearly, in linear time big O(n). We can reverse the list by changing the next pointer of each node. Each node's next pointer should point to the previous node. In one pass from head to tail of our input list, we will point each node's next pointer to the previous element. Make sure to copy the current.nextNode attribute into the next node before setting the current next node to the previous. So hopefully that sounds a little familiar from the lectures as far as how to insert new nodes and the order to do it in. In this case, we're not inserting anything new, we're just reversing the linked list in place. Let's go ahead and see this idea and strategy implemented out in code. I'm going to go ahead and hop over to a Jupyter Notebook. Alright, and let's go ahead and get started. First thing I'm going to do is start by writing out my function. So I'm going to say def, just call it reverse, and it takes in that head node. What I'm going to do is set up 3 variables, current, previous, and next. And these just stand for the nodes I'm at. So current, we'll start that off as the head node. Previous will just be none for now. Whoops. And we'll say next node is also equal to none right now. Now we're going to say while current. And this while loop will essentially let us know until we have gone through the end of the list. And then what we're going to do is make sure to copy the current node's next node to a variable next node before overriding as the previous node for reversal. And what I mean by that is doing this. I'll set next node variable equal to the current next underscore, actually next node in this case. Let me go ahead and paste in. We'll say pass here for now, just so I can paste in the cell code here. Copy and paste it just so we remember what the actual attributes are. We have value and next node. Alright, so just continuing on. So we set next node equal to current.nextNode. The reason I stopped for a bit is because in some of the node implementations we did, we had an underscore there. That's pretty much up to you on how you implement it. But in this case, for the solution notebook, we didn't have an underscore there. So I'll just say next node variable equals the current node's next node. So I want to make sure to copy the current node's next node to a variable next node before overriding as the previous node for reversal. Then I'm going to reverse the pointer to the next node. I'm going to say current dot next node is equal to previous. Then I'm going to go one forward in the list, which just means previous is now equal to current, and current is equal to that next node. After all of that, I just return previous. Let's go ahead and run this and test our solution. I'll zoom out a bit. And as I noted in the previous lecture, we can just copy and paste what the cell says there. So we create a list of 4 nodes, set up that order A, B, C, D with values 1, 2, 3, 4. We go ahead and print those values. I'm just copying and pasting from that solution notebook. And then we get 2, 3, 4. Let's go ahead and reverse this in place. Okay, we reversed it. It returned. And now let's print D, C, B, and we get 3, 2, 1. Okay, so now we can see that each of the values points to the actual previous value. Given that we're calling the next node of D, it's actually 3 now. C next node is pointed to, B is now pointing to 1, etc. Instead of the other way around, where B next node was pointing to 3. In this case, we don't do D in this first one or A in this first one because they're both pointing to none. Alright, that's it for this problem. Let's just walk through the main code one more time, this reverse function. All we have to do is set current, previous, and next node. And in this solution, the key thing to note is that you have to go through the entire list until the end of the list, and you want to make sure to copy the current node's next node before overriding as the previous node for reversal. That's basically the trick to this. So making sure to copy that current next node before overriding the current next node as the previous. If you mix up this ordering, you won't have anything else to reference and the algorithm won't make sense anymore. After that, you just set previous equal to current and then current equal to that next node. Okay, go ahead and check it out on your own. Make sure you understand it. But that's really all there is to it as far as reversing a linked list in place. This is a pretty common interview question, so make sure you fully understand it. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This one's called linked list nth to the last node. Here's the problem statement. Write a function that takes a head node and an integer value n, and then returns the nth to last node in the linked list. For example, given class node with value and next node attributes, your example input and output should look something like this. If we set up a linked list called A, B, C, D, E with node values 1, 2, 3, 4, 5, and then set up the order A, B, C, D, E, then quickly checking what the solution should look like as far as the format, your function will take in n, that nth to last node number, and then the head node. So here, if we pass in, given this singly linked list formatted as such, pass in 2 with the head node A, this should return the node D with a value of 4, because it's the second to last node. So if you have A, B, C, D, E, the second to last node is then D, and that has a value of 4. So if we go ahead and check the target node value, it returns 4 for us. As far as testing your solution, you can go ahead and run this test cell. It'll test your solution against a test case. Just note that it's just one test case, so go ahead and check it manually, as you might, to make sure your function is actually working as you think it should. Okay, again, your problem statement is just write a function that takes in a head node, an integer value n, and then returns the nth to last node in the linked list. And here's an example of what it should look like. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the linked list nth to last node solution. Okay, your problem statement was to write a function that takes a head node and an integer value n, and then returns the nth to last node in the linked list. So for example, if you were given a class of node that looked something like this, as we've seen before, and you were creating a singly linked list, A, B, C, D, E, with values 1, 2, 3, 4, 5, and then you assigned it like this, so it's all in order. Then your function, taking in a n value and the head node, would then return that nth to last node. In this case, 2, which means second to last, and that would return the node D with a value of 4, so if we went ahead and checked that out, there it is. Alright, so now let's go over the solution to this before we actually dive into this code below. The solution goes a little something like this. Imagine you have a bunch of nodes and a block which is n nodes wide. We could walk this block all the way down the list, and once the front of the block reached the end, then the other end of the block would actually be at the nth node. So to implement this block, we would just have to have two pointers, a left and right pair of pointers. Again, you have a bunch of nodes in basically a straight line. We're not worrying about cycles here. And then you have a block, which is n nodes wide, which is going to be dictated by this input argument. So then you keep moving or walking down this block, which is n nodes wide, all the way until it reaches the end, meaning that the other end of the block would be at the nth node. And we're going to implement this block as just two pointers, a left and right pair of pointers. So we're going to mark out the steps we need to take. We walk one pointer n nodes from the head, and that's going to be the right point. Put the other pointer at the head, and this will be the left point. We walk or traverse through our linked list, and that block, as it's being walked, essentially both those pointers, towards the tail end of the linked list, one node at a time, we keep a distance n between them. So they start off separated, both pointers, essentially making that block of n nodes, and we keep moving them one node at a time in sync together. And once that right point has hit the tail, given that they were moving in sync, we know that the left point is at the target. Okay, let's go ahead and implement this so we make sure it's really clear. First thing I'm going to go ahead and do, say DEF, and we'll just say nth to last node. We take in that n value and then that head node. Then I'm going to make two variables, that left pointer and that right pointer. And these are going to define that, essentially that block that's moving along our linked list. So I have a right underscore pointer as well. That starts off as that head node. So we are going to set the right pointer at n nodes away from the head. So I'm going to say for I in, I'll say x range. For using Python 3, that's just range. Difference between them is one's a generator, one's not. We can check for edge case in case we don't have enough nodes. So we'll say if not right pointer dot next node. And this basically means that we just didn't have enough nodes. I'll raise an error. In this case, I'll actually just raise a lookup error. And I'll say error n is larger than the linked list. It's always good to think about edge cases as you're programming. Your interviewer will definitely be checking out for those and see how aware you are about edge cases. Again, they're not your primary concern, so you should always be coding stuff out, and a common strategy is to code out the basic solution and then think about edge cases verbally along with your interviewer. In this case, this one's a pretty obvious one, so I just put it in right now. Alright, so if we're not receiving an edge case and we do have enough nodes, I'll just say right pointer is equal to right pointer dot next node. Okay, essentially that block and the left and right pointer are now set up. The left one starts at the head, and the right pointer has now moved n nodes away from the head. And we're going to move that block, those two pairs of pointers, left pointer and right pointer, down the linked list. We're going to use a while loop to do this. I'm going to say while right underscore pointer dot next node, which essentially means while it hasn't reached the end, while it's not none, which is why I'm able just to do these if not right pointer next node, while right pointer next node. So I'm not putting any comparison operations because I know that this value is essentially going to be none eventually, meaning it's reached that tail. And that's why I'm able to not have to do any comparisons with that if and while statement. So I'm basically saying if not none or while, basically it actually still exists and is not none. So while that's still going on, we haven't reached the end yet. I'll say the left pointer is just equal to left pointer dot next node. And then I'll say right pointer is equal to right pointer dot next node. So that's just moving them along together in sync. And now we just return the left pointer because this is going to keep executing until you've reached the end. So once that's done finishing executing, we just say return left pointer. That's going to be at the nth to last node. Okay, that's all there is to it. So let's make sure we run it and it all works out. I'm going to go ahead and copy that test cell. And let's run this. And all test cases pass. Excellent. All right, let's go real quickly line by line and make sure we fully understand what's going on here. I'm trying to find the nth to last node in a linked list, and my basic strategy is going to have a left pointer at the head and then have a right pointer that starts off n nodes away from left, essentially n nodes down the list, so we have a block of nodes between left and right. Then I'm going to keep moving them along together in sync with each other until the right pointer, that right end of that block, has reached the final node, meaning while this is actually still true in some fashion and it's not none. After all that, we've reached the last node with the right pointer, then we know that the left pointer is at the correct node. It's the nth to last node in that linked list. And that's all there is to it. Okay, go ahead and code this out yourself. Make sure you understand it. Make sure you understand the logic of those two pair of pointers moving down. This is a pretty common interview question when it comes to linked lists, and you should definitely know it. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome just to the last pair of questions as far as the linked list interview problem section goes. In this case, what I want you to do is just finally implement a singly linked list and implement a doubly linked list. Again, just for this interview problem, all you have to do is fill in this class node as we've done and use it to create a singly linked list, then add what you need to add in order to create a doubly linked list. There's no test for this solution because that would basically give away the answer structure for both of these. We do have implementation lectures, so you can review those in case you need the answers. The main reason this is actually even an interview problem to begin with is because usually for the previous interview problems we've seen, they may not give you the actual code for a singly linked list or just the nodes in general, so you have to implement the linked list yourself and then answer one of the questions that we previously asked. So it's always good to review and know how to build out the node class for both a singly linked list and a doubly linked list, know the pros and cons of each and how they work. Alright, with that being said, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to just a quick solution on the implement a linked list interview problem. As I mentioned in the previous lecture, it's a really common interview problem just at the beginning for you to implement a singly linked list and a doubly linked list. You can go ahead and check out the solution. It's just the exact same node codes as we've used before. The main difference between the doubly and the singly is that the doubly linked list, as you can recall from the lecture, can refer to the previous node, while the singly linked list only refers to the next node. Again, I won't bother coding these out because by this time you should be a total pro at this and be able to program these with your eyes closed, essentially. If you still have any confusion on them, go ahead and check out the full implementation lectures as well as the theory lectures for all the details on implementing a linked list, both a singly linked list and a doubly linked list. Okay, well, that's it for the linked list section. Hope you enjoyed it. Up next is going to be recursion, and we'll learn how to use recursion to solve a variety of problems. Okay, thanks everyone, and I'll see you at the next section.
Hello everyone, and welcome to the recursion section of this course. So in this lecture, what we're going to do is quickly go over what you can expect in this entire section, and then we'll go over the introduction to recursion lecture. Okay, so what's coming up in this section of the course? First, we have an overview of recursion, what it is and why we use it. Then we'll have some basic recursion examples that we'll walk through. After that, we'll get an introduction to memoization and dynamic programming and how it relates to recursion in general. And then we'll end it with 4 real interview practice questions for you to check your solutions against. Okay, so let's go ahead and get started with this lecture where we go over the basics of recursion through an introduction. So, what is recursion? There's 2 main instances of recursion. The first is when recursion is used as a technique in which a function makes one or more calls to itself. This is the main instance we're going to be focusing on throughout this entire section, since it's the one that comes up most in interview-style questions. It's important to note that a second instance of recursion is when a data structure itself uses smaller instances of the exact same type of data structure when it represents itself. We'll focus on this later on in other sections of this course. But for now, we'll focus on when a function makes one or more calls to itself. Okay, so why use recursion in general? Recursion provides a powerful alternative for performing repetitive tasks in which either a for loop or a while loop isn't really ideal. It should be noted that most modern programming languages support recursion, and recursion serves as a great tool for building out particular data structures. So let's go ahead and start this with an introduction by example using a factorial function. So the factorial function is denoted with an exclamation point, and hopefully you're already familiar with it. It's defined as the product of integers from 1 to some number n. So n factorial, or n exclamation mark, is equal to n times 1 times n times n minus 1 times n minus 2 times n minus 3, continued on until you reach 3 times 2 times 1, etc. Now, what's important to note here is if n equals 0, then n factorial is equal to 1. That's important to note because we're going to be using this as our base case later on. So, let's look at a quick example. 4 factorial is equal to 4 times 3 times 2 times 1 equals 24. So, how can we state this in a recursive manner? And this is where the concept of that base case is really going to come into play. So, we can see that 4 factorial is equal to 4 times, and we can group everything else together, 3 times 2 times 1. So we realize that this is actually equal to 4 factorial is equal to 4 times 3 factorial, which is equal to 24. So you note here we can keep making recursive calls to this factorial function. And to write that formally, we can say n factorial is equal to n times n minus 1 factorial. Okay, so the base case is the key to understanding this. If n equals 0, then n factorial equals 1. So this means that the base case occurs when n equals 0. The recursive cases are defined in the previous equation, right here. So we have the recursive cases, and then we have our base case. And this will be clear when we actually code this out live in a Jupyter notebook. So, quick reminder, whenever you're trying to develop a recursive solution, it's very important to think about the base case, as your solution will need to return to the base case once all the recursive cases have been worked through. So eventually, after going through every single recursion case, you'll come up to the base case. Okay, so let's actually code this out so it becomes a little more clear what a base case is and what the recursive cases are, and how we can build recursive functions off of that. Okay, so what we're going to do is jump now to the Jupyter Notebook and code out the factorial example. Alright everyone, now we're at the Jupyter Notebooks. As always, you can check out more information on what we just went over in the Introduction to Recursion notebook here, and it goes over everything we just went over in the slides. So let's go ahead and get started with some live code, which is also in this notebook and we'll be working out through this sample notebook. Okay, so recursion, and let's go ahead and tackle this factorial function. Remember, the factorial function states that n factorial, if we write this in a recursive manner, is equal to n times n minus 1 factorial. And our base case is if n is equal to 0, then n factorial is equal to 1. So you can imagine eventually this term here, n minus 1 or n minus 2, n minus 3, etc., will eventually become n equals 0, and we'll have this base case. Okay, so let's start out writing our function. We'll call it fact, and it will accept the number n, and it's going to return the factorial of n. So we want to start off with the base case. So the base case happens, like we said, if n is equal to 0, I will return 1. Okay, so let's go ahead and mark that through a comment as our base case. And then we're going to have an else statement. So if the base case isn't met, what we want to do is return that n times, and this is where the recursive call comes into play. We call the function itself and call it on n minus 1. And that's our function. That's really all there is to it. This is a pretty basic example of recursion. And we can see that factorial of 5 is equal to 120. So what's important to note is we had an if statement to check if a base case occurred here. Without this function, it wouldn't have successfully completed running. And there's a figure in the Jupyter notebook for you to go ahead and check out, so we can see what's actually happening when we run this function. Sometimes recursion is a little hard to visualize, so hopefully this helps you out here. So we input our function, and we input 5 into the function. So it says, all right, 5 factorial. So we pop back here, we're inputting 5 for 5 factorial. It'll check if it's the base case, which it's not, so or else, and if it's not that, then it's going to return n times factorial of n minus 1. So it's returning 5 times 4 factorial. Now remember, this is recursive, so now it's calling 4 factorial, so that becomes 4 times 3 factorial, etc. 3 times 2 factorial, 2 times 1 factorial, and then that goes to 1, returns 1, 2 times 1 equals 2, returns 2, 3 times 2 equals 6, returns 6, returns 24, returns 120. And that's how we get our final value. So make sure you take your time. You can follow this chart from the top to the bottom, and then back up to reach the base case. So recursion is a really powerful tool, and it can be a bit of a tricky concept to implement. So what we're going to do is, in case you had a little trouble understanding what just happened here, in the next couple lectures, we're going to go over a few more example problems for recursion. Then afterwards, hopefully you'll be fully prepared to face some real interview questions involving recursion. What I want you to do is, if this was a little bit troublesome for you, or you're still not completely understanding it, see if you can add some print statements to print out all the steps, or print out some sort of statement for yourself, so you can see what's actually happening as the function is being run. Okay, I'll see you at the next lecture. Hello everyone, and welcome to the Recursion Homework Example Problem section. So in this section, you're going to have a homework assignment where you'll have to fill out some simple example problems using recursion. So let's go ahead and do a quick overview of what the problems look like in the attached notebook. Let's go ahead and jump to that notebook now. Okay, so as always, you can find the Jupyter notebooks on the links, on the NB viewer links, or on GitHub as well. So in this case, we'll be looking at the Recursion Homework Example Problems notebook. Note, there's a Solutions notebook, so be careful not to click on that before you've had a go at the example problems yourself. In this video, we're just going to quickly explain what the Recursion Homework Problems are looking for. You can go ahead and just skip this video and read along for yourself. Everything's in the notebook. But in this video, I'll just explain what the problem's asking for any clarification. Problem 1, let's go ahead and zoom in on it. Says, write a recursive function which takes an integer and computes the cumulative sum of 0 to that integer. So, for example, if your input equals 4, what I want you to do is return 4 plus 3 plus 2 plus 1 plus 0, which is 10. So you function should return 10. So this is really similar to that factorial problem, but instead of multiplying, we're adding. So hopefully this should be a simple introduction and follow along with the base case thinking that we did when we were creating that factorial problem. And here's a cell for you to fill out, def rec sum or recursion sum, with a pass statement there for you to fill out. Problem 2 says, given an integer, create a function which returns the sum of all the individual digits in that integer. For example, if n equals 4,321, what I want you to do is return 4 plus 3 plus 2 plus 1. So this might be a little confusing, so let me go ahead and break it down for you. What you're going to do is, given any integer, you're going to break it up first into its individual parts, and then add up each of those individual digits. So you're not doing what you did here in problem 1. Instead, you're going to be splitting up that digit itself into individual digits. So how can you do that recursively? This is pretty tricky. So I've set up 2 hints for you. The first hint is that you'll have to use mod. And I left you a hint here that 4,321 mod 10 will return 1. The second hint I gave you is that 4,321 single digit divided by 10 is 432. Excuse me, single slash divided by 10. So what you'll have to do is, in order to think of this function recursively, know that this equation is what it's going to look like for your recursive case. So these are pretty strong hints here. Go ahead and think about them as you build out your function. Let's move along to problem 3. Now, problem 3 is probably a more advanced problem than the previous 2, and it also has a lot of variation and possibilities, and it can be asked in a lot of different ways. So we're going to ignore just strict requirements here. And what the question asks for is for you to create a function called word underscore split. So that's this function right here. And it's going to take in a string phrase and a set list of words. And what I want you to make the function do is the function will determine if it's possible to split the string in a way in which words can be made from the list of words. And you can assume the phrase will only contain words found in the dictionary if it's completely splittable. So for example, the function should be able to take in a string like this, the man ran, all one word in the string, take in a list of words, the ran man, and then recursively check if it's able to split that string and output the words that were in the dictionary. Another example is I love dogs John, all one string, one giant word. And here we have a dictionary or a list of words, excuse me, a list, not a dictionary, a list of words that says I am a dog's lover, love John. So it has a bunch of words. And what I want you to do is recursively check if you can split up this string into words found in that list of words right here. So I love dogs John. The last one is an example of something failing. So the man ran. Here we have a list with clown, ran, and man. And you'll notice that the function is not able to split this up into words that are all in the dictionary, since this the phrase is not in the dictionary, or anything else that the is attached to, since only clown, ran, and man, so it returns an empty list. Go ahead and take your time with this one. If you're confused or are a little stuck, then go ahead and check out the solution notebook. Okay, so that's it for this video. Remember, this notebook, if you go to the Jupyter NB viewer or the GitHub page, it's called Recursion Homework Example Problems, the IPython notebook, and as always, it's under the Recursion folder for this course. Okay, everyone, best of luck on the homework assignment. Feel free to check out the solutions if you get stuck. In the next video, I'll be briefly going over the solutions. Okay, I'll see you at the next lecture. Hello everyone, and welcome to the lecture where we'll be going over the Recursion Homework Example Problems and the solutions. Here I'm at the Jupyter Notebooks, and if you go to the Recursion folder, you'll notice a Jupyter Notebook called Recursion Homework Example Problems - Solutions. You can go ahead and click this notebook. It'll take you here to the Solutions notebook, and you can go ahead and read through the solutions here on your own. if you're interested in following along. Okay, I'll go ahead and live code the solutions and explain the thinking through them. So let's go ahead and start off with problem 1. So the first problem said, problem 1, write a recursive function which takes an integer and computes the cumulative sum of 0 to that integer. For example, if n equals 4, return the result of 4 plus 3 plus 2 plus 1 plus 0, which is 10. So how do we do this? First thing you want to consider is the base case. So in this case, if we write this recursively, we have n plus n minus 1 plus n minus 2 all the way to plus 0. So regardless how high the n is, we know it's going to go all the way down to 0. So our base case will be then if n is equal to 0. And what I'm going to return, in this case, is 0. Because once I hit 0, I don't want to add anything else to it. So this is our base case. After that, we have the recursive case, which in this case, what we're going to do is just return that n plus our recursive call in that function, recsum, on n minus 1. And we can go ahead and check this out if we want to, recsum on 4, and you'll note we get 10. All right, so go ahead and read through, make sure you really understand the solution here. The big factor here was the base case, recognizing it, knowing what to return, and then being able to transform this line of thinking, n plus n minus 1 plus n minus 2, into this line of code, return n plus the recursive call in the function on n minus 1. Hopefully this looked familiar to you because it's so similar to that factorial function we created earlier. All right, moving along, we have problem 2. Let's go ahead and make some more space in the cell. Given an integer, create a function which returns the sum of all the individual digits in that integer. For example, if n equals 4,321, return 4 plus 3 plus 2 plus 1. Okay, this one was a little trickier, and I gave you a couple hints. So let's think of what the base case is here. The base case will happen as we go along and use mod and division to take and strip these numbers each individually, will be when the remaining length of that n is just 1. So what I mean by that is if length of that digit, and you'll notice there's an error with this, which I'll fix in a second, is equal to 1, I just want to return that n. We won't have to strip off any more digits from it. And what we're going to be doing in the recursive case, else, is doing something here to basically strip another digit off of that. So the error that's going to happen here, if I don't fix it, is that since it's an integer, it actually doesn't have a length. So kind of a quick way, and thanks to Python, I can just cast it to a string and then take the length and make sure it's equal to 1. There's other ways to do this, but in this case, it's a pretty straightforward solution. So how can I strip another digit if I'm not at the base case? Let's go ahead and just comment that as the base case so it's clear. So I wrote about this in the hint, and what I can do is return n mod 10. That will be the number I want to add to the recursive call, which in this case will be sum underscore func and divided by 10. Note that I'm dividing by an integer here, and since this is Python 2, this will work correctly. You'll have to use the differences between classic division and true division. So this is going to perform classic division since I'm using Python 2 right now. If you're using Python 3, you'll have to make sure this is performing classic division, not actual true division, in order for this to work correctly and for you to strip these functions out. Okay, there's a note about that in the solution notebook. So moving along, we have the last problem. Now, as I mentioned, it's a more advanced problem than the previous two, has a lot of variation on possibilities, and we're going to go ahead and solve it a particular way. So let's go ahead and break it down. So we have this function, word underscore split. So what I'm going to do is have, in this case, 3 arguments. And note, the solution I'm going to implement here makes a lot of use of the Python language. Now, the first thing I'm going to do is check if output is none. I'm going to set output equal to an empty list. So the reason I just can't put in output as an empty list into the function here is because I'm going to call it recursively. And if I were to set it at the beginning as a default parameter, it would overwrite the output list that I want to put out every single time. So basically all this does here, if output is none, output equals empty list, is it just takes care of creating an empty list on the first instance of that recursion. So let's go ahead and think of what I want to do here. I want to say for word in list of words, so for every word in that list, for word in list of words, I'm just doing tab complete there. Then I want to think if the current phrase begins with the word, we have a split point. So remember what we're trying to do here. We want to create a function that takes in the string phrase and a set list of words. And then the function is going to then determine if it's possible to split the string in a way in which words can be made from the list of words. So what I'm doing here is I'm saying for every word in that list of words, if the current phrase begins with the word, we have a split point. There's lots of ways to do this. You can just use simple indexing, but I'm going to use a little Python trick here called starts with, which actually just checks if a string starts with another string. Another way to do this would just be by indexing. So you would check the length of this word if it's equal to the first index of that phrase, given that length. But this is a little more concise way to do this. And then what I'm going to do, if that phrase starts with that word, also what's nice about using starts with is it's super legible here. You can really read it. It's almost like pseudocode. And then I'm going to append it to that output with word. And then what I'm going to do now is recursively call the split function on the remaining portion of the phrase. So I'm going to return, and this is where my recursive case comes into play. I'm going to say word underscore split. I'm going to input the remaining portion of that phrase, which is phrase, index from the length of that word to everything else. I'm going to pass in the list of words since that's not changing. It's the same constraint there. And then I'm going to input the output. That sounded a little weird, but basically pass the output list that has been appended to. And then finally, I can return the output. So this will happen if no phrase starts with that word. Okay, perfect. So that's it. You can go ahead and run the solutions that are in the solutions notebook here. There's a little more explanation with the comments here, so you can really get an understanding, since it's a bit of a confusing problem and there's lots of ways to do it. And also, as I mentioned, it's kind of a Python-y solution, what I did here, but it's nice and legible. I encourage you to try to basically switch out this phrase using indexing, so it's a little more agnostic as to what language is being used as far as programming languages. But that's it for the examples. Hopefully they were a little challenging, but not too impossible for you to solve. Again, go over them, make sure you fully understand them. And that's it for the recursion homework example problems. After this, you'll be faced with your first real interview questions involving recursion. All right, great job, and I will see you at the next lecture. Thanks, everyone. Hello, everyone, and welcome to the memoization lecture. Now, I know in the previous lecture I said that interview problems were next, but I wanted to make you aware of this topic, memoization, and this lecture, which is actually going to be mostly a homework reading assignment that I want you to be aware of. So if you're in the Jupyter NB viewers, under the recursion folder, there's a IPython notebook called memoization.ipynb. You can go ahead and click it. It'll take you to this lecture here. And what I want you to do is, before reading the notebook itself, go ahead and click the link to the Wikipedia article on memoization. Give it a read through because it's actually quite good as an overview. And the pseudocode is very reminiscent of Python code, so you should have no problem reading it. And it uses the factorial example that we used earlier to explain memoization. And it turns the example we use, which was recursive, using a memoized version of the factorial function. So go ahead and take a look at that. It'll line up perfectly with the factorial example we showed earlier. And go ahead and you can also read about automatic memoization, which we discuss a little bit at the end of the notebook. But what I really want you to focus on is this first section of the overview for that article. Once you're done reading that, come back and then take a look at a coded out example of the same factorial problem using Python. Okay, that's it. Only one or two of the recursion interview problems will actually need memoization. I believe it's actually just one. Memoization with recursion is sometimes known as dynamic programming, or at least a type of dynamic programming. So I want you to be aware of that. So I would recommend that you read that article and go through this lecture before heading into the interview problems, but it's actually not necessary to tackle the first interview problems at first. You'll see a warning or a note or a hint that will lead you to read the memoization lecture if in case the recursion interview problem requires it, or it's just a better solution to solve it using that technique. All right. So that's it. This is mostly just a reading assignment lecture. So go ahead and read that Wikipedia article overview section and then go through this IPython notebook or Jupyter notebook. All right. Thanks, everyone. And in the next lecture, what we're actually going to be doing is going over the recursion interview problems and the solution. Okay. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the first interview problem for the recursion section of this course, where you'll have to reverse a string using recursion. Before we begin, I want to remind you how you can get to this lecture, or at least a notebook related to it. Once you're at the Python for Algorithms, Data Structures, and Interviews repo, you can go to the recursion folder. Here you'll see another folder called Recursion Interview Problems. You can go ahead and click it. You'll see two other folders, Solutions, and then Problems. Go ahead and then click Problems. And here you can see the 4 real interview problems set up. And then we have the Reverse a String notebook. So what I want you to do for this interview question is you're required to reverse a string using recursion. And really make sure you think of what the base case is going to look like here. So again, you have to use recursion. Don't use slices or use some sort of iteration for this. You have to use recursion in your function. Here you can fill out your solution below, and here's an example of it being used. Reverse takes in a string hello world, outputs the reverse of hello world. Once you've filled this out, you can test your solution by running the cell below here. So you can run this cell to test your function against some test cases. Here are the test cases. It uses the assert equal as always from those tools to test, and you should see this print statement passed all test cases if you passed all the test cases. All right, so keep in mind you have to use recursion. There should be another call here of reverse somewhere in this function in order for it to be recursive. Think of what the base case would look like and just take your time with it. Really focus. Try timing yourself so you can see how long it takes you, and treat it as a real interview question. All right, best of luck. Remember, you can always download the notebook right here with this button on the top right in the Jupyter NB viewer. Or if you've forked everything on GitHub, there's a GitHub link here as well. You can just have it downloaded and then run it locally. All right, thanks everyone. Best of luck. In the next lecture, we'll go over the solution. Hello everyone, and welcome to the recursion interview problem solution for the first interview problem, reversing a string using recursion. Remember, you had to use recursion to solve this. You couldn't slice or use an iterative process. As always, there's a full solutions notebook that goes over the solutions with code and an explanation, and then you can test out the solution yourself. In this case, it's in the folder under recursion interview problems, and then recursion problems - solutions. You can click that folder and it'll take you to all the solutions for all the interview problems. In this case, we're looking at reverse a string. So we're going to go ahead and walk through the particular solution we have for this interview problem. So let's go ahead and think about the problem. What we have to do is reverse a string using recursion. So that phrase recursion, we already know we need a base case and some sort of recursive case. So let's go ahead and start filling that in. We'll need a base case, and notice how I'm just thinking out loud with comments. This is important to do during an interview. You really want to make sure that your interview isn't just watching you perform silently or think silently. Think out loud during the interview process. So what I'm thinking right now is, since I know I'm going to use recursion, I'll have a base case and a recursive case. And let's go ahead and put a pass in here so we don't get an error when we run that block. So let's think about what we want to do here. If I have a string, let's just say it's A, B, C. I want to reverse this string, which means I'm going to want to grab C somehow, and then grab B, and then grab A, and then add them up together. But I want to do that in a recursive fashion. So how can I do that? Well, we can start by thinking of the base case. How would I know that I'm done? If we're constructing this reverse string recursively, I'll start out with C, and then I'll have to do some sort of recursive call on that reverse function, and I'll pass in everything else that's remaining. Let's say AB. And then that will eventually lead to, and this is just pseudocode, to some sort of call on CA, and then, CB, and then I'll have some single letter remaining. No matter how long the string is, eventually at the end, I'll just be adding one single element to that string as I reverse it. So I know I can think about this as my base case being when I only have one element left in that string. So we can go ahead and fill that out. I could say if the length of what string is, in this case I'm just going to say less than or equal to 1, I'll return that string because I know I'm done. So already, just by thinking about it logically, I can think that I have a base case when the length of my string is 1. So I won't need to do any more recursion calls on it. So now we can focus on the recursive case. What do I actually want to return here? So if we think about this, we want to grab the first element of the string. And in this case, that will be S index 0. And we actually want to tack it on, since we're reversing it, we want to tack it on to the recursive call of the function, reverse in this case, on the string. But I don't want to do it on the whole thing. I want to do it on everything that wasn't in that first element. So I want to do it from 1, index 1, all the way to the rest of the string. So let's go ahead and run this, make sure it works. I'll call reverse. And here we go, CBA. Great. So let's go ahead and work through this and make sure we understand what's actually happening. First, we check if we have a base case. Is the length of the string less than or equal to 1 here? And what I want you to know is we could also have just said check if it is equal to 1. So we're checking if it's equal to 1. If it is, then we know it's the base case. In some languages, you may need to check if it's less than or equal to 1, which is why I keep it here. So then we'll return that last element of the string. For every other case, we'll pop off that first letter. So if we're just starting out, we'll pop off A, and then we'll attach it to the recursive call on everything else, which will then pop off B, and then we'll pop off C. So in this case, what's happening recursively is I grab A, and pop off B and C. Then, on the next recursive call, I grab B, pop it off from there, and I'm remaining with C. And then I see that C, that element, only has a length of 1. So these little sections of string here, granted this is pseudocode, I can make it into real code by adding single quotes, will then form the reversed version of that string. So as far as code, this is actually very, very simple, what you had to code out, but it was really the process of thinking about it, thinking about what order this statement and this statement go in order to have the correct solution. So again, walk through the solution notebook, make sure you really understand the important parts here. We're thinking about the base case, what it would look like when you're reversing the string. So don't worry if you had a little bit of trouble in thinking about what the base case would look like. It just takes a lot of practice, and you do have to struggle with it for a bit since thinking about things recursively doesn't come naturally to a lot of people. So it's important to see a lot of examples. Again, if you're having trouble with it, you can look through the example homework problems we did earlier in this section of the course, or go ahead and look up just basic recursion problems online through Google. All right. So again, hopefully this was pretty straightforward as far as what the solution actually looked like, and make sure that both the base case and the recursive case make sense to you as you review this problem. All right, great job, and I will see you at the next lecture. Hello everyone, and welcome to the second recursion interview problem. In this problem, you'll have to find all the permutations of a string. So in this video lecture, we're going to quickly go over what the problem is asking for, what your solutions should look like, what the test cases look like, and then I'll let you get on with tackling the problem on your own. So let's go ahead and look at the problem statement. So given a string, write a function that uses recursion to output a list of all the possible permutations of that string. So for example, if your string s equals just the letters A, B, C, you should return a list that looks like this: ABC, ACB, BAC, etc., all the various permutations. Now what I want you to note here, if a character is repeated, treat each occurrence as distinct. So for example, if your input is XXX, you should return a list with 6 versions of XXX. So don't worry about taking care of duplicate letters here, just all the permutations as if each character was distinct. That should make your job a lot easier. All right, so what you're going to do is fill out your solution below. Again, think about the base case, what recursive call you're going to have to make in order for this to all work out. After that, you can test your solution. You'll run this cell to test your solution. There's a couple of basic test cases here, and if you pass all of them, it'll say all test cases passed after you run that cell, after you fill out the permute function. All right, so best of luck. This one's a little tricky. There's a few different ways that you could solve it using recursion, so don't expect your code to look exactly like the solution. In the next lecture, what we're going to do is go ahead and walk through the solution. Make sure you've attempted it first before seeing the next lecture video. All right, best of luck everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the string permutation solution lecture. So before we begin, what we're going to do is check out the problem statement. Again, there's a solutions notebook fully explaining the solution below, as well as a commented version of the code. Okay, let's go ahead and remind ourselves what the problem statement was. Given a string, write a function that uses recursion to output a list of all the possible permutations of that string. So for example, if the string is ABC, the function should return these 6 permutations of it. Now there was a special note here. If the character is repeated, what you should do is treat each occurrence as distinct. And what that meant was, if you had an input string of 3 X's, then you should get 6 versions of XXX. All right, so given that, we want to fill out a solution below. Something I wanted to make note of, if the problem was just to permutate a string, you really wouldn't write your own function. In Python, you would use the itertools library. So I go ahead and suggest that you check that out. It's a really, really useful library in Python for doing these kind of operations. Okay, and it'll get you some bonus points with your interviewer if you mention that you know about it before you begin. So let's go ahead and look at the steps we're going to take to solve this problem. I'm going to zoom in a bit below. So there's 4 main steps here that we're going to use to solve. The first one is we're going to iterate through the initial string, so ABC. And that makes sense. In order to have any sort of permutation, we'll have to iterate through that string. Then, for each character in that initial string, so for instance, A and B and C, we'll set aside that character and then get a list of all permutations of the string that's left. So, for example, if the current iteration is on B, then we want to find all the permutations of the string AC, which would be AC and CA. Then, once we have that list from step 2, we would add each element from that list to the character from the initial string and append the result to our list of final results. So if we're on B again, we've gotten the list AC and CA, and then we'll add B to the front of those, resulting in BAC and BCA. And in each of those, we add to our final output list. And then we return the list of final results. So that's the main thinking we want to do. For each of these letters here, grab the rest of these letters and then see all the permutations of them, and then tack them on to that first initial letter. Now, hopefully you can see that this is starting to become a recursive problem, because if you have more elements or letters in that string, in a more generic term would be elements. So if you have more elements in that string, you could keep doing this for all those letters until you've come back recursively to that first initial letter. So to give you a better idea of what I'm trying to say here, let's go ahead and start coding it out. So first thing you want to do is just create the function. I'm going to call it permute. It takes in a string, and then I'm just going to say pass right now. All right. So in this case, what we're going to do, since we're going to output a list, it specifically asked for a list in the problem statement, I'm just going to make a variable called out and set it to an empty list. And let's think of the base case again. Remember, as we iterate through the string and go through all the elements, we know, similar to the last interview problem we just did, that the base case is going to happen when we just have one letter left, because there aren't going to be any following letters that we can do any sort of permutations on. So right off the bat, we already know what the base case is going to look like just by thinking about it logically. We're going to say if length of that input string is equal to 1, then we know out, we would just put that element on there. All right, now for the recursive case. So else. So what we want to do is, just like we were saying in those 4 steps, for every letter in that string, and I'm actually going to comment what we're doing in plain English. So for every letter in string, and in this case, I actually want to keep track, so I'm going to be using slicing. So I'll use enumerate. So I'll say for I, let in enumerate that string. Then for every permutation resulting from step 2 and 3 that we described, so for every permutation resulting from step 2 and 3, so that would be for, I'll say for perm in, and this is where the recursive call comes into play. For perm in permute, and I'm going to type it and then explain what I'm actually passing here. Let me go ahead and center that. Plus s of I plus 1 continued. I'm going to add it to the output. I'm going to say out equals plus the letter plus that permutation. And then finally, whoops, once that's done, I will return the output list. Okay, so base case should have been pretty straightforward. Once you have just one letter left, you just return that letter. Now else is a little different. So for every letter in that string. So what are we doing here? I'm saying, using enumerate, I grab the index of my total string and then the letter in enumerate. And then for every permutation resulting from step 2 and 3, I'm going to add it to the output. So I say for perm in permute s, and s is going to go all the way from, oops, this should be I, excuse me, sorry, from everything up to the current index we're on here, plus the string from I plus 1 all the way to the end. So this is kind of tricky to understand, so I'm going to break it down a little further. So look what I'm doing here. I'm grabbing everything up to that index and attaching it to that index plus 1 all the way to the end. And so what that will do when I pass it into permutation, it will, if we go back to the solution notebook, you can see here it's going to basically say, okay, get A, and then pass that BC into the permute function, and then recursively keep calling it all the way until you only get a single element in that string. So your homework assignment, if you're having trouble understanding what this slice notation is actually doing in this permutation recursive call, go ahead and add print statements to help yourself really visualize this. So for instance, you can add print statements for yourself if you want to know perm is, you can add that, print, well, let's just go ahead and see what that will do if we run it that way. And then go ahead and run it on a very simple and obvious string like 1, 2, 3. And it'll show you the steps printed out for the permutations that it's doing. Perm is 3, perm is 2, perm is 2, 3, perm is 3, 2. And then since you're adding that to let, you can actually print that out as well. So we can go ahead and then put in, for instance, print current letter is LAT. And if we run that, we can say current letter. I should say element since I'm actually running numbers here, but I'll say A, B, C. So current letter is B, the perm is C, current letter is C, perm is B, current letter is A. And notice here, now we have the permutations we can add to it. BC and CB, which will end up being ABC and ACB, and that's going to be added to that out list. So use print statements to help you understand this. I know it's a little confusing if you just look at it at first glance, but feel free to print out as many of these things as you need to. You can also print out these specific index slices to help you really understand how these recursive calls are working here. Okay, so that's it for the solution. Remember, you can read the entire solution notebook for a deeper view of how it's actually working. But all we're basically doing is going through the iteration of the string. Then for that string, we take off an initial letter, look at everything else, and then find the permutations of it. In which case, if we do this recursively, we'll take off that initial string and then find the recursions of that using that slicing notation we did earlier. All right, so go ahead and walk through the solution and make sure you fully understand it. And other than that, I will see you at the next lecture. Good job, everyone. Hello, everyone, and welcome to the recursion interview problem number 3, the Fibonacci sequence. So in this interview exercise, we'll begin to get a feel of having to solve a single problem multiple ways. All right, so if you decided to skip the memoization lecture reading material, you'll have to go back and read it in order to fully understand the various ways to solve this problem. So for this problem, what you're going to do is implement a Fibonacci sequence. In case you're unfamiliar with the Fibonacci sequence, you can go ahead and click the link that's provided for you in the notebook, and it'll take you to the Wikipedia page for the Fibonacci sequence. All it is just takes the last two numbers to define the next number of the sequence. So 1 plus 1 delivers 2, 1 plus 2 delivers 3, 2 plus 3 delivers 5, etc. Okay, so you can see how this is kind of set up already for you to do some sort of recursion in order to solve this problem. You can also use dynamic programming, which utilizes memoization. That will allow you to store results. Then you can also solve this problem iteratively. So let's just go over what the function is going to actually accept for input and what it'll output, and then we'll discuss each of the different methods of solving it. So your function is going to accept the number n, and then return the nth number of the Fibonacci sequence. So remember that a Fibonacci sequence, like I mentioned before, it's just a series of numbers, starts off of a base case, checks if it's either n equals 0 or 1. If that's the case, it would return 1. Otherwise, it returns something that looks like this sort of recursive sequence. So hopefully that's a big hint as far as solving it using basic recursion methods. So your first part of this interview problem will be solve the Fibonacci sequence problem. So for instance here, fill out this function using simple recursion to put in the n that you want, and it will put out the nth number of that sequence. So the 10th number in a Fibonacci sequence is 55. Okay, then you'll have to use dynamic programming, which will implement memoization using a cache to store results. You'll need to instantiate cache information. So I've put that here for you already, kind of as a setup, and then you can fill out that function. Again, you'll have to go back and do the homework reading material in order to fully understand memoization and go through that factorial example in both that notebook and the Wikipedia article reading from that lecture. After that, I want you to solve this iteratively, just using simple iteration. You'll have to use tuple unpacking, or you should use tuple unpacking. You don't have to, but it's definitely the better way to go as far as solving this. And here's an example of it being solved. So depending on which of these functions you want to test, you can test your solution with this cell. What you got to do is simply uncomment the one function you want to test. So for instance, right now, this will just test the first recursion function. Something I want to point out is, besides uncommenting, you'll have to take into account, especially for the dynamic programming, that you may need another input as far as the cache. I'll leave it at that so I don't kind of drop too many hints, but if you're having too much trouble with the normal recursion function taking just way too long, or having the dynamic version not pass any tests, go ahead and make sure that you can compare it to at least some of these first cases here and see if it sticks out the correct result. And then after that, go ahead and check out the solution notebook. So don't worry too much as far as this particular testing cell, because it may fail even if you have the right solution for some of these more complicated dynamic programming solutions. Or if you have a normal recursion solution, it may just take forever, and you shouldn't have to wait for that. You should just go and check your solution against the one in the solution notebook. All right. So again, this is good practice. A lot of times in an interview situation, you'll be asked to solve the same problem in multiple ways. So you can go ahead and do that here with the Fibonacci sequence problem. All right. I'll see you at the next lecture, where we're going to walk through the various solutions for this problem. All right. Thanks everyone, and best of luck. Hello everyone, and welcome to the Recursion interview solution to the Fibonacci sequence interview problem. All right, before we get started, just again, a reminder as always, there's a full solution notebook for this interview question in the recursion problems folder. It's the recursion problems-solutions folder here. So this is the notebook. It has the solutions for all three of them, all three requests, and the test your solutions cell. All right. So let's go ahead and begin. What I'm going to do is go through the problem statement, make sure we understand it, and then do a walkthrough of the three separate solutions for this problem. Now, the question itself was implement a Fibonacci sequence in three different ways: using recursion, using dynamic programming, so using memoization to store the results, and then using just a straight iterative approach. So remember, just a reminder, the Fibonacci sequence, there's a link here to the Wikipedia article. is just when you take the two previous numbers and add them to get your next number in that sequence. Now, remember the base case checks to see if there's a 0 or a 1. In that case, it returns a 1. Otherwise, it returns this, fib n minus 1 plus fib n plus 2. So in this specific case, what I wanted you to do was for the n that was input, you would return the nth number in the Fibonacci sequence. All right, so let's go ahead and get started. What I'm going to do is start by going over the iterative solution first. So if you scroll down to the bottom of the notebook, that's this one. After that, we'll go through the recursion solution and then the dynamic programming solution. So what we're going to do is first walk through the iterative solution, since that's the most straightforward one. And it also shows that as far as approaches to a particular problem, you don't always have to do it a classic way or a certain way. There's multiple ways to solve a single problem, and that's really the main point of this interview question, is to show 3 separate approaches to solving a problem. So in an interview scenario, you could easily get asked this problem of a Fibonacci sequence, and you could also be asked to solve it every single way here. So let's start off with the iterative solution. So we'll call this fib underscore iter. It takes an input n. And we're going to go ahead and set a starting point. In this case, we started at 0. I'll say a equals 0, b equals 0. And then after that, all we have to do is just follow the algorithm that's in place. So for I in range, remember we're going all the way to n since we want the nth number. And in this case, we can actually use the tuple unpacking method in Python. I can simply say AB is then equal to B, A plus B. And then I just have to return A. And let me fix something real quick. This should be a 1. And if we actually want to use tuple unpacking further, I can say A, B equals 0, comma 1. And that will assign things. This is using a very Pythonic solution to say A equals 0 and B equals 1. All right. So let's quickly review what's going on here. If I go ahead and run that cell and then input fib underscore iter, put in 10, I get in return 55. Okay. So all this is doing is just saying A is going to be equal to B and B is going to be equal to A plus B. And at the end, return A. So this is just using just a very simple looping technique, using a for loop here to loop through the range, and then using tuple unpacking to set the new Fibonacci number at the n. All right, so that's the most straightforward solution. What I wanted to make you aware of is this nice little link, and I'll add it to the solution notebook. But if you actually just Google Python or 5 ways of Fibonacci in Python, here's the complete URL. It's on TechnoBeans. But if you Google 5 ways of Fibonacci in Python, we can go ahead and do a Google search for that. That will take you to this page, this TechnoBeans page, and it'll show you 5 different ways of calculating the Fibonacci sequence in Python. So you can use that looping technique. This is actually what we just did. In his case, he started at 1, 1. Let's go ahead and zoom in here so you can see better. You can also use recursion, which we're about to go over. You can do it using generators, which is an interesting way. And then you can use memoization, which we'll also go over. And finally, he shows using memoization as a decorator, which we actually go over in the memoization lecture itself for the factorial problem. All right, jumping back to the solutions, we can now go ahead and tackle the recursive version of this problem. So, how will we do this recursively? Let's go ahead and get started. We'll call our solution fib underscore rec. And what we need to do is have a base case and a recursive case. So, what is our base case? Well, we know we need to start with either 0 or 1. And in that case, we can just say if n is equal to 0 or if n is equal to 1, return n. And that's it for our base case, which makes sense because that's how the Fibonacci sequence starts. What about the recursion case? Well, that's actually just writing the algorithm for the Fibonacci sequence. All we have to do is return the recursive call of our function on n-1 plus the recursive call of our function on n-2. And let's make sure that worked. I'm going to call it on 10. And there we get 55 out. So what might be interesting to explore is using timeit or any other sort of timing library in Python to see which one of these solutions runs faster. Again, for iteration, all we're doing is setting a equal to 0, b equal to 0, and then for I in range all the way up to n, you're just setting a equal to b and then b equals a plus b. Very similar here, except using recursion, you set your base case first, and then in the recursive case, you recursively call this function on n-1 and n-2, so those previous two numbers. Then you add them up, that gets you your final solution there. All right, finally we want to explore dynamic programming using memoization. So in the form I'm about to implement it here, I'm going to set the cache beforehand, and it's based on the desired n of the number of the Fibonacci sequence. So this is only going to work for this specific n that I know beforehand, so just keep that in mind. All right, let's go ahead and get started. It's going to look pretty similar to the recursion problem we already have, but it's going to be a lot more efficient because we're storing stuff or previous known results in memory. So let's go ahead and get started. I'm going to go ahead and start with the cache information. Now the particular way I'm doing it now is I'm setting it on an n that I already know I'm going to ask for it. And there's quite a few notes on why I'm doing this in the solution notebook itself and how that affects your test cell in that notebook. So make sure you go ahead and review that before continuing on. And I'll set my cache equal to a list of nones, length of n+1 or 11. So I'll multiply it by that. Okay. And then what I'll have to do three things here. I'll have to figure out what my base case is. I'll have to check my cache. And I'll have to basically keep setting that cache. And then finally, what I'm going to do is, since I'm using memoization, is return that nth number on that cache. Okay, so we got three cases here. Let's go ahead and get started. Base case, that's going to be the same as the normal recursion problem. I'm going to say if n is equal to 0, or if n is equal to 1, just return n. So that's pretty straightforward. Those are the first numbers in the Fibonacci sequence. Now checking the cache. So I know that if my cache at that particular n is not equal to none, all I have to do is return that cache, because it means I haven't filled it out yet, or I haven't set it. And finally, how am I going to set that cache? So that cache of n here is just going to be equal to the recursive call, which is the exact same thing we just did in the recursive solution. So basically, all I'm doing here is the recursive case, but I'm making sure to check my cache first, and instead of just producing these in a recursive fashion, I'm actually keeping track of them by adding them to this list. And in this case, instead of using append, I've set my cache first. I already know what n I'm going to ask for. So if I run this and then say fib dyn for dynamic and ask 10, I'm going to get 55 out. Now what happens if I choose another n? I will get an error, because you'll notice I get an index error because the list index is out of range. And that's because the way I've set it up here, to make it really obvious that we're having a cache, I set the cache instantiation outside. I would have to set this n value to whatever n I'm going to run first. 144 in this case for 12. All right. So how could you fix that? Well, you would fix that by using append here and being able to create that cache on the fly as you go along. You wouldn't reset it or set it since the beginning here. All right. So those are the solutions for all three of them. You'll notice that actual coding is very simple. It's the thinking that's the most difficult part of this problem. And that's the case for a lot of these recursion problems. Thinking about the problem is much, much harder than the actual code you're going to write. So let's go ahead and jump to the solutions notebook and make sure we really understand everything we just went over. So the iterative solution, we set a starting point, in this case a equals 0, b equals 0, and we just follow the Fibonacci algorithm. We set a equal to b, and then b is equal to a plus b. Notice with tuple unpacking, I can save myself a temporary variable. So I'm actually not setting a equal to b first, otherwise this would just be b plus b. So that's a really nice Pythonic solution here as far as setting this all in one line. This basically automatically takes care of the ordering, so you don't have any errors of setting b equal to b plus b or setting a equal to the new b instead of the old b. All right. And then for the recursive solution, all you have to do is think about the base case and then just follow the formula or the algorithm by calling it recursively on n-1 and n-2, since you're concerned with the last two numbers of that sequence in order to come up with the next number of the sequence. And in a really similar fashion here, and I've instantiated the cache information first, just so it looks really similar to the recursion solution, we check for that base case, and we set a cache by calling that recursion function if it equals none. All right, so make sure you go ahead and walk through this entire solutions notebook to get a really good understanding of the Fibonacci sequence problem. It's a pretty common interview problem, at least on the basic level, and you can learn a lot, especially on learning how to solve a single problem in a bunch of different ways. And I encourage you as a homework assignment to use some sort of time it feature in Python or some sort of time it library in order to see which one of these runs the fastest. Okay, so that's it for this interview problem. Good job, everyone, and I will see you at the next lecture. Hello, everyone, and welcome to the fourth and final recursion interview problem, the coin change problem. A quick note before we begin, this problem has multiple solutions, and it's actually a very classic problem, and it's classic because it shows some issues with basic recursion. So if you're having trouble with this problem, or it seems to be taking a long time to run in certain cases, really check out the solution notebook and fully read the conclusion link for a detailed description of the various ways to solve this problem. And then something to note, this problem is actually classic or common enough, it's famous enough that it actually has its own Wikipedia entry. So I've linked it here for you. So if you go ahead and click that link, it'll take you to the Wikipedia page, which is right here, and it says the change-making problem. And it's a knapsack type of problem, depending on how it's asked. But you can go ahead and check it out here, check out the mathematics behind it. Probably don't check out the pseudocode until you've had a good stab at it yourself. Okay, so let's go ahead and look at the problem statement. In this particular version, what we're going to say is given a target amount n and a list of distinct coin values, or an array of distinct coin values, what's the fewest coins needed to make the change amount? So for example, if I say n equals 10, your target, and then coins, your denominations are 1, 5, and 10, there's 4 possible ways to make change here. You can have 10 ones, a 5, and then 5 ones, 2 5s, and 10. So the minimum amount of coins you need is 1 coin, that 10, that dime. Okay, so in this case, I want you to implement your solution below. Here, I just have a simple recursion solution set up, so it takes in that target and then that list of coins. Right now it has pass, but you pass in the target and the coins, and you'll get the minimum amount of coins used. It should be noted that there's other versions of this problem that ask you different things, such as instead of asking what's the minimum amount of coins, they may ask you how many possible ways are there to make change. So they may be looking for this answer, 4 possible ways, instead of the minimum amount. Right now, we're focusing on the minimum amount because of its implications of dynamic programming and memoization. So the reason this is the last recursion interview problem is because it's one of the tougher ones if you approach it through a straight recursive mindset. You should really think about dynamic programming and memoization. So again, note the test cases here in this test cell is only going to test with 2 parameter inputs, the target and the list of coins. If you decided to use some sort of cache and that's a 3rd argument in your solution, this clearly won't work because your solution here, as far as the test cases, is only going to take in 2 arguments. So if your non-dynamic function is taking a long time to test and you believe you have a solution, you should go check the solution notebook instead of really running this cell. All right. So again, extra, best of luck. Remember to read the solution notebook for this once you think you have a solution. In the next lecture, we'll be discussing a notebook. It's a lot to read, so it's going to be a last homework assignment for this recursion section to fully read the Wikipedia entry and the entire notebook that really dives into this coin change problem. Because this is actually going to serve not just as an interview question, but a real learning example of dynamic programming, memoization, recursion, and really wrap up this section in a great way for you to learn everything we've learned in this section. So really go over all those topics. Okay, so that's it. Best of luck with the coin change problem. Once you think you've had a good stab at it and have your own solution, go ahead and go to the next lecture where we're going to discuss and go over everything we learned in this section. All right, thanks everyone. Best of luck. Hello everyone, and welcome to the lecture discussing the coin change problem and its solution. As always, there's a complete solution notebook here describing the solution to the notebook problem. This problem is actually common enough that it has its own Wikipedia entry, and it's a really famous problem in showing some of the issues with recursion in general and why dynamic programming and memoization is such a key tool to improving on basic recursion. So what we're going to do is go through basically 2 implementations of a solution. One is just a classic recursion that doesn't use memoization, so note the solution is not optimized, and then we go through a better solution. I would really encourage you to read through this entire solution notebook first, as well as read through, if you scroll all the way down to the notebook, there's an extra resource here, Dynamic Coin Change Problem. I would really recommend that you read that entire extra resource. It's just a page long that describes this exact same problem and why there are issues with normal recursion. And also there's the Wikipedia entry that's linked here that you can also read. And there's solutions as far as implementations with dynamic programming, and it's in Python, so you can read about it as well. All right, so let's go ahead and discuss the coin change problem then. We're going to go ahead and jump to some live code here and start by thinking about what the problem statement's actually saying. So we're given a target amount n. So some target amount of money we want to make or change we want to make. 56 cents, 50 cents, 45 cents, 46 cents, etc. And then we're giving a list or an array of distinct coin values. And we want to know what the fewest coins needed to make that change amount is. So for instance, if we jump back to the solution notebook, we can see here that if you have n equals 10, so your target number is 10, and you're giving values of 1, 5, and 10, there's 4 possible ways to make change. You can have 10 ones, a 5 and 5 ones, 2 5s and a 10. And the correct answer for the minimum amount is, of course, just 1 coin, that 10-cent coin. So what we're going to do is first do a classic recursion solution to this problem. And then we'll talk about what the issues are with that solution. So let's go ahead and get started. First, I'll start just by calling def rec_coin. I'm going to take in, I'll call it the target, and then the list of coins. So what I'm going to do first is think about certain base cases or certain scenarios where I should instantly return something. So one of those cases is if the target number is in coins. So for instance, in that last example, 10, the target, was actually in the list of coin values, you would just immediately want to return it. So we want to see if we have a single coin match. And in this case, we'll just return 1. So the minimum number of coins is 1. If that's not the case, what I'm going to do is set a default value here that the minimum number of coins is the target number. And what I'm going to do is actually recursively solve for that. And at the end of everything, I will return min underscore coins. All right. So let's go get started at what we actually want to do here. So in plain English, what I want to do is for every coin value in that coins list that is less than or equal to the target number, what I want to do is recursively call my function and add a count coin and then subtract from the target. And then I'll reset the minimum if I have a new minimum number of coins. So that's a little complicated, so let's go ahead and write it out. So I want to say for, let me go ahead and zoom in here so it's really clear. For every coin value that is less than or equal to my target value. So I want to say for I in, and then I'll make a list using list comprehension that's saying C for C in coins if C is less than or equal to that target. So here I'm saying I'm making a list comprehension that's grabbing all the coins for C, if C is less than that target number. And I'm saying for each of those basically coin values, I'm going to make a new variable called number of coins, the number of coins we need. And I'm going to recursively call 1 plus the recursive function here. I'm going to subtract the current coin I'm on and then pass in their coin values, which hasn't changed. And if the number of coins, it suddenly finds itself being less than the minimum number of coins, which we started off as the target number, I'm going to reset it. I'm going to say the min coins is now equal to the number of coins. So this is the full recursive solution. It's inefficient, but it will work for most cases, for cases that have American style coins. If you have odd coin values or weird prime values, such as like a coin that has value 7 or something like that, and you're looking for a distinct number, you may have an error solving with this recursive solution. And that's part of the problem we'll discuss in a second. But basically what's going on here, just to go over this basic recursive solution, which note is not actually the correct way to solve this problem. We have a default value for the minimum number of coins, and we set it to the target. We have what we can think of a base case, which checks to see if target is in coin values list, right? Otherwise, I'm saying for every coin value that's less than or equal to my target, so for every value in that list, I'm going to add a coin count. That's what this 1 is here. So I've already had to use a coin. And then I add it to the recursive call, where the recursive call is now a new target. I will subtract the value of that coin from it. So for instance, if I'm looking for 15 cents and I just subtracted a dime from it, my new target is now 5 cents. And again, I pass the list of coins, searching for that new minimum. And I will reset the minimum here if the new num coins is less than the min number of coins, which we set first as the target. And that's all there is for this recursion. Now, if we actually run this, you'll notice it takes a very long time to run for certain values. I'm going to do a basic example here. So I'll pass in 15 as my target value, 1, 5, and 10. I'll run it. It outputs 2, so that's correct. It needs 1 dime and then 1 nickel. But if I input something else, maybe something as 63, and I'll also pass in a quarter in value, it'll take much, much longer with this. And you'll notice the problem with this approach is that it's inefficient. It can take many, many recursive calls to finish this problem. So I'm going to go ahead and jump to the solutions notebook. I'm going to kill the cell by interrupting it. So I'm going to say kernel interrupt here. And then I'm going to clear its output, cell current output clear. And go ahead and jump back to the solution notebook to show you an issue here. So for instance, let's pretend that I'm looking to solve for 26 here. So if we look at the figure that's in the solutions notebook, each node here corresponds to a call to that recursive function. The label on the node indicates the amount of change for which we are now computing the number of coins to solve for. Now note how we're recalculating values we've already solved. For instance, 15 here is solved for 3 times. Over here, where my mouse currently is, over here, where my mouse currently is, and over here, where my mouse currently is. So it would be much better if we actually kept track of the function calls we've already made, so we don't have to constantly resolve for things we already know. And that's where the dynamic programming solution comes into play, that memoization that we discussed earlier in this section. And I'm going to zoom out so you can see the, whole equation here, or whole code. And the key to reducing the work time for the function is using this dynamic programming. So the better solution is to remember past results. That way, before computing a new minimum, we can check to see if we already know a result. And you won't have this straight recursion call where you look at results that you've already done in the past but haven't saved in memory. Now, something to keep in mind here is that while this is very efficient in time, it's going to be less efficient in memory since you're storing more results. Usually that's a trade-off you would want to make for a simple problem like this, but you really have to think of what's going on in the general scope of your problem that you're trying to solve and see if this is a good trade-off. Usually it is, especially in this context of an interview question. All right, so now what we're going to do is this function is going to take in 3 inputs. It's going to take in a target, coins, and then we're going to have a cache, known results. And instead of actually putting it outside the function, we're going to develop it inside the function. So let's go ahead and live code this dynamic programming solution so we can really understand why this is the best approach to solving this problem. We're going to go ahead and jump back to the live code. All right. So let's start by naming our function, rec underscore coin underscore dy dynam for dynamic. And in this case, we've taken 3 arguments, the target, the coins, and a new parameter, results, or known results. So I'm going to do the exact same thing I did last time. I'll set the default output to the target. So far, the minimum number of coins I need is whatever target number gets passed. And then I'm going to think of my base case. So what does that look like? Well, again, if I know the target is in the coins, then I'm going to say known results of that target, and I'm going to set that equal to 1, and then I'm going to return 1. So what's going on here, it means if I kept doing recursive calls and suddenly I find that the target number is actually in coins, then I'm going to set the known results at the target equal to 1. And then I'm going to continue on to what's the more complicated part, this actual recursive calls. And it's going to be an else if statement or an elif statement. And what I want to do here is I want to return a known result if it happens to be greater than 1. So if I know my known results at that particular target is greater than 0, then I'm just going to return that value. And this is the dynamic programming that's going to save you a lot of time in recursive calls. And hopefully it'll be clear once we go through the final else statement. So again, I'm going to say for every coin value that is less than or equal to the target. So for I in, and I'm using list comprehension again, C for C in coins if C is less than or equal to target. I'm going to make a recursive call, but pay attention here because I'm going to include the known results. So I'm going to say num of coins. It's going to look really similar to the last one. Another recursive call here, rec coin, in this case dynam. I pass in my target minus I, that current value that I'm on. The coins, the values we know doesn't change. And then I pass in my currently known results. And then I reset my minimum just like we did in the last one. So if my num of coins is less than my minimum number of coins, I can just say min coins is equal to the current number of coins. And here's where it comes into play. I will also need to reset that known result. I will have to say my known results at target is equal to the minimum number of coins. And then finally, I will return the minimum number of coins here. So let's go ahead and check that out. Let me fix a typo here. This should have been known results. Make sure results is plural on all of these. All right, let's see if this runs. Make sure there's no other typos in it. And we will call it on, let's say, an interesting target number, maybe 74. My coin values will be 1, 5, 10, 25. And I'm going to initiate my known results just like we did in that last memoization problem by a list of zeros of length target plus 1. And now, if I call my function on my target with my coins and my known results, you'll notice I get 8. Now, if I try doing that on that first function with just targeting coins, you'll note it's just taking forever to run because it's making a ton of recursive calls here. So I'll have to stop that cell from running. Okay, so if you notice, the notebook did have a test your solution, but no, it was designed for non-dynamic functions, and they will take a long time to test. So if you believed you had a solution, you should have come here and checked this. All right, so let's go ahead and briefly go over what we did here. We tried to create a normal recursive solution, but it would have failed because it would have taken so long because it kept making repeated recursive calls for results it actually had already previously calculated before, as we can see from this diagram of trying to figure out 26 here. All right, we came up with a dynamic programming solution that took into account our known results, but also solved a very similar recursive fashion, just like the first solution, except it updated its known results here, here, and here. And that's really the case of memoization dynamic programming. So once you've gone through this video, remember, you should really check out this great resource here, Dynamic Programming Coin Change Problem link at the bottom of the Solutions notebook. Read through it. It's a great walkthrough on the coin changing problem. Or you can also read the Wikipedia page entry here that also explains the dynamic programming solution. It does it in a little bit of a different fashion here by creating a matrix, but again, you should walk through it and make sure you understand it, because there's various ways of writing out this particular dynamic programming solution. All right, so your homework is to make sure you read both that Wikipedia entry and, if you scroll down here, this link here is to the dynamic coin change problem. It's going to be pretty similar to what we discussed here. It will also have this figure in it, but it's important to read it because it goes through a very slow and steady solution explanation for the case of dynamic programming there. All right, that's it for this section on recursive interview problems. Recursive interview problems, as far as the way they're presented in interview situations, sometimes they won't explicitly tell you to use recursion, but hopefully after completing this section, you have an idea of in your mind what situations would call for a recursive solution. And if you're ever confused in an interview situation, don't be afraid to ask of something like, hey, would recursion be a good call here if it's on the brink of your mind but you're unsure? Remember to ask a lot of questions, do your thinking out loud when you're in an interview situation. Other than that, as far as this question goes for the coin change problem, make sure you do that homework reading, and I will see you at the next lecture. All right, great job everyone on the interview questions. I will see you in the next section.
Hello everyone, and welcome to the lecture on Introduction to Trees. So in this lecture, we'll be going over what this section is about, and then we'll get a brief introduction to the data structure that is called a tree. So in this section, the tree section, we learn about tree data structures. We're going to implement trees with lists, and we're also going to implement trees using object-oriented programming, so classes. And then we're also going to implement a priority queue data structure, and then we're going to have some interview problems. There's going to be a lot going on in this section, but what I want you to know is this section only covers basics of trees and what's known as an abstract data type, or ADT. This topic in general is pretty vast, and it could easily warrant its own course, so just keep this in mind. But throughout the lectures, you'll get additional resources to check out in case you want to dive deeper into trees. So let's just talk about trees in general. The tree data structure has a root, branches, and leaves. So just like a tree in nature, you have a similar structure. The difference between a tree in nature and a tree in computer science, though, is that a tree data structure has its root at the top and its leaves at the bottom, so it branches downwards. So you've maybe have already seen these kind of tree data structures, so let's just look at a few common examples. Here we can see a tree as a classification tree from biology. So we have biological classification of some animals, so this is a pretty simple example, but we can learn about the properties of trees. So this example demonstrates that trees have a hierarchy, and they're structured in layers where more general things are near the top and more specific things are near the bottom. So here we have a hierarchy that's the kingdom, the phylum, the class, etc. So no matter how deep we go into the classification tree, we get all the organisms are still animals. So that's important to note here. Another second property of trees is that all of the children of one node are independent of the children of another node. And a third property is that each leaf node is unique. And we'll go more into what nodes are and what leaves are and what children are in the vocabulary section of this lecture. So another example of a tree structure that you probably use every day is a file system. So in a file system, directories or folders are structured as a tree. So here we can see an example of this, where you basically have just a small part of a Unix file system as a hierarchy. And just like that biological classification tree, you can follow a path from the root to any directory. And that path will uniquely identify that subdirectory, so all the files in it. And another important property of trees, also derived from that hierarchy, is that you can move entire sections of a tree, called subtrees, so there's a subtree here, to a different position in the tree without affecting the lower levels of the hierarchy. So for example, in this particular picture, you could take the entire subtree starting with etc., this etc/, and you could reattach it to under user here, USR. And important to note that it's not going to affect any of the children that are at the same level of this tree. Okay, so one final example is a web page. So if you're familiar with HTML, it also has a similar structure where the tree that corresponds to the HTML tags, you can use that to create a page. Okay, so I've mentioned some terms such as nodes, children, parents. What we're going to do now is go over some common vocabulary terms that you should know when discussing trees. So a node is a fundamental part of a tree. It can have a name, and you can also call that the key. So a node may also have additional information, and you can call that additional information the payload. So while the payload information isn't actually central to a lot of the tree algorithms we're going to be learning about, it's often critical in applications that make use of trees. Next term we're going to learn about is edge. So an edge, again, another fundamental part of a tree. It's an edge connects two nodes that show that there's a relationship between them. And then every node, except for that root node, is connected by exactly one incoming edge from another node. And each node may have several outgoing edges. So to show you what I mean by this, we're going to learn about one more, the root. So the root of the tree is the only node in the tree that has no incoming edges. So here we have kind of an illustration of a tree. It looks a little different because the children of the nodes are linked and attached to it, but that's just to show the hierarchy levels. So here we can see, there's a root node for you with two children, and each child has only one edge coming out of it, and it goes to the next level of nodes. And notice that the root node is the only node here that has no incoming edges. And then we can see children and then other nodes. So a path is an ordered list of nodes that are connected by edges. So if you look, for example, back to the biology tree that we were looking at, mammal to carnivores to other Felidae, Felis is a path there. So as you continue on and have an ordered list of nodes that are connected by edges, you have a path. And then children, formally, are a set of nodes, we'll call them C here, that have incoming edges from the same node too, and are said to be the children of that node. So for example, we can see here that the root node has two children, and then each of those childs goes to another node. Node 1 has 3 children, node 2 only has 1 child. And then we have parents. So a node is the parent of all the nodes it connects to with outgoing edges. So here you can see that child 1 is the parent of node 1. Sibling nodes in a tree are the children of the same parent are said to be siblings. So here child 1, child 2, and child 3 are all siblings of node 1. And then a subtree is a set of nodes and edges comprised of a parent and all the descendants of that parent. So you could loop around some subtrees here versus the entire tree. And then lastly, a leaf node is a node that has no children. So node 3, 4, 5, and 6 don't have any children, so they're leaf nodes, just like the leaf on a tree that doesn't have a branch extending out of it. Now what we're going to learn about is levels, not particular nodes. So the level of a node n is the number of edges on the path from the root node to n. So if we're looking at node 2 here, or node 1, they are both at level 1, since it only takes one path to get back to the root node. And then the height of a tree is equal to the maximum level of any node in the tree. So we've described all the parts of a tree, and now we're going to bring them together to form a full formal definition. And something to note here is the image I've been showing you about a root node of a tree goes along with this particular definition. So a tree consists of a set of nodes and a set of edges that connect pairs of nodes. So a tree has the following properties. One node of the tree is designated as the root node. So that was that top node in the picture, which if you go to the next slide, here it is. So every node n, except the root node, is connected by an edge from exactly one other node, p, where p is the parent of n. A unique path traverses from the root node to each node, and if each node in the tree has a maximum of 2 children, we say that that tree is a binary tree. And we'll learn more specifically about binary trees and binary search trees later on in this section of the course. So this figure illustrates that definition of the tree. The arrowheads on the edges indicate the direction of the connection. There's also a recursive definition of a tree. So you could say a tree is either empty or consists of a root and 0 or more subtrees. each of which is also a tree. So the root of each subtree is connected to the root of the parent tree by an edge. So to show you what I mean by that, here's kind of a simpler figure, and this is the recursive definition. So you have roots, and then you have subtrees. And as I mentioned, a tree is either empty or consists of a root and 0 or more subtrees. So if you remember back to the recursion section of the course, I mentioned that recursion can be used to define trees and define tree traversal algorithms. So it's important to also understand this particular definition. So here we know that in this figure, the tree has at least 4 nodes, since each of these triangles representing a subtree must have a root. So you have the root node, and then 3 subtrees, and we know each of these 3 subtrees also has a root, since we're dealing with the recursive definition right now. So we know we have at least 4 nodes. It may have many more nodes than that, but we don't know until we look deeper into the tree, which basically means making another recursive call. Okay, so let's just go over a review of everything we learned. We got a brief overview of what to expect for this section of the course. We went over some of the basics of trees and real-life examples. We also learned about vocabulary for trees and definitions for trees. And now we're ready to learn more about trees and learn about them to prepare for interview problems. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on tree representation implementation. So in this lecture, we're going to implement a tree as a list of lists. So this is probably the simplest way you can implement a tree in Python. It's not going to be the standard way of implementing a tree. We'll learn about nodes and references in a subsequent lecture, but for right now, just want to get a basic idea of how we could represent a tree in Python. So in a list of lists tree, we're going to store the value of the root node as the first element of a list. Then the second element of that list will actually be a list itself that represents the left subtree. And that third element, so this is going to be at index 2. Remember, you have 0, 1, 2 since indexing starts at 0. So that third element at index 2 of that list will be another list that represents the right subtree. So for instance, if you have a tree like this, you can represent it as a list of lists. Here A is at index 0, that's your root. And then notice at index 1 of this main tree list, you have B, and then again you have a list of lists representing trees. And notice how you have these empty sublists here, since D, E, and F don't actually have any children of their own. Okay, so that's what we're going to be implementing. So let's go ahead and get started. Hello everyone, and welcome to this lecture on representing a tree as a list of lists. So if you go to the folder for trees, you'll see a lecture or a notebook titled Tree Representation Implementation, in parentheses lists. So this is the code we're going to be going over. You'll notice it's actually just a series of functions. We're not going to be using any object-oriented programming or classes. We'll do that in the next implementation of a tree. But this is just to give you a basic idea of how we could implement a tree using lists, a built-in data structure in Python. So I'll be coding these functions out and explaining what each of them do along the way. All right, so I encourage you to follow along, so let's go ahead and get started. I'm going to start out by creating a function, and I'll call it binary tree. It's going to take in an argument r for the root node, and then it's going to return a list. And this list will have r, that root node, and then it's going to have 2 other empty lists. So what this function does is just simply constructs a list with a root node and then 2 empty sublists for the children. And now what we're going to want to do is if we want to add a left subtree to the root of a tree, we need to insert a new list into the second position of the root list. So you have to be careful here. If the list already has something in that second position, we need to keep track of it and then push it down the tree as the left child of the list we are adding. So let's go ahead and see the code for inserting a left child. So I'm just going to make each cell have a function in it. So I'm going to make a function called insert left. It's going to take in the root and then it's going to take in an object we'll call new branch. We'll set a variable t equal to root pop, and we'll pop out that index at 1, since that will be the left. And then we'll say if length of t is greater than 1, meaning it has something in it, I'm going to call root.insert, and we'll go over what that actually means in a second. We'll say root.insert 1, and then we'll also pass in new branch t and an empty list. Okay, so we know now what to do if there's already a list there. So we'll do an else statement to say root.insert, and keep in mind insert is just a method on a list. We'll insert new branch, and then we'll also pass in 2 empty lists, since there's nothing there yet. And then I'll return the roots that we basically affected. Okay, so notice here that to insert a left child, we first obtain a list, which could possibly be empty, that corresponds to that current left child. Then we add the new left child, installing the old left child as the left child of the new one. So this is basically allowing us to splice a new node into the tree at any position. So we're going to do another function called insert right, which is going to be really, really similar. So similar, in fact, that I'm going to copy this function and then show you the differences here. So if I'm inserting right, I'm actually going to pop in or pop out 2 here, since that's going to correspond to that right branch. Excuse me, right child. This actually stays the same, so if there's something already in there, I'm going to go ahead and insert at index 2 a new branch, and in this case I'm going to reorder these guys since I'm inserting on the right. So it goes new branch, an empty list, t, if there's already something in there. Otherwise, it goes index 2, and then the list that we're inserting here is new branch, empty list, empty list. So to round out this set of tree making functions, we're going to write a couple of access functions for getting and setting the root value, as well as getting the left or right subtrees. So this is just going to be a series of short functions. First one, let's say I want to get the root value. I'll make a function called getRootVal. It'll take in that list, that root, and it's just going to return the first item in that list at index 0. So that makes sense since we define the root as 0. Okay, then I want to say def set, if I want to set a new root value, I'll take in that root, and I will also take in a new value. All right, and the way I'm going to do that is just reassign index 0 there. So notice I'm not returning anything, I'm just resetting that root. And then if I want to get the left child, we'll say get left child, pass in the root, and the way we're constructing this, that's going to be at index 1. And you can imagine for getting the right child is going to be extremely similar, except we'll do it at index 2. So I'm going to say return root 2. Okay, so with this list of functions, we've actually already done a simple representation of lists. So let's go ahead and use them. So I'm going to say r is equal to binary tree. Let's pass it a value of 3. And then say, let's go ahead and insert left, pass in that root, pass in a value of 4. And here you can see we're actually building out the tree. So it's returning what the tree is looking like. So then let's go ahead and insert another one to the left. Again, we pass in that root. Let's put in 5. You can see how we're building out that tree. Let's go ahead and insert right. Let's say 6. Whoops, forgot to pass in that root. All right, then we're going to insert right. Let's go ahead and do another one. Let's just say 7. Again, got to pass in that root. Okay, and notice how we're building out that tree in a list of lists fashion. Now, normally you wouldn't do it this way. You'll use a class and object-oriented programming with nodes and references, which we're going to do in next lectures. But here we can actually just get a simple representation of a list purely through functions, a simple representation of a tree purely through the data structure of a list in Python. Okay, so you can see how we're inserting left and right, and it's building out that tree. So we can also say, for instance, L is equal to get left child, and we'll pass in the root node. And then let's go ahead and print L, see what it looks like. And you can see now what that left child off that root looks like. And we also mentioned we created a set root value. So I can pass in, for instance, that left child and set its root equal to 9. If I print R, notice now we've affected that by setting its root here, since it's still referencing that original tree. Okay, so that's it for the basics here. Go ahead and review this. Make sure you understand how you're building out this tree. It's pretty simple. You're just inserting left with index 1, checking to make sure if there's a list in there, how you build out that new branch. Otherwise, you build out an empty branch with no reference to that previous popped out list. And then right, same thing, except now it's at index 2. And then these simple methods are just basically indexing to grab left and right childs. Okay, that's it for this lecture. Thank you guys so much, and I'll see you at the next lecture. Hello everyone, and welcome to a lecture on the nodes and references implementation of a tree. So in this case, what we're going to do is define a class that has attributes for the root value, as well as the left and right subtrees, and then some methods within that class. Since this representation more closely follows object-oriented programming, or OOP, with classes in Python, we're going to continue to use this sort of representation for the remainder of the section of the course. So we won't do that list of lists representation. So just a reminder, this is the kind of tree we're going to try to implement using object-oriented programming with nodes and references. So you can see nodes of A, B, C. You have A as your root node, and it splits off into left and right children. And let's go ahead and go implement it. Alright, so now I'm here at the Jupyter Notebook representing a tree, nodes, and references. So as always, there's a reference notebook under the trees folder. This is the code we're going to be implementing here, and here's some examples of the code being used. So let's go ahead and get started. Okay. First thing we're going to do is start out with a simple class definition. So I'm just going to say class, call it binary tree, pass an object, and then start with its attributes. So the important thing to remember about this representation is that the attributes left and right will become references to other instances of the binary tree. So let's go ahead and make init, pass in self, and then I'm going to pass in, let's just call it root obj for root object. And I mentioned earlier that we sometimes call that root the key, so we'll go ahead and say self.key is equal to root obj. And as I mentioned before, we're going to have left and right attributes become references to other instances of the binary tree. So for example, when we insert a new left child into the tree, we're actually creating another instance of binary tree. In this case, we're going to just start off with no childs, or no children. So we're going to say left child equals none to start off with, and then say self.right child equals also none to start off with. Okay, So something to notice here is that the constructor function expects to get some kind of object to store in the root. Just like you can store any object you like in a list, the root object of a tree can be a reference to any object. Okay. Next, what we're going to do is look at functions we need to build the tree beyond that root node. So what I would want to do is have an insert left. It'll take self and then some new node. And I'm actually going to put in pass here for now. And then we're also going to have a insert right, and it would also take a self new node. And we'll put a pass there. So to add a left child to the tree, we're going to create a new binary tree object and set the left attribute of the root to refer to this new object. So in order to do that, we can start filling out insert left. So I'm going to say if self.leftChild is equal to none, meaning we don't have anything there yet, what I'm going to do is say self.leftChild is equal to a new instance of binary tree. In this case, with that root node being new node. Otherwise, similarly, when we're doing the list of lists, I'm going to set an object or a variable t, have it be equal to a binary tree with new node, and say t left child is equal to the self.leftChild. And then say self.leftChild is then equal to t. All right, let's go ahead and break down what this code is actually doing on the insert left. We're going to have to consider two cases for insertion. The first case is going to be characterized by a node with no existing left child. So self.leftChild is equal to none. When there's no left child, we're just simply adding a node to the tree. The second case is going to be characterized by a node with an existing left child, that else. So in the second case, we insert a node and push the existing child down one level in the tree. The second case is handled by that else statement. So make sure you review this and make sure you understand what's actually going on. First case, there's no left child, so we're simply adding a node to that tree. Second case, we have a node with an existing left child, so we insert a node and push the existing child down one level in the tree. So the code for insert right is going to consider a symmetric set of cases. There will be either no right child, or we must insert the node between the root and an existing right child. So let's go ahead and code that out. It's going to be really similar. I'm going to say if self.rightChild is equal to none, then we just insert that node. Right child is equal to an instance of binary tree with new node. And then we're going to say else t is equal to binary tree with that new node. Remember, we're going to push it down one, so we're going to say t right child. Let me scroll over. T right child is equal to self dot right child. Then finally, set self.rightChild equal to t. Reason for doing this is that so you don't accidentally overwrite something before you set it. Okay, so now to round out the definition for a simple binary tree data structure, we're going to write some methods that allow us to access things, such as the right and left children, as well as the root nodes. So this will just be 4 methods. Let's get some space here. I'm going to say get right child self, and then I'm going to return self dot right child. So that makes sense if we get the right child. Similarly, I'm going to do the same for the left child. So get left child calls self, and then it just returns self dot left child. I also want two functions for setting the root value and getting the root value. So for setting the root value, we'll just call it set root val. And it's actually going to need to take some object to set the new root value, and then we're going to say self.key is equal to that object that you pass. And then lastly, to get the root value, get root val, we just need to pass in self, and we're just going to return self.key. Okay, so let's go ahead and quickly review what we just did. We have our class binary tree. We start off with the attributes, set the key or equal to that root object, that root node, no children to start off with, and then we have two basically symmetrical methods for inserting left and right nodes. And you can see that we check if there's something there. If there isn't, we just set it equal to the new binary tree. Otherwise, we're going to push it down to the new level. And then we have four methods for getting and retrieving children, and also getting and retrieving root values. So let's go ahead and make a simple tree to show how this can work. First thing we're going to do is set R equal to an instance of binary tree, and we're going to set a string A. Whoops. Got an error here, and that's because I forgot to write this correctly. Sorry about that. Okay, so now everything's working. Remember, if you ever have two double underscores in Python, you also need to close them out. All right, going down, we have our binary tree R. So let's go ahead and just start off by getting that root value. So I can say by tab, get root val. Let's go ahead and close parentheses so we actually get something returned. All right, and there we have that root value. So if we say get child, such as left child, we shouldn't actually get anything. So that's a none. So if we actually print this out, you'll notice it turns none up. All right, so let's go ahead and try inserting a left child. So I'm going to say r dot insert left, call it b. So we've inserted something to the left. So if I say r dot get left child, you'll notice something interesting happens here. Remember, we actually get another instance of that binary tree. So what I could do is then call roots off of this. So I can say then get root value, and then that's how we get B. So with this nodes and reference systems, you're referring to subtrees again. So you have your main tree and then subtrees within it, which is why when you just call that left child, you got an instance of that binary tree. All right, so that's it for the basic implementation using nodes and references. What I encourage you to do is try to build out your own tree. So write a tree down, just a simple one on a piece of paper, and then see if using this implementation, you can actually code it out and insert the children correctly. All right, that's it for this lecture. I'll see you at the next one. Thank you. Hello everyone, and welcome to the lecture on tree traversals. So we're going to learn on how to traverse through a tree, and there's going to be three main methods for this: pre-order, in-order, and post-order. So we're going to start out by defining these three traversals more carefully, and then look at some examples where these patterns might be useful. So there are commonly used patterns to visit all nodes in the tree, these three. And basically the difference between these patterns is the order in which each node is visited. And like I mentioned before, they're pre-order, in-order, and post-order. So we'll start off with pre-order. So the definition of pre-order is that in a pre-order traversal, we visit the root node first, then recursively do a pre-order traversal of the left subtree, followed by a recursive pre-order of the right subtree. In an in-order traversal, we recursively do an in-order traversal on the left subtree, visit the root node, and then finally do a recursive in-order traversal of the right subtree. Post-order, recursively do the post-order traversal on the left subtree and the right subtree, followed by a visit to the root node. So if you notice, you're basically just changing when you visit the root node, and this will be more clear when we actually see coded out examples of this. What we're going to do now is learn through a quick example on how you might use pre-order. So let's go ahead and check out this tree here. So here we have a representation of a book as a tree. The book is the root of the tree, and each chapter is a child of the root. Each section within a chapter is a child of the chapter, and each subsection is a child of each section, and so on. So this figure here shows kind of a limited version of a book with only 2 chapters. And note that this traversal algorithm works for trees of any number of children, but right now we're just going to stick with binary trees for 2 children for each node. Alright, so let's start with, suppose you wanted to read this book from front to back. And a quick note, in the slides, there's notes about what I'm going to be talking about here, with text of what I'm saying as far as the code implementation of this, but I'm going to explain this with just a figure here. If you want to go ahead and follow along with text, you can download the slide from this lecture. But anyways, let's go back to the task at hand, trying to read this book from front to back. That's what the pre-order traversal gives you exactly for ordering. You're going to start at the root of the tree, the book node, and then you're going to follow the pre-order traversal instructions. You're going to recursively call pre-order on the left child, in this case it's chapter 1, and then recursively call pre-order again on the left child to go to section 1.1. Since section 1.1 has no children, you can't make any additional recursive calls there. Once you're finished with section 1.1, then you move up the tree to chapter 1. At this point, you still need to visit the right subtree of chapter 1, which is section 1.2. As before, we visit the left subtree, which brings us to section 1.2.1. Then we visit the node for section 1.2.2. With section 1.2 finished, we return to chapter 1. Then we return to the book node and follow the same procedure for chapter 2. So the code for writing these tree traversals is actually pretty elegant, given there's kind of 2 options to write it. This is the text of what I just said. So the base case here, as far as coding this out, is simply to check if the tree exists. So if tree, if we have a tree. Then if the tree parameter is none, the function is going to return without taking any action. Something to note here is right now we have this pre-order traversal algorithm as just a function. It's not a method. So note here how there's no self comma tree. This is a function outside of the implementation of binary tree class. So you could have also implemented this as a method. So here we can implement preorder as a method of the binary tree class. The internal method must check for the existence of the left and right children before making that recursive call. So it would look something like this. You would have preorder here, self. Here I'm just printing self.key, and then saying if self left child, if self.right child. So you might be wondering what's the best way to implement this, as a function outside of the class or as a method within the class. So implementing preorder or any of these traversal algorithms as an external function is probably better in this case. And the reason for that is that you're very rarely just wanting to traverse a tree. In most cases, you're going to want to accomplish something else while using one of the basic traversal patterns. So for now on, we're going to write the rest of the traversals as external functions. And moving on to post order, this algorithm for the post order traversal is nearly identical to the preorder, except that we're going to move the call to print to the end of the function. So you'll notice here, we're going to check if that tree exists, then do the recursive calls from post order on the left and right child, and then we get that root value. For in order traversal, we visit the left subtree, then followed by the root, so you're going to see that print root value, and then finally the right subtree. So notice that in all 3 of the traversal functions, we're simply changing the position of that print statement. And here I'm actually using Python 3 printing, so with the print function, just so it's a little clearer. So you'll notice here we have in order recursive calls after you check that the tree exists, but for an in order, that print function where you're actually getting that root value is in between the left and right calls. Okay. So now finally, for your homework assignment, You're going to implement each of these algorithms as a function. Remember, not a method, a function outside of that binary tree class. So you can go ahead and use the binary tree class we made in the last lecture. The code is in these slides for reference. So if you go throughout this presentation that we just went through, you'll see the code for each of these functions. Go ahead and implement them and then play with them and see how it changes the ordering of the print statements. Notice here I'm using Python 3 style printing, which you can import from the future module, or if you're just using Python 3, that's what you've been doing all along. All right, so that's it. Go ahead and download this PowerPoint presentation if you need the code for reference, or just look at the video as you're coding along, which your homework is to implement each of these 3 functions. Should be pretty simple. Once you've done one, you're basically just changing where you're getting the root value, or that root node. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to Priority Queues with Binary Heaps lecture. So we're going to switch gears a bit and talk about priority queues with binary heaps, and later on we'll see how that relates to trees. So we discussed stacks, queues, and Deques, and now we're going to talk about an important variation of a queue called a priority queue. So a priority queue acts like a queue in that you can dequeue or remove an item by removing it from the front. However, in a priority queue, the logical order of the items inside the queue are determined by their priority. So the highest priority items are at the front of the queue, and the lowest priority items are actually at the back. And then when you unqueue or enqueue, basically meaning adding an item to your queue, into that priority queue, the new item may actually move all the way to the front, depending on its priority. So the classic way to implement a priority queue is using a data structure called a binary heap. And the binary heap is going to allow us to both onqueue and dequeue, add and remove items from this priority queue on order of log n. So the binary heap has 2 common variations: the min heap, in which the smallest key is always at the front, and the max heap, in which the largest key value is always at the front. In this section and the next lecture, we're going to implement the min heap. Okay, so let's go ahead and get ready for the next lecture, where we're going to discuss the implementation, show some code throughout a presentation, and then you'll have a Jupyter notebook as a resource. So in the next lecture, you'll actually see a presentation, and you'll be able to refer to the code notebook. We're not actually going to live code it because there's a bit of an explanation to go through as far as what the binary heap is actually doing. All right, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the binary heap implementation lecture. Just so you know, all the code we're going to be going through in this presentation is already written out for you in the Jupyter notebook. Also, I highly recommend that you read through the Wikipedia article on binary heaps first before viewing this lecture. Let's go ahead and jump quickly to the browser to go over these 2 things. Okay, here we are at the Jupyter notebook. It's called binary heap implementation. And we're going to implement binary heaps with certain operations. The operations we're going to implement are just binary heap, which creates a new empty binary heap. We'll add an insert operation, which adds a new item to the heap. We'll have a find min operation that will return the item with the minimum key value, leaving the item in the heap. We'll have a del for delete min, which returns the item with the minimum key value and removes the item from the heap. We'll also have an isEmpty operation. Essentially, these are all methods in our class. And the isEmpty method was going to return true if the heap is empty, returns false otherwise. We'll have a size operation, which returns the number of items in the heap, and then a build heap list, which builds a new heap from a list of keys. Later on in the lecture, we'll actually discuss how the list data structure can be mashed up with a binary heap implementation. As far as the actual code, here it is, written out for you, so you can go ahead and check it out. We're actually going to be basically looking at each of these method chunks and explaining them as we go along throughout this video lecture. The other note I wanted to make was the actual binary heap Wikipedia article. So I highly recommend you actually just go ahead and read this first. Just read the introduction, and then go ahead and read both the heap operations on insert and extract, which are really similar to the ones we're going to implement. And you can go ahead and read about building a heap, but that's not super important for this lecture, but the heap implementation will probably be super useful since it also discusses how to implement it with an array, since we're essentially going to be doing the same thing, implementing it for list. So I highly recommend you just check out this article and read it. It's actually pretty straightforward, so definitely check it out. Okay, with that being said, let's go ahead and jump back to the presentation. Okay, so we're back at the presentation. Let's go ahead and continue. Alright, first thing we're going to do is, in order to make our heap work efficiently, we will take advantage of the logarithmic nature of the binary tree to represent our heap. In order to guarantee logarithmic performance, we must keep our tree balanced. A balanced binary tree has roughly the same number of nodes in the left and right subtrees of the root. In our heap implementation, we keep the tree balanced by creating a complete binary tree. A complete binary tree is a tree in which each level has all of its nodes. So let me show you an example binary tree. Here we have a complete binary tree, and you'll notice it begins to only have one node at this particular branch because it has an odd number of elements in it. What's another interesting property of a complete tree is that we can actually represent it using a single list. We do not need to use nodes and references, as we showed earlier, or even a list of lists, which was our other implementation. Because we know the tree is complete, the left child of a parent, let's say at position P, is the node that is found in position 2P in the list. Similarly, the right child of the parent is at position 2 times P plus 1 in the list. Let me go ahead and show you a figure of a complete tree with its list representation. So here you can begin to note that this 2p and 2 plus 1 relationship between the parent and children given this list representation. The list representation of the tree, along with the full structure property, allows us to efficiently traverse a complete binary tree using only a few simple mathematical operations, which we're going to see as we show you the implementation code. We will see that this also leads to an efficient implementation of the binary heap. So if we just look at this figure, we can see that we have 5 as a level at the root level of the tree, and then 9, 11 at the next level, 14, 18, 19, 21 at the next level down, and then 33, 17, 27. And we see here the pattern. We just have 0 as an index of 0, and then we continue on with the levels. So let me go over what I was talking about that 2p and that 2p plus 1. Let's say, for instance, we want to find out what are the children of the 9 node. So over here, the children are 14 and 18. Well, we have the index of 2 over here. So if we just want to say 2 times p, that parent value, is 2 times 2, which is 4. And here we have 14, which is the left child. If we want to find the right child, we just have to say 2 times p plus 1. P just stands for that parent position. So 2 times 2 plus 1 is 5, and then we get 18. Let's go ahead and try that one more time. Here we have 18. Let's say we want to find out the left child. That's just going to be 2 times p, which is going to be that 5 index, times 2, which will bring you over to 10, which is 27 element, which you found and matches correctly. You can go ahead and reference that Wikipedia article I mentioned earlier in case you want a full mathematical breakdown of that 2p and 2p plus 1, but hopefully here you can see that it's pretty straightforward and basic. So again, let's just go ahead and choose one other number. We'll say 11. So 11 is at position p equals 3. If I wanted to find the right child of 11, I would say 2 times p plus 1. So that's going to be 3 times 2, which equals 6, plus 1 is 7. So I go to index 7, and here I found 21. So this is pretty cool in the fact that I just need to use a single list. I don't need to use those nodes and references or the list of lists implementations that we saw earlier in this section of the course. So keep that in mind. It's going to be really useful as we implement our binary heap. And again, just a quick reminder, as we continue on, you can use the Jupyter Notebook to reference the complete code. I'll be showing you just screenshots of sections of the code. First off is going to be the class bin heap, And as I mentioned, we're just going to use a list representation. So I have self.heap_list equals to just a single number 0 there, and self.current_size equals 0. So we have heap list as just a single element of 0 in the list, and then the current size is 0. And what I wanted to point out here is that the next method we're going to implement is insert. And before we implement insert, let me go back real quick and clarify every step that's going on here. We're beginning our implementation of a binary heap just with this simple constructor, that bin heap. And since the entire binary heap can be represented by a single list, as we just saw, all the constructor will do is initialize the list and an attribute current size to keep track of the current size of the heap. So you will notice that an empty binary heap has a single 0 as the first element of the heap list. And this 0 is not used, but is there so that simple integer division can be used on in later methods. So if we go back real quick, you notice that 0 here, this is really just for simplifying and all the other methods we're going to be using later on for integer division purposes. Okay, let's go ahead and keep moving on. So we have our constructor ready to go, that class bin heap, and we have that heap list and current size. Now the next method we'll implement is insert. The easiest and most efficient way to add an item to a list is just to simply append the item to the end of the list. The good news about appending is that it guarantees that we will maintain the complete tree property. However, the bad news about appending is that we will very likely violate the heap structure property. However, it is possible to write a method that will allow us to regain the heap structure property by comparing the newly added item with its parent. If the newly added item is less than its parent, then we can actually swap the item with its parent. Let's go ahead and see the series of swaps needed to essentially percolate the newly added item to its proper position in the tree. Okay, so here we have our complete tree, and we just added a new item 7 as the right child of 18. So what we're going to do is keep doing swaps and essentially percolate it, the new node, up to its proper position. So meaning we do one swap here and another swap here. And notice that when we percolate an item up, we are restoring the heap property between the newly added item and the parent. We're also preserving the heap property for any siblings. Of course, if the newly added item is very small, we may need to swap it up another level. In fact, we may need to keep swapping until we get to the top of the tree. In this case, we don't, because it's just 7, and the root was 5. So this is just everything I just said as far as having to keep swapping to go up to the top of the tree. And as far as the method for insertion, this is what it looks like. We have this perk up method, and we're able to use this simple integer division here due to the fact that we're using just that simple heap list. So we just say if the heap list is less than, well, the heap list at that index is less than the heap list at that index integer division 2, then we set up this temporary variable as that integer division 2, and this is just to deal with classic division versus floating point division, just so we always have an index coming out here. And then we essentially just reassign it to that original index and then set the old index to the temporary variable. This is just a switching that's happening here. And then we just set I equal to I classic division divided by 2. And then we are ready to write the insert method. So most of the work in the insert method is actually really done by that perk up method we just saw. Once a new item is appended to the tree, perk up takes over and positions the new item properly. So you can see here in the insert, we just append k, say the current size plus 1, and then we call that perk up function or method to help us out and do the heavy lifting of the actual inserting that's going on. So with the insert method properly defined, we can now look at the delete min method. So since the heap property requires that the root of the tree be the smallest item in the tree, finding the minimum item is actually pretty easy. The hard part of delete min is then restoring full compliance with the heap structure and heap order properties after the root has been removed. We can restore our heap in 2 steps. First, we will restore the root item by taking the last item in the list and moving it to the root position. Moving the last item maintains our heap structure property. However, we have properly destroyed the heap order property of our binary heap. Second, we will restore the heap order property by pushing the new root node down the tree to its proper position. So let's go ahead and check out the series of swaps needed to move the new root node to its proper position in the heap. So here in this figure, we just decided to remove that minimum element, which is 5. And in this case, we're going to begin to doing some swapping. So we'll do one swap from this 9 to the root, and then we have 27 being swapped to go to that place. Then we're going to swap 14 and 27 to move 14 up, essentially percolating it up. And then you'll notice we have to do another swap since 27 is still greater than 17. In order to maintain the heap order property, all we need to do is swap the root with its smallest child less than the root. After the initial swap, we may repeat the swapping process with a node and its children until the node is swapped into a position on the tree where it is already less than both children. So here's the full code for percolating a node down the tree, and it can be found in both perk down and the min child methods here. I'll let you go ahead and check those out on your own, but it's essentially just doing those swapping mechanisms that we just described, which then just leads us to the code for that delete min, and you can note again that most of the heavy work is going to be done by this perk down method. So here's the code for delete min. So when you call delete min, you're just setting that return value equal to heap list 1. Remember, because heap list 0, that index at 0 just always stays 0, meaning heap list at 1 is your root node, which is the minimum element in your heap structure. So you have that return value, and you go ahead and return that return value at the end. But before you do that, you say heap list at 1 equals self.heaplist self.current size, and then self.current size equals self.current size minus 1. So you readjust your size because you just got rid of an element. You say heap list.pop, and then you perk down. And perk down just follows this method of swapping, and as well as getting that minimum child finding. Okay, the reason we have the minimum child here as well is because perk down needs to call it in order to find it. Continuing on, to finish our discussion of binary heaps, we will look at a method to build an entire heap from a list of keys. The first method you might think of may be like the following. Given a list of keys, you could easily build a heap by inserting each key one at a time. Since you are starting with a list of one item, the list is sorted, and you could use binary search to find the right position to insert the next key at a cost of approximately order log n operations. However, remember that inserting an item in the middle of the list may require order n, or linear, operations to shift the rest of the list over to make room for the new key. Therefore, to insert n keys into the heap would require a total of n times log n big O operations. However, if we start with an entire list, then we can build a whole heap in just order n operations. So there's the code to build a heap. You can check it out in the Jupyter Notebook as well. But let's go ahead and show a diagram of what this is actually doing. So we're actually going to essentially build a heap from the list that looks like this, 9, 6, 5, 2, 3. So what happens here is the swaps that the build heap method that we just saw in the last slide makes as it moves the nodes in an initial tree of 9, 6, 5, 2, 3 into their proper positions. And although we start out in the middle of the tree and work our way back towards the root, that perk down method ensures that the largest child is always moved down the tree. Because the heap is a complete binary tree, any nodes past the halfway point will be leaves, and therefore have no children. Notice that when I is equal to 1, we are percolating down from the root of the tree, so this may require multiple swaps. As you can see in the rightmost two trees, so these two trees over here, first the 9 is moved out of the root position, but after the 9 is moved down one level in the tree, perk down method ensures that we check the next set of children farther down in the tree to ensure that it is pushed as low as it can go. meaning we're checking here against 3 to continue pushing it down. So note now that 9 has been moved to the lowest level of the tree, no further swapping can be done. And it's useful to compare the list representation of the series of swaps, as shown in this figure here, with the tree representation. Something that might seem a little strange is when I said that we can actually build a heap in order n or linear time. The proof of how that actually works is really beyond the scope of this course and interviews in general. However, just to note, the key to understanding that is that you can build a heap in linear time because that log n factor is derived from the height of the tree. For most of the work in that build heap function or method, the tree is actually shorter than log n. And then using the fact that you can build a heap from a list in linear time, what we're going to do is construct a sorting algorithm that uses a heap and sorts a list in n log n time. Okay, so I know we went through quite a bit and that was some pretty heavy stuff, so make sure you review the Jupyter Notebook and the Wikipedia article. This lecture is going to lead into the next topic, binary search trees. Go ahead, take your time with this. This is a lot of information to just take in one single, essentially 20-minute span. So if you want to review this, again, I suggest you check out the basics of that Wikipedia article, open up your Jupyter Notebook, and try to type along as you see the figures. So you can slow down the video or just pause the video and see if you can type along with your Jupyter Notebook and the figures you see to correspond the code to the actual logic and diagrams that is happening with those methods. Okay, that's it for this lecture. Thanks. I know it was a long one and a lot of information, so take your time in reviewing it. Thanks. Hello everyone, and welcome to the Binary Search Trees lecture. So just to give you a bit of a background, we've already seen two different ways to get key value pairs in a collection. You can recall that these collections implemented the map abstract data type. The two implementations of a map abstract data type, or ADT, that we discussed were binary search on a list and then hash tables. In this section, what we're going to do is study binary search trees as yet another way to map from a key to a value. In this case, we aren't interested in the exact placement of the items in the tree, but we are interested in using the binary tree structure to provide for efficient searching capabilities. That means up next, we're going to go over the implementation of a binary search tree. We won't live code this due just to the sheer amount of code. It's going to be a lot of code. So instead of having to live code it all out, what we're going to do is instead go through each block and explain it through diagrams, just like we did in a few previous lectures. Again, if you do want to access all the code, it's written out for you in the Jupyter Notebooks, and I'll be sure to show you those links when we go through the next lecture on binary search tree implementation. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Implementation of Binary Search Trees lecture. This is going to be a two-part lecture. You can refer to the Jupyter Notebook for the code discussed in this lecture. We'll be jumping to the Jupyter Notebook from time to time to discuss larger chunks of code. You can also refer to the Wikipedia article on BST or binary search trees for more information on this subject. In this two-part lecture, we're going to be going over an overview of binary search trees and also an implementation of them in Python. Let's go ahead and get started. A binary search tree relies on the property that keys that are less than the parent are found in the left subtree, and keys that are greater than the parent are found in the right subtree. We're going to call this property BST property, the fact that keys that are less than that parent node are found in the left subtree, and keys that are greater than the parent node are found in the right subtree. So in an interview setting, when someone mentions BST or BST property, think of that specific property, that keys that are less than the parent go left, keys that are greater than the parent node go to the right subtree. As we implement the map interface as described above, that BST property is going to be our guide to implementation. So we'll see it crop up again and again. So here we have an example of a tree. And notice that the BST property here holds. So every node, and if you look to the left and right of the node, you have that BST property. All keys in the left subtree are less than the key in the root. All of the keys in the right subtree are greater than the key in the root. Notice that this BST property only refers to the direct parent, not the entire tree. So, just to reiterate this really important property, all of the keys in the left subtree are less than the key in the root. All of the keys in the right subtree are greater than the key in the root. So, now that you know what a binary search tree is, we will look at how a binary search tree is constructed. The search tree in the figure here, which is the last one I showed you, represents the nodes that exist after we have inserted the following keys in the order shown: 70, 31, 93, then the next level, 94, 14, 23, and 73. Since 70 was that first key inserted into the tree, it becomes the root. Next, 31, since it's less than 70, becomes the left child of 70. 93 is greater than 70, so it becomes the right child of 70. Now we have two levels of the tree filled, 70 level and then that 3193 level. So the next key is going to be the left or right child of either 31 or 93, which is where 14, 73, and 94 come into play. Since 94 is greater than 70 and 93, it becomes the right child of 93. Similarly, 14 is less than 70 and 31, so it becomes the left child of 31. 23 is also less than 31, so it must be in the left subtree of 31. However, it is greater than 14, so it becomes the right child of 14. So keep that in mind, and you can go back and reference these slides for that list ordering of the way the keys were inputted into this binary search tree. In order to implement the binary search tree, we will use the nodes and references approach similar to the one we used to implement the linked list and the expression tree. So go ahead and review that lecture on the nodes and references implementation in case you need to review it. However, because we must be able to create and work with a binary search tree that is empty, our implementation is actually going to use two classes. The first class we're going to call binary search tree, and the second class we will call tree node. You can begin to reference the Jupyter Notebook if you need to, but in this case, the binary search tree class has a reference to the tree node that is the root of the binary search tree. In most cases, the external methods defined in the outer class just simply check to see if the tree is empty. If there are nodes already in the tree, the request is just passed on to a private method defined in the binary search tree class that takes the root as a parameter. In the case where the tree is empty or we want to delete the key at the root of the tree, we'll have to take a special action. And we'll discuss all of this in much more detail as we jump back and forth from the Jupyter Notebook. But the basics of the class we implement called binary search tree look like this. We have this init method which takes in none and sets the root as none, and then also starts off the size as 0. So it's totally empty, has none as the root. Then we return length as just a method to return size, and also we use this special method __len, and it also returns size, but that allows you to use the len length built-in method in Python on your binary search tree. We also have this special method called iter, which allows you to iterate through the binary search tree, and we'll call that on root as well. Let's go ahead and jump to the notebook to check out the full tree node class and just go over some of the code. Okay, here we are at the binary search tree's notebook. You'll notice we have the class tree node with some basic methods. There's quite a few of them, so that's why we didn't have them in the presentation. But it's the basic ones that we discussed earlier, such as has left child, is root, is leaf. And these methods just do exactly what they say. They check if it has a left child, they check if it has a root, or if something is a root, returns if it has any children, etc. And the binary search tree is just taking advantage of that tree node class as well, which is why we split it up. Go ahead and review the nodes and references implementation of a tree in case you want to refer to the tree node class here and get a little more background understanding on it. Throughout the rest of this two-part lecture, we're going to be focusing on some of these special methods such as putting items into our binary search tree, getting items, and then what's a little tricky is deleting items from a binary search tree and splicing them out, and this find successor method. Also, removing items from a binary search tree is a little complicated, and there's a couple of cases we need to consider there. So we'll be going over those in much more detail. But just as far as the basics of what the tree node class looks like, it just basically has left and right child methods and isRoot and isLeaf methods, which are essentially just checks or returns of self.rightChild or self.leftChild. So go ahead and review that in the notebook, but for right now, let's go ahead and go back to the presentation and discuss some specific methods used here. Okay, now that we have that binary search tree shell and that tree node class, it's time to write the put method that will allow us to build our binary search tree. The put method is just a method of that binary search tree class. Again, you can refer to the Jupyter Notebook, but we'll also have screenshots of some of the code methods here. This put method will check to see if the tree already has a root. If there's not a root in place, then we just put the new tree node and install it as a root of the tree. If a root node is already in place, then put calls the private recursive helper function put to search the tree according to the following algorithm. So what it's going to do, it's going to start at the root of the tree, search the binary tree comparing the new key to the key in the current node. If the new key is less than the current node, we'll go to the left subtree. If the new key is greater than the current node, we search the right subtree. And that's due to that BST property that we were talking about earlier. When there is no left or right child to search, then we've actually found the position in the tree where the new node should be installed. To add a node to the tree, we create a new tree node object and insert the object at the point discovered in the previous step. So this is the code that does all that. Notice we have essentially two put methods, one with an underscore and one without the underscore. The one without the underscore is just for code factoring or refactoring reasons, so it looks a little nicer, and we use the underscore.put as a helper function to do that heavy lifting. So again, what's happening in this code is we start at the root of the tree, we search the binary tree comparing that new key to the key in the current node. If the new key is less than the current node, we search the left subtree. If the new key is greater than the current node, we search the right subtree. When there is no left or right child to search, we know we've found the position in the tree where the new node should be installed. To add a new node to the tree, we just create a new tree node object, which you can see that happening here and here, depending where it goes. We also have the self.root equals tree node in case there's not a root already in place, which is essentially what the put with no underscore does by itself. It checks if there's a root. If there is, it calls that helper function. Otherwise, it just adds the tree node there. Note that this underscore put function is written recursively following the steps I just mentioned. Also notice that when a new child is inserted into the tree, the current node is passed to the tree as the parent. One important problem with our implementation of insert is that duplicate keys are actually not handled properly. As our tree is implemented, a duplicate key will create a new node with the same key value in the right subtree of the node having the original key. The result of this is that the node with that new key will never be found during a search. So a better way to handle the insertion of a duplicate key is for the value associated with that new key to replace the old value. For right now, we'll just ignore those duplicate subkey scenarios, but you can go ahead and explore and fix that code if you wanted to check for a duplicate key, and then replace the old value with it. And then here we just show a screenshot of that set item method, which allows us to use the key value. And this is what inserting a node of key 19 would look like in a tree. So we go around, check which ones are filled, which ones aren't filled. So here at 29, we can see that 19 is less than 29, so it would be inserted into the left subtree. Once the tree is constructed, the next task is to implement the retrieval of a value for a given key. The get method is even easier than the put method because it simply searches the tree recursively until it gets to a non-matching leaf node or finds a matching key. When a matching key is found, the value stored in the payload of the node is returned. So this is the code for that get, and then it also has its own underscore get helper function. The search code for the underscore get method, the second one, uses the same logic for choosing the left or right child as that underscore put, that helper put method used. Notice that that underscore get method returns a tree node to the original first get method. And this allows the underscore get to be used as that flexible helper method for other binary search tree methods that may need to make use of other data from the tree node besides just the payload. And by implementing this special method, underscore underscore get item underscore underscore, we can write a Python statement that looks just like we're accessing a dictionary. So that basically allows us to use the bracket notation that you use in a dictionary when you call a key from a dictionary. So that's why this is here. Using get, we can implement an operation by writing that underscore underscore contains underscore underscore method for the binary search tree. Again, this is a special method, and the contains method will simply call get and return true if it gets a return value or false if it returns none. So we'll have a couple special methods throughout the binary search tree. You can go ahead and check them out if you want more details from the Python documentation, but you can essentially just read the code and assume that they're allowing us to use built-in methods or syntax with Python for our specially created binary search tree class. So finally, we're going to turn our attention to the most challenging method in the binary search tree, and that's the deleting of a key and the removal of a key. This is what we're going to be discussing in part 2 of this lecture. But just to give you an idea of what we're going to do, that first task for deleting a node is to find the node to delete by searching the tree. And then if the tree has more than one node, we're going to use the underscore get method to find the tree node that needs to be removed. So in the next part of this 2-part lecture, we're going to be talking about deleting nodes and removing nodes. Okay, go ahead and review the Jupyter Notebook and the slides that we've gone over so far. So far we've gone over just get and put, and also just building out our basic binary search tree and using that tree node class representation. Okay, thanks everyone. I'll see you at the second part of this lecture, where we're going to go into deleting nodes from our binary search tree in more detail. As far as what you should have gotten out from this lecture, definitely that BST property, where keys that have a value less than the parent node go to the left, and keys that have a value greater than that parent node go to the right. That's really the key to remember binary search trees. Alright, thanks everyone. I'll see you at the next lecture. Hello everyone, and welcome to part 2 of the implementation of binary search trees lecture. In this part 2, we're going to focus on deleting and removing nodes. Let's go ahead and jump to that section of the presentation. Okay, so as we mentioned in the last lecture, we finally have turned our attention to the most challenging method in the binary search tree, which is deleting a key. The first task is to find the node to delete by searching the tree. If the tree has more than one node, we can search using the underscore get method to find the tree node that needs to be removed. So underscore get method is that helper function we described in the previous lecture. If the tree only has a single node, that means we're removing the root of the tree, but we still must check to make sure the key of the root matches the key that is to be deleted. In either case, if the key is not found, that del delete operator will raise an error. So here's what that basic delete method looks like. We can walk through the basics here. We'll check if self.size is greater than 1 to call the node to remove using the underscore get and passing in the key as well as the root. We'll say if node to remove, then we just remove it and set the size equal to size -1. Otherwise, we raise a key error saying the key isn't in the tree. Then we have an else if or elif statement here. We'll say if the size is equal to 1 and the root key is equal to the key, then we reset the root equal to none and subtract 1 from the size of the tree. If neither of these cases turns out to be true, then the key is not in the tree and we raise a key error. This special method, del item underscore underscores surrounding it, just allows us to use that del special delete operator in Python. Again, this is just a special method. Once we've found the node containing the key we want to delete, there's going to be 3 cases to consider. The first one is that the node to be deleted has no children. So for instance, if we wanted to take this tree and delete the node here 16, which doesn't have any children, this is going to be the simplest case. This first case is just straightforward. All we have to do is say if the current node has no children, we just delete the node and remove the reference to this node in the parent. And that's what we're doing in this section of the code. You can refer to the Jupyter Notebook for the entire deleting code, but here we're just going to take it little bits by little bits. So here we're just saying if it is a leaf, if that's true, then if current node is equal to the current node's parent left child, then we just set the left child equals to none. Otherwise, it's the right child, so we set the right child equal to none. Here we're just checking if it's a leaf, meaning it has no children. That's the first case. The second case is that the node to be deleted has only one child. So for instance, if we wanted to delete here node 25, which you can see only has a single child, that right child. The second case is just slightly more complicated. If a node has only a single child, then we can simply promote the child to take place of its parent. Meaning, if we look back here, we can think of this that instead of removing 25 altogether, we're removing it but still just replacing it with 35. So removing this person, or this node, one up and replacing it, if the node to be deleted only has one child. So let's go ahead and jump to the code to discuss this second case, because it's a little too much to fit here on the screen in the presentation. So here we are at the binary search tree. If we just go ahead and scroll down here and go all the way to the remove method in the binary search tree, and we can zoom in on this guy. What we're going to be discussing is this section. The node only has one child. So here we just do a couple checks, and we essentially do the following. If the current node is a left child, then we only need to update the parent reference of the left child to point to the parent node of the current node, and then update that left child reference of the parent to point to the current node's left child, just that replacing switch. If the current node is a right child, then we only need to update the parent reference of the right child to point to the parent of the current node, and then update the right child reference of the parent to point to the current node's right child. So we're just exchanging the pointers here as we remove a node. If that current node has no parent, then it's actually the root. In this case, we just replace the key, payload, left child, and right child data by calling replace node data method, which is going to be over here, replace node data or replace node data, depending if it's a left child here or if the current node even has a left child. So this is the case for if it only has one child. You can go ahead and review this code, but you can essentially just think about it as pointing the parents and the children to each other as we basically pop out one of those nodes. The figure explains it probably a little more clearly, but here's the actual code that implements this. Alright, again, it's quite a bit of code, so just go through it slowly if you want to understand every single step that's going on here. Let's go ahead and jump back to the third case of deleting an item. Okay, the third case is that the node to be deleted has two children. So imagine here we wanted to delete the 5 node that has 2 children. We'll have to choose a successor for it. That means this third case is the most difficult case to handle, and it may be one of the most common cases, which is unfortunate since we need to think about how to handle this specific case. If a node has 2 children, then it is unlikely that we can simply promote one of them to take the node's place. We can, however, search the tree for a node that can be used to replace the one scheduled for deletion. So what we need to do is we need a node that will preserve the binary search tree relationship, that BST property, for both the existing left and right subtrees. The node that will do this is the node that has the next largest key in the tree. We call this node the successor, and we will look at a way to find the successor shortly. But let's talk about that successor. The successor is guaranteed to have no more than one child, so we know how to remove it using the 2 cases for deletion that we just discussed and implemented. Once that successor has been removed, we simply put it in the tree in place of the node to be deleted. Notice that we make use of the helper methods in the actual Jupyter Notebook code, find successor and find min, to find that successor. To remove the successor, we make use of the method splice out. The reason we use splice out is that it goes directly to the node we want to splice out and makes the right changes. So here we have just a little snippet of that code. And in this case, you can see the helper functions. So we say if current node has both children, meaning it's deleting node's case 3, it has both children, we set this variable succ for the successor to the current node.findSuccessor. So we're going to have to use that findSuccessor method in order to find the appropriate node to replace. And if we go back real quick to the figure we discussed, here you can see in this particular case, the successor was 7. And 7 works because it has 2, which is less than 7 on the left, and 11, which is greater than 7 on the right. So it's the immediate successor if we go down from 5 that works here. Okay, let's go ahead and check this out in the Jupyter Notebook. So I'm going to jump to find successor method in the Jupyter Notebook. Okay, so here we are at that find successor method. If you can see here, the code to find successor is just a method of that tree node class. And this code makes use of the same properties of binary search trees that cause an in-order traversal to print out the nodes in the tree from smallest to largest. Okay, there's going to be 3 cases to consider when looking for the successor. 1, if the node has a right child, then the successor is the smallest key in the right subtree. So that's what's happening here. If we have a right child, the successor is going to be find min off that right child in that right subtree. If the node has no right child and is the left child of its parent, then the parent is the successor. If the node is the right child of its parent and itself has no right child, then the successor to this node is the successor of its parent, excluding this node. The first condition is the only one that matters for us when deleting a node from a binary search tree. However, the find successor method has other uses that we're going to explore later on. The find min method, if we scroll down here, is called to find the minimum key in a subtree. Using what we know about the BST property, we can convince ourselves that the minimum valued key in any binary search tree is simply the leftmost child of the tree. Therefore, this find min method simply follows the left child references in each node of the subtree until it reaches a node that no longer has a left child. Alright, with that being said, we just have a few more methods to cover, so let's go ahead and look at them. Okay, one last method. If we need to look at one last interface method for the binary search tree, and that's because suppose that we would like to simply iterate over all the keys in the tree in order. This is definitely something we've done already in dictionaries, so why not trees? You already know how to traverse a binary tree in order using the in-order traversal algorithm we discussed earlier in this section. However, writing an iterator requires a bit more work, since an iterator should return only one node each time the iterator is called. So here's the iter method, the special method that we can use. And Python provides us with a powerful function to use when creating the iterator. The function is called yield. Yield is similar to return in that it returns a value to the caller. However, if you're familiar with generators versus iterators in Python, yield also takes the additional step of freezing the state of the function so that the next time the function is called, it continues executing from the exact point it left off earlier. Go ahead and search for iterators versus generators in Python if you want more information on this yield keyword. But for our situation here, what we really care about is that it takes that additional step of freezing the state of the function, so next time you call yield, it just continues executing from the exact point it left off earlier. Functions that create objects that can be iterated are called those generator functions. Here's the code for in-order iterator of a binary tree. And if you look at this code carefully, at first glance, you might think that the code is not recursive. However, remember that this __iter__ method overrides that for x in operation for iteration. So it really is recursive. Because it is recursive over tree node, instances the __ special iter method is defined in that tree node class, which you can check in your Jupyter Notebook. Go ahead and review this code in the Jupyter Notebook in the larger picture of how to iterate through the tree, and make sure you review the in-order traversal algorithm for this to be really clear. But I'll let you go ahead and read this on your own through the Jupyter Notebook and really take your time with it. And keep in mind that it actually is recursive because of the way we're using this iter special method. Alright, we've covered a lot of ground. Make sure to review the Jupyter Notebook and review the Wikipedia article on binary search trees. As far as implementing a binary search tree, it's going to be pretty rare for you to have to implement something as thoroughly as we just did here, but you may be asked to implement your own traversal algorithms in order, etc. So up next, we'll have some interview problems to reflect some common tree questions that you might find in a tree interview setting. Alright, thanks everyone. Again, make sure you review the Jupyter Notebook, the Wikipedia article on binary search trees, and the 2 lectures here, the part 1 and part 2, to really understand binary search trees. Thanks, and I'll see you at the next lecture.